Good morning, ladies and gentlemen. We have to begin the workshop. To all participants, please be seated in front of the chair. And all participants in the outside room, please enter the room. If you have the register in registration. Thank you. We will begin in 2 minutes.
And to all participants, please fill the front row chair first.
Check.
If you have already registered, please enter the room and fill the first row. May we have your attention? The workshop is about to begin. To all participants, please enter the hall and be seated. And please fill the front row first. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Good morning, distinguished guests, esteemed professors, researchers, and to all participants offline and online. A warm welcome to the second PlateauPlus workshop BMKG ITPCAS TPESR.
And ladies and gentlemen, we also want to welcome you to BMKG. Welcome to Jakarta, Indonesia, and we hope all participants have a wonderful time here. My name is Mario, and my partner is Gloria, and we are deeply honored to be your master of ceremony for this today event.
Ladies and gentlemen, this second PlateauPlus workshop serves as a vital platform for fostering international collaboration and sharing cutting-edge research.
And through the exchange of ideas and findings, our goal is to enhance scientific efforts related to plateaus and mountain belts, ultimately contributing to better hazard mitigation and sustainable regional planning.
Ladies and gentlemen, before we start the agenda, for our mutual safety, let us first take a look of the safety instruction in the BMKG auditorium. Please watch the safety briefing.
Welcome to the BMKG Jakarta Auditorium. Here is some information of safety instructions in the BMKG Jakarta Auditorium. Right now, we are currently in the BMKG Auditorium room, which is located on the first floor of the A building BMKG. In case of an emergency situation like earthquake, immediately drop, cover, and hold. Drop so you don't get knocked off your feet. Cover your head and neck. Get under a desk or a table if you can and hold until after the shaking stops. After the shaking stops, we can get out through the available doors. The BMKG auditorium has several exits that can be used. First, we can exit through the main doors behind you. Simply walk down to the ground floor using the stairs, and then exit to the parking area of the BMKG auditorium building. Secondly, you can also use the path behind the podium, heading to the main BMKG building and going down to the lobby using stairs. If you are at the auditorium tribune, you can go down the stairs at the right, and the left side of the tribune then exit through the main doors. Keep in mind, in an emergency, the elevator should not be used. For temporary countermeasures, inside the BMKG auditorium, there are 2 hydrant boxes located at the back end of the room. There is also a hydrant box located in the corner of the tribune. In an emergency, ladies and gentlemen can gather in the parking area of the auditorium building. Smoking indoors is not permitted, following appropriate government regulations. Thus, our safety instructions. If you need our assistance, please don't hesitate to contact our team at the number listed. Thank you and have a good day.
Okay, ladies and gentlemen, following the safety briefing, we move to our first agenda, the introduction of PlateauPlus. Please welcome Professor Mike Harrison, the co-chair of the International PlateauPlus Association, to deliver his address for the next 10 minutes. To Professor Mike Harrison, the time is yours.
Well, good morning. As you just heard, I'm Mark Harrison. As you've almost certainly heard, our official opening ceremony has been postponed until 11:30 due to, I understand, presidential decree. But we thought it'd be a good idea to start by, for those of you that are new to PlateauPlus, giving you a sense of what we want the initiative to be. refresher for those that participated last year. So let's get on with the first. Here we go. Great. Okay. The PlateauPlus Association first convened a meeting almost 2 years ago in Beijing under the aegis of these co-chairs. I don't know what ancient archive these photos were resurrected from, but I think in the future we could get something a little more contemporary. The meeting was a big success in my view. I learned a lot, particularly about the sort of anthropological aspects to plateau science. Before I tell you a little more detail about what PlateauPlus is, a couple of bits of news. Very exciting. As anticipated, the first PlateauPlus Young Scientist training session was held in southeastern Tibet a few months ago. Great international participation and diverse group of people studying complex Earth systems. Very proud to say that also this year, the UNESCO's International Decade of Science for Sustainable Development Program included PlateauPlus. You can find us on the web there. So, welcome to PlateauPlus 2025. Why do we study plateaus? They obviously, as you say, shape the Earth's surface. They influence climate, the hydrosphere, the biosphere. They're fabulous natural laboratories. We don't understand the interactions between deep Earth forces and the surface, but that's obviously a goal, a foundational goal of the PlateauPlus Association. Why do plateau research matter? Well, again, this is a wonderful manifestation of deep internal forces of the Earth pushing material to extraordinary heights, and then the forces of nature that are trying to, in fact, erode that material back to sea level. So the foundational science is fascinating. On short time scales, plateaus regulate regional climate, drive hydrological cycles, and on longer terms nurture biodiversity. Our species has long been attracted. I mean, we call Tibet the roof of the world. They're naturally attractive to our species, and we have in fact transformed not only the landscape, but in fact ourselves by adapting to these high altitudes. So what do we get out of PlateauPlus? In the same way that it would be, frankly, bankrupt to study any one planet by itself. Of course, it's comparative planetology that's allowed us this rich understanding we have of the solar system. So what we're proposing is comparative plateauology, okay? That any one plateau has got its own reasons for existing and the forces causing its deterioration. But are we missing something by not linking all these features? In the same way, we would miss fundamental information about solar system evolution without comparative planetology. It starts, of course, with foundational, basic geological science. What are the forces that are producing this and working on it to evolve these plateaus? But ultimately, as we mentioned, our species lives on them, and we're interacting with them in positive and potentially negative ways, and we want to understand both the history of our time up on these high stands, as well as ways to preserve, to create a resilient society. I would say if there's a vision of PlateauPlus, it's nicely summarized in this last bullet point here, which is the basic science, okay, to understand the origin, the geophysical roots of the creation of these things, but in fact, to use that information to inform a sustainable occupation of these high elevations. And also, we emphasize the importance of educating the next generation. Okay, so if that's the vision, how are we going to do this? Promote global comparative plateauology. Important, foster interdisciplinary collaboration and data sharing. Okay, agree on data standards, interoperability, and be sure that, and ensure open access. And lastly, empower early career researchers through training and exchanges. As I'd mentioned, the first of these young scientist workshops was held recently in Eastern Tibet. Okay, 6 grand challenges. Already pointed out the importance of understanding how these big plateaus reach their elevation, what are the forces that in fact are causing them to deteriorate. This bullet point, I think, I'm going to show you a nice example later this morning of how the lack of integration between geodynamical thinking and geochemical data, in fact, caused or set back our understanding of one aspect of plateau evolution by many decades. So focus on this integration, that the sum is greater than the individual parts. Morphology, once these things go up, what are the forces causing them to come down? How does this influence regional and global climate? What are the feedbacks between the formation and the atmosphere, hydrosphere, and biosphere? And again, as always, encourage cross-disciplinary, data-driven studies with a consistent policy of data standard. Okay, well, we get up there into these high plateaus. We, in fact, have adapted genetically. Take the EPAS1 gene, for example. We, in fact, have ourselves been modified by occupation. How can we use this basic information to create a more resilient and sustainable occupation? The anthropological, archaeological aspects are just intrinsically interesting, but they also inform how societies in the past have in fact maintained resilience against, say, for example, changing climate. Plateaus host critical water sources. This is an understatement, right? Okay, I mean, it's remarkable, but 1/4 of the global population is sustained by rivers coming off one single plateau. So, this is obviously key to understand the evolution and the sustainability of that resource. As I've already mentioned, data integration, standardization is an important aspect of the thinking in behind PlateauPlus. Not every plateau is an OECD country. They are going to have different opportunities for work. It'd be great to have a central clearinghouse like PlateauPlus to try and ensure uniform data quality across all plateau research. Establish open access repositories and data standards. Nice example, the Open Tibet Data Repository held at the Institute of Tibetan Plateau Research in Beijing is a good jumping off point. Now, more on the aspirational side, linking machine learning and responsible AI to plateau studies. That's something in its infancy. When I say responsible AI, I mean, not making pictures of giant moons hovering over Mount Kilimanjaro would be a start. But as I've also mentioned, the hope is, and funding contingent, that in fact the second summer school will focus on machine learning and plateau science next year. Okay, so we want a global network, a global community. Here's a nice representation. This was done largely for aesthetic purposes, but it's interesting that we've already met here and we are meeting here, and it would be lovely to think in 20 years that in fact the PlateauPlus itself has been sustained and is met in every one of the nexus in this global web. Okay, I'm repeating myself a lot here. I think we can speculate on our future health by having regular workshops like the student and the young researcher summer schools. The biennial conference, we're off to a good start. We're at conference number 2. Again, with this emphasis on educating the next generation. So if you're not already an active participant, please join us. We're looking into getting our own PlateauPlus.org. But in the meantime, and I'm going to return to this, here's some contact information for you from the Institute of Tibetan Plateau Research. So at this point, I'm going to say thank you. Terima kasih. Sheshe.
Thank you, Mr. Harrison. Ladies and gentlemen, our agenda continues with the keynote session 1, spanning in 125 minutes. This session will be expertly chaired by Professor Muhammad Kasimja.
It is our distinct honor to hand over the proceedings to our esteemed session chair, who will guide us through the presentation. Please welcome Professor Muhammad Kasimja.
You can come and sit on the high table. Professor Linding is already there. Maybe I can call other names also. You will that small screen over here. LinkedIn, and then we have Professor Andrea Mulch. We have Professor Sutu Professor James Mori, and Professor Mark Harrison already is there. So would you like to sit here on the high table? I make one little suggestion that if you could finish your talks in about 20 minutes, that would in the end give us time for discussions and questions. So that's a suggestion. We kindly be seated, and we would then call the first speaker. Thank you. Thank you. And I request now Professor Linden to make his presentation, please.
Good morning, distinguished guests. You're welcome here. My talk is about timing of initial collision and the search process in the new treatise. I'm Lin from Institute of Tibetan Plateau Research. Next, please. Okay, my talk including these 4 parts. First is collision in the new treatise. Here is new treatise domain. Our theme of this year. Here is the new treatise domain in the Cretaceous time. At least 4 plates have been collided with Eurasia during the Cenozoic time. So the timing and the process of collision onset is very important to understand the migration and the evolution of the faunas, or to test the potential linking between orogenic growth, global cooling, and the intensification of Asia monsoon. Lots of methods have been developed for constraining the collision process. At least tens of methods I mentioned here, like high pressure metamorphic, like the ophiolite abduction, mollusbation, structural faults, liquid granite, fauna migration, even numerical and physical simulation. Among these methods, the tectonic sedimentary response here is in the early foreland basin, which provides the most direct evidence, whereas the apparent polar wind path offer a quantitative constraint on the collision process. Okay, let's look at the collision between India and Eurasia first. Formerly, in the 1980s, most geologists believe that the initial collision between India and Eurasia continents occurred around about 55 to 50 million years at West Himalayan syntax. However, after 2000, more and more geologists support the initial collision might have taken place in the middle of Tibetan Plateau around 65 million years ago. But this new one model requires more continents to be consumed after collision, this part. In solution this issue, over the past decades, more hypotheses have been proposed based on different elements. Many can be classified into single-stage collision and multi-stage collision model. For the single-stage collision model, they include eastward diachronous collision. First begin in the West Himalaya, then diachronous to the west at about 40 million years ago. The central diachronous collision start at about 60 or 63 million years. Then diachronous to both to the west and the east Himalaya syntax. The third one is the synchronous collision. And the fourth one is presented by the large Great India collision. For the multi-stage collision model, they included intra-oceanic arc collision, the Great Indian Ocean Basin collision, the Shigas Bazark Ocean Basin collision model, and the triple stage North India Sea collision. For in solution, which the initial age of the collision, we first find it the Yellow Jambu Foreland Basin in the middle of the Tibetan Plateau. Here we show the same collision Jambu Foreland Basin, which was fragmented by Himalayan fold thrust system. Now it's composed of many small relic basins scattered in the Himalaya and the less Himalaya, like the Yellow Jambu Foreland Basin in the 30th Himalaya, the Shivalik Foreland Basin in the south of Himalaya. In the Yellow Jambu Foreland Basin, evidence for the initiation of collision of India and Asia was found in the Sandali section in the Saga area. It's in the west of Lhasa city. It's about 500 kilometers west of Lhasa. Here we find the former Yellow Jambu Foreland Basin related with the initial collision of the India and Eurasia. It is located just above the northmost 30th Himalaya. This stratigraphic section preserved the most complete record of the Paleocene strait in the entire Himalaya. Formerly, this area is occupied by the Jurassic Cretaceous stratigraphy. In this Jurassic Cretaceous stratigraphy, we find the Paleocene stratigraphy. Here's a typical outcrop of the Yellow Jumbo Fault Basin, the Sandaling section. Here we find the existence of the Paleocene deep water sequence and radiolarian faunas in this outcrop. We published the first paper in 2005 in Tectonics. We constrained the initial collision between India and Eurasia at about 65 to 63 million years ago. From now on, lots of papers have been published based on this outcrop. Now, tens of papers have been published about these sections all over the world journals. Here's a typical outcrop of the Fault Basin. The lower part we call Zhongzuo Formation is a pure sandstone. The material is sourced from the Indian continent. Above is continually covered by the Sandaling Formation and the Zhongzuo Formation. It's a deeper marine stuff. In the lower part, the Zhongzuo Formation, we find lots of foraminid fossils. It's confirmed age of this India affinity strata is 68 to 65 million years. However, the lower part, the upper part, which was well constrained by the well-preserved radiolarian fossils, the age was constrained between 65 to 55 million years ago. Look at that. The stratigraph is very colorful and strong deformed. So until now, 3 main relic fault basins have been found in the Himalayan in the Himalayan range. First is the Saga Jiangzi Fault Basin deposit, which is located at the northmost Indian margin, which formed immediately in response to the fluxial loading of the Euro-Asian lithosphere during the early stage of India-Euro-Asia collision at 65 to 63 million years. Then the fluxial wave migration southwards by 53 to 49 million years to the inner of 30th Himalayan, then to the late Himalayan by 48 to 38 million years ago, then to the sub-Himalayan in the Shivalik area by 21 to 16 million years ago. In summary, in combined with the detailed study for both West and East Himalayan syntax, we concluded that the India and Euro-Asia continent collided for the first time in the middle of Yellow Jumbo Suture Zone at about 65 million years, followed by diachronic close to the both East and West Himalayan syntax at around 50 million years ago. Yeah, we think the collision between India and Eurasia have strongly impacted the Tibetan and the surrounding region, which linking between the orogenic growth, global cooling, oceanic circulation, and intensification of the Asian monsoon. Here I cannot go in detail. Okay, now we look at the collision between Arabia and Eurasia. The proposal time of Arabia-Eurasia collision is also debated. Lots of age have been suggested from late Cretaceous to Miocene, from between 70 million years to 11 million years. It's a bigger range. There are different hypotheses for the Arabian-Eurasian collision have been suggested, including the abductional initial collision, which happened at about 40 million years ago. First, the abduction of the ophiolite, and the eastward diachronous collision, the synchronous collision, and the intra-oceanic collision. In order to better understand the configuration and the timing of the Arabian-Eurasia continent collision, we conducted detailed analysis of samples from Paleocene to Miocene porphyrial fault basin strait in the interior far South Iran many years ago. Based on the study from the Zagros fault basin, we concluded that the collision-related fault basin deposit started at about 34 million years ago. We think the Eurasia finished detritus into the Arabian plate at about 26 million years ago. We think the nearest ophiolite was abducted onto Arabian during late Cretaceous to early Paleocene time. And the Arabian-Eurasia intercontinental collision occurred before deposition of 26 to 21 million years ago in this region, in the Fars region. So we think, we suggest two stages of Zagros fault basin have been developed. First, the Paleocene fault basin, which records the ophiolite abduction in this region, while the Miocene fault basin developed, which marks the Arabian-Eurasia collision here. We think the collision-related fault basin, the last one, first developed in the interior Fars by 34 to 27 million years. Then in the middle part by 26 to 16 million years. In the coastal Fars during 15 to 5 million years. Then finally reach the modern coast of Persian Gulf in the southmost area. The collision between Arabia and Eurasia also strongly impacted the environment. We think the course of the Turkish Seaway at 6.4 profoundly affects the ocean circulation, which also strengthens the upwell of the cold seawater along the Arabian coast, which also profoundly affect the atmosphere circulation, which much enhance the South Asia summer monsoon. Finally, let's take a look at the Australia collision with Eurasia here. This figure shows the Sanda and the Sanhu plate collected in this region, which make a very complex figure between the Sanda and the Sanhu plates. Here's the suture zone. It was very covered like a 2U shape. Lots of important lines have occurred in this region, like Wallace line, the Weber line, the Linker line. This range is also linking the New Turkish Ocean and the Paleo-Pacific Ocean. In the east side is the Paleo-Pacific subduction zone in the early time. The southwest is the New Turkish suture zone, which happened in the early time from Jurassic to Cretaceous to now. You can see here the red dashed line is a Paleo-Pacific subduction suture in Borneo, in west of Sulawesi. We also found some Paleo-Turkish suture zone in Sumatra and Java in the southwestern side. From the study of how he suggested, at about 25 million years ago, the Australia collision, began when the solar spur collided with the North Solar Ridge volcanic arc here. At about 15 million years, the subduction quickly rolled back and caused the extension of the solar spur in the hang wall of the subduction. At about 4 to 3 million years, the Banda Arc and Australia collided again in this region and finally closed the seaway between India and the Pacific Ocean. The close of India Seaway also impacted the environment. People thinking with the Australia Plateau drift to the north, the Indonesia Seaway closed after 4 to 3 million years. With the reducing of warm water from Pacific Ocean flow into the Indian Ocean, the East African continent is dry and dry. People think with the dry of East Africa, the human went out from Africa. I cannot in detail this part. So why is the collision the India with the Eurasia make a huge plateau? Why is the collision of Australia with the Eurasia just formed arc basin sisters? We think the first reason may be the deep geodynamics. We think the deep geodynamic process and the driving force behind the ongoing plate convergence before and after collision are essential to understanding how the Earth system operates. Another reason is the convergence rate. The duration of the collision and the convergence rate determine the extent to which Arabia, India, and Australia have penetrated into the Eurasia. Further influence the deeper dynamic, plateau growth, deformation kinematics, and global climate modulations. So the collision, the India-Eurasia initial collision began in the central Himalaya at about 65 to 50 million years. The Arabia-Eurasia collision most probably initial at 34 million years. And the Australia-Banda Arc, the first collision may be happening at about 25 million years, then quickly extension. The final collision may be at about 4 million years. We think the Indonesia mountain range and the India plateau preserved as subduction domain structures, whereas the Tibetan plateau evolution still complex, deeper process. That's all. Thank you for your attention.
Thank you, Professor Linding. I think that we might have some questions, but you may take your seat for the moment. And we leave the question and answer to later on, to the end. Thank you. I now request Professor Andreas Mulch to make his presentation regarding decoding past climate and geodynamic processes. Professor Mulch.
Well, good morning, everyone, and first and foremost, thanks for the organizers, the local organizers, and the PlateauPlus Association for having me here today. It's a great honor and pleasure to be here. I took the liberty to take PlateauPlus seriously and will jump through a few observations from different regions of the world. I always would like to thank my collaborators who contributed to this, and as Professor Mark Harrison has already outlined early on, we look at very different compartments of the Earth system that are intertwined when we study plateaus. And we all know about the different material fluxes from the rock cycle all the way to the carbon cycle. Geobiosphere interactions are key when we would like to understand how the different parts of the Earth system are affected by the rise and maybe the demise of plateaus. And a third element that probably falls into the range of sustainability that I feel really important for the future and also for the entanglement between society and nature is that mountains have an enormous emotional value and inspirational value for many of us, no matter where you go on this planet, and I think we need to capitalize on this. If you think about the elements of these three different large topics, the mountain building processes and the underlying geodynamics, they directly influence the rock cycle. I will not be able to talk about the other elements like the water regions and the carbon cycle today, but what matters in the end when you try to combine all this is that we're looking at regions with enormously large gradients, and these are the ones that allow us to study a variety of first order elements in the Earth system. The three examples I chose to look at this is one, how does actually warming take place in high elevation regions? We all know that glaciers nowadays are strongly affected by climate change, but we don't really know how much amplified warming or how different warming we may actually experience in high elevation regions. I will briefly touch upon some twisted things about ancient monsoons and how we can recover them from the geologic record. And if time permits, I will also look into the Central Anatolian Plateau, which I frequently call the little sister of the Tibetan Plateau, because it shares quite a few similarities, others it doesn't, and its role in shaping Central and Eastern European vegetation composition over time. I think it's no surprise to us if we look into the current debate, and we just had thousands of people meeting in Brazil to talk about this, that the plateau regions are prime examples to understand where we cut thresholds and where all of a sudden the system, no matter how big or how small we define it, will actually go to a state where it completely changes its behavior. And we know how these systems work. They have cascading effects. They will result in a systemic change where at one point you will change the entire relationship of the individual elements of the system, and frequently it's hard to predict what happens once you've gone through such a system change. Today we question things like, water resources. What are the future of water resources for the Tibetan Plateau? What do we know about stability of the permafrost regions, the integrity of the ecosystems? How will topography, climate interactions lead to biodiversity change and maybe even the loss of diversity or genomic diversity? All of these questions are open questions, and we don't know whether these are elements that may get to a tipping stage or not. Earth's past may allow us to look into this. We study the long-term hydroclimate, we can understand how warming happened at high elevations, and we can go through all of these elements. What I wanted to highlight here is that our systemic knowledge, past and present, is still from quite a bit away from being satisfactory. As one example, maybe 20 years ago we had one point on this diagram on the left. How did the elevation history of large mountain ranges evolve over time? Now we have a very good understanding of how these things actually work. And if we want to combine this, for example, with our knowledge about mountain biodiversity, and this is a complex diagram, but I want you to focus on the colored bars at the bottom, which show different parameters for different mountain ranges. The one thing you should take away is they don't look alike. They look very different, and different drivers may exist for diversity in different mountain ranges. So in order to combine these different fields, we still have quite a bit of work ahead of us. The modeling community and the integration between proxies and models has helped us enormously to get forward. I will only very briefly touch upon this because we will hear much more about this tomorrow, but we are now able to actually use combined and coupled ocean atmosphere models, integrate the required paleogeographies, and understand how, for example, the distribution of isotopes and precipitation allow us to look into these past climate features of high elevation regions. Since I already touched upon isotopes and precipitation, these are For those of you who don't think about this every day, relatively simple diagrams, you see how, for example, the oxygen isotopic composition of precipitation changes with elevation. That is one element that we're commonly using to understand how high elevation regions have developed in the past. And you can see on the top left diagram a very strong decrease in those blue colored dots once precipitation has to cross the high elevation regions of the Himalayas. And on the lower right, you see the same element on the left for the much, much smaller Tauride mountains in Turkey and the Turkish Central Anatolian Plateau, but again, a very strong decrease in this isotopic composition that then gets modified within the plateau interior. And we will use this throughout the talk at one or the other location. This is not a feature that one cannot trace back in time. This is one example where a lot of my colleagues have worked on in the Sierra Nevada of California. Today you see the same feature, isotopic composition of precipitation changes with increasing elevation in the blue dots at the bottom. And you can trace this back through time with different isotopic systems, either hydrogen or oxygen, different materials, clay minerals that actually form from rainfall, biomarkers that form from plants that actually recycle the water, or you have hydration of material that was deposited at the Earth's surface like volcanic glass. So all of these lines to the right show you that this gradient that we observe today has actually been around for quite some time and can be recovered from a variety of different materials. So this is actually a rather robust way of looking at first-order changes in the Earth's surface. I wanted to highlight this one example here, which tries to trace this back into the past. We're looking at the Andean Plateau here in the central part. And what you can see on the right diagram is three colored regions: the high elevation region in red, the Puna, the Cordillera in gray, which delimits the foreland from the high elevation region, and in green you see the foreland region. And if you look to the diagram on the left, you see the same colors, and you see that these regions are characterized by different isotopic composition of the glass, the hydrated volcanic glass that we measured there, which is a direct representation of the hydrogen isotopic composition of the rainfall. No matter what the underlying principles are, you can see that the foreland sits on the right, the intermediate mountain range sits in the center, and together it produces a large depletion in the heavy isotopes, so you get those low numbers for the high elevation region in red. This is what you observe today, and you can trace this back in time for a few million years here, and it seems to be a stable configuration. If you go back in time, and we extend this diagram to deeper time intervals, all the way into the middle Miocene, you can see that some of these relationships have changed. So if you start this diagram from the bottom, you see that the red and the green are actually relatively close to each other. So about 18 to 15 million years ago, the plateau itself wasn't as high as it is today, as the difference between the green and the red are relatively small. You see how the red moves away from the foreland basin at around 12 million years, and this difference becomes larger, and it becomes the same as today at around 10 million years. So the plateau increase can actually be tracked by this information, and you can also see that the Eastern Cordillera, the mountain range, changed at around 8 million years to its intermediate position. Going back to the western US, we know that the high elevation regions occur where the high mountains have been, and we have features there like core complexes that are able to store fluids that make it deep into the crust. Many of them have been shown to contain waters that have originated at the Earth's surface, and they delineate this core of high elevation regions and zoom into one, which is Montana. And wanted to look into one feature that we recently discovered. This is a beautiful terrestrial section in the high elevation region. You see on the right that these records date around the Eocene-Oligocene transition. And if we look at their paleoenvironmental information, you see that the red dots, which is the section that you've just seen in Montana, has lower values in terms of their oxygen isotopic composition than compared to the Great Plains, the lower elevation regions in green. And you see that they don't really mimic what we see in the oceans. That's one of the things that is important. And we've then used a way of recovering temperatures from those soil carbonates. And what you can see here is that these soil carbonates do actually show a long-term cooling in red in the Oligocene. And if you see the middle Eocene dot on the far left, it doesn't really show a strong decrease across the Eocene-Oligocene transition. And this increase in oxygen isotopes at the top basically is just a reflection of that long-term cooling that we observe in those soils. We have I'll skip the technical details. We have basically concluded that, in this high elevation continental region, we see a long-term cooling that postdates the EOT and actually does not really mimic what we observe in the ocean. So the warming response in those continental interiors may actually be very different than what we deduce from the oceanic records. If we jump back to the interaction of Earth surface processes and the interaction with the hydrological cycle, which would be the second example I would like to show, we have an understanding of where the big orographic barriers develop. I refer again to the work that we've seen before here, where somewhere in the middle Miocene, we have this transition from one major mountain barrier, the Gangdesi Mountains, to the Himalayas that actually become important in basically controlling the distribution of moisture across the Himalayan Tibetan system. And once you go away from those, the beautiful records that we have there, and you go to the Central Asian records, we may see responses of such far field effects. And here what I'd like to highlight is a study by postdoc Niels Meyer. We see a stratigraphic record from Central Asia, from the Xining Basin. And here we're covering the carbon isotope record that shows in the brown bar a very strong negative excursion in its carbon isotope values. That's very common for this time. This is at the Paleocene-Eocene thermal maximum. It goes along with a change in vegetation composition. And it seems very plausible that he was actually discovering the PETM in this part of the section. So a warming event should actually result in warming if we use our tools to look at temperature. And once he did this, he actually realized that the temperatures at the top that you see in the brown bar aren't actually that warm. In fact, they're actually very cold. They're much colder than you would expect them to be. And if you look at the climate model output, they actually look like winter temperatures, the 20 degrees that you see here, which are at the tail end of this temperature distribution. So what does that actually mean? This is something that we have to understand in the record. We look at minerals and materials, in this case pedogenic carbonates that form in soils, that form when the soils get dry. And what we propose to see here is actually that the soil drying went from the summer season to the winter season, and basically we see the cooler temperatures during the winter time when the soils dried and these materials formed. And that makes sense if you think about a monsoonal system, because in the monsoonal case, the winters are the dry and the summers are the wet season. So during this time, the monsoons may have penetrated all the way to this location, as they only very, very rarely do later on in Earth history. Last but not least, I said we can very briefly touch upon the Central Anatolian Plateau. What fascinated me when we started to work there some 15 years ago was that a lot of the elements that we see in larger plateau regions actually do work in this relatively small plateau, and it's still fascinating to this day because you see the complex interaction of meteorological systems that occur, and how can we benefit from this. What I would quickly like to touch upon, and this is a paper that we studied, that we just published earlier this year with former postdoc Maud Myers. You see the orange dots on this diagram are plateau interior records of isotopes and precipitation, and the more bluish and violet colors are the foreland regions and the Aegean. And as I highlighted before, I'll just go back. This difference on the left-hand side of your diagram between the low elevation high delta O18 values and the high elevation low delta O18 values can be traced back in time, and this difference between the foreland and the high elevation was existing already 10 million years ago. So at this time the plateau was already distinct from the Mediterranean region in terms of elevation. If you try to plot this as an elevation diagram, you see that the 8 to 6 million year rocks, they almost attained present day crest elevations, and the 10 million year rocks were on its way to get there. So we can actually track the elevation history of the plateau interior. This doesn't really match, and I cannot go into all of the details, what we know from the plateau margin, but the plateau margin has another interesting element. And here we're looking at the carbon isotopic record in the same soils. And for those of you who are familiar with this, there's a very strong global signal of increasing carbon isotope values at around 10 to 6 million years, depending on where you go on this planet. And you see all those red dots moving to the right in the center of the diagram, which is what you would expect when you compare this to India, or when you compare this to North America. The weird thing here is that all the red dots move back to the left sometime around 6 to 4 million years, and it seems like we have this increase in what is driving this C4 vegetation, the expansion of grasslands at the expanse of forest biomes, and this increase basically returns back to what we observe today with a very strong C3 vegetation. So this interaction of surface uplift, interaction with the rainfall patterns and temperature, which are all affecting the photosynthetic pathways of those biomes, is in the end a key element to be studied here. So to summarize this, what we observe in this region of the world is a plateau region that starts to grow at around 10 to 11 million years, develops a plateau structure around 8 to 6 with subsequent uplift of the margin, post-dating this 8 to 6 million year period to form the gray topography as you see it today. And this directly influences the vegetation composition within, across, and all along the plateau. So to sum up, I hope I could convince you that depending on where you go on this planet, we have very different climate conditions, and it's really worthwhile to study these plateau regions depending on their larger geodynamic context. I was pinpointing the change in warming at high elevations compared to the ocean records from this EOT example, the Eocene and Oligocene cooling in North America. We used sophisticated thermometry advances at this point in time to look at the seasonality of rainfall, for example, during the PETM in Central Asia, and we're currently exploring how surface uplift and the evolution of large biomes in the Eastern Mediterranean, in the Central Anatolian Plateau region actually conspired to shape the modern day ecosystem. And with that, I really thank you for your attention, and again, a pleasure to be here. Thank you very much.
Thank you, Dr. Punch, for a very nice presentation. I now request Dr. Suku Adi to talk on South Central Java earthquake system and the background of our system.
Ini untuk next sama previous. Next-nya mana? Next ini next one. Yang misalnya untuk next ini previous. Ini untuk laser. Oke. Saya ganti dulu. Oke, makasih. Thank you very much. Good morning, everyone. Yeah, today I present the different folding of the 2023 magnitude W 5.7 and 5.9 South Central Java earthquake and backstress fault system. Next slide. This South Asia region with the highest natural disaster. Next. Okay, sorry. Yeah. This we can see Indonesia is very rigorous hazard, ground shaking, and with
460 years return period. Okay. Yeah. Yeah. Next slide. Help me, please. Yeah, okay, sorry. Yeah. Okay, thank you. We can see Indonesia is very active earthquake because Indonesia is, look at the subduction from Indonesia Australia plate moved to North Eurasia plate and from East Pacific plate and from East Philippine plate. So impact Indonesia is active and earthquake. Okay, this systemicity in Java. We can see megathrust on Sunda Strait and new big thrust system in south. This right there with the sponsor it's 20 and 21. Next slide. Yeah. Introduction. There are three main tectonic systems in Java subduction: interface, intraslab, defocus. In my study, we successfully found another system called the back thrust. Next slide. The two moderate earthquakes occurred in South Central Java in June 6, 2023, magnitude W6.5.7 and 5.9, followed by 120 aftershock respectively. The magnitude W5.9 earthquake occurred in deep of 50 km with west east thrust mechanism, while the magnitude W5.7 earthquake was shallower 15 km with southerly back thrust mechanism. Next slide. The data used in this study, the temporal graph of the seismicity from data compilation in South Java along June 2023 with the two large earthquake magnitude W5.9 and 5.7. The volatility diagram shows the ratio of VP/VS 1.76 from arrival time data and recorded by BMKG seismic station, Green Triangle in Java Island. The red start are the epicenter location, magnitude W5.9 and 5.7. The earthquake frequency and magnitude distribution show relation with the parameter of magnitude 2.7, E value 4.93 and P value 0.77. Next slide. Result my research, the optimum 1D velocity model of South Java earthquake show the VP and model in deep between 0-100 km. The red line is the base model with the from 100 initial green line model with the low residual. The graph or root mean square significant change after 50 iteration with the low value 0.535. The seismicity map show the distribution of relative play location result with final hypercenter location quality with the uncertainty plus minus 5 kilometer and error then less 2 kilometer. Next slide. We can see the focal mechanism from variation inversion for magnitude W 5.9 with the probability density function show coverage solution and the central tip 55.7 plus minus 1 kilometer with 8% confidence level. The displacement waveform fitting show the comparison between observation, black line, and synthetic real-time red line with correlation between 70% and 90%. To show the central parameter sucks the central time with division plus minus 2 seconds and location with nothing shift B division plus minus 5 kilometer. While eastern shift with division plus minus 5 kilometer, all sig tensor component M in and MDT, MEE, MNT, figure coverage solution with the division plus minus 0.1 and convergent solution for magnitude 5.9 plus minus 0.02. Next slide. This table is comparison of the magnitude W 5.7 and 5.9 earthquake June 2023, South Central Java. Time and location and 6 June 2023, deep 20 kilometer. But and 30 June 2023, deep 60 kilometer. Magnitude W for 5.7 plus minus 0.03 and magnitude 5.9 plus minus 0.02. Focal mechanism oblique thrust strict north-northwest, south-southeast, and deep 27 degree, rigs 33 degree. Thrust strict for earthquake 20 June 197 degree, dipole 26 degree, and rig 102 degree. Tectonic system, Pectra system, and magnitude for 5.9 Pectop system. This is different. Aftershock, plus minus 80 aftershock, vertical shallow cluster, and plus minus 70 aftershock, deeper cluster. MT component, double couple, 95%, CLVD 5%. Double couple for magnitude 5.9, 91%, and CLVD 9%. Impact, moderate emergency, sig intensity like moderate damage, and this similar with magnitude 5.9 and moderately sig intensity but like moderate damage. Interpretation, evidence impact thrust and accretion width, and evidence of existence of the international backstate similar to Tasik Malaya 29. Next. Seismotectonic map show the hypercenter location and focal mechanism into two specific clusters. Slash A absent show vertical profile, the relocation result magnitude W 5.9. The slide P and P absent show the vertical profile of the hypocenter cluster of magnitude W 5.7 with two focal mechanism. The hypocenter distribution show possible of the backstress system. The vertical profile of CC absent was set parallel with the trend line and showed two different hypocenter distribution for magnitude 5.9 and 5.7. Next slide. You can see this map show focal mechanism for magnitude W 5.9 with the 5 accelerogram location and peak ground addition bigger 100 cal and the distance range 75 and 125 kilometer. The 5 accelerogram are suitable for the building damage distribution and intensity field with the moderate Mercalli 5 and 6. Next slide. Next slide. This is recent studies show update system possible, backstress and less Java with similar mechanism with our study. Next slide. This is, we can see offshore backstress system in Sumatra, for example, and subduction zone. Next slide. This is the Mentawai backstress, another possible source for very large, destructive earthquake and tsunami along a coast of Sumatra. Fisherman et al. 2011. Next slide. Yeah, my conclusion. We successfully analyzed the activities for moderate earthquake that provide a new insight about the geometry of subduction zone in South Java. The relocation results show different deep distribution for magnitude W 5.9 and 5.7 that confirm the evidence of backstress. The peak ground addition value produced with bigger 100 cal with intensity 6 moderate Mercalli confirm the possible limit where it has been found from previous large international event in 1867. Important result, the seismicity in South Java can provide the new understanding different folding along slab subduction and impact the seismic hazard. The next tectonic literature must indicate not only megatrust zone but also the backstress zone along the Sunda Arc, Sumatra, Java and subsystem. Next slide. This is my team. Dr. Ibu Dokirita is my boss last year, and Dr. Daryono is now need the best man, Director Earthquake and Tsunami PMKG, and my friend Sengji from Singapore, from Nanyang University, and Professor Moksin from Sahkuala Banda Aceh, and Pepen, my junior, the best man from PMKG, and Andris Panjuta is the best too, and Marchuki and Bagus is my son. Thank you very much. Next slide. Thank you for your attention. Greeting of health and success to all and us. Thank you very much.
Thank you, Professor Adi. I now request Professor James Mori, to talk on models to the region of the 215 Gorkha, Nepal earthquake.
Okay. Well, thank you for this invitation. It's nice to be back in Indonesia after such a long time. And let's see. So I'm going to talk about the Gorkha earthquake in 2015, and anyone that's been working in the Tibetan Himalaya area probably remembers this. Very important event. It was the largest event that's happened in the last 80 years in the Himalayas. It really emphasized the importance of seismic safety, earthquake hazards. You know, you really need to build your buildings to be safe during these kind of events. And it's probably representative of future earthquakes that are going to happen in the Himalayas in the next decades. Okay, so there's severe damage over much of Nepal. Probably you know that. This is a slide in Chotara region in the northern part, north of Kathmandu, which we visited a few months after the earthquake. Here's a good slide that shows an old masonry building on the right and a new modern building on the left. And the old building obviously has lots of cracks, very dangerous, and they have to put these wood stabilizers to keep the building up, while the new building did very well. So this is the kind of comparison that we really want to emphasize and to improve the building stock of Nepal, China, Bangladesh, not Bangladesh, I can't even think of names. But anyways, of the whole area in order to improve the standards of the seismicity. Well, the earthquake was big, and so there are lots of aftershocks, thousands, tens of thousands, and we can use these small events that happen after the earthquake to really study the area. And that's the main purpose of this work, is to look at the velocity and attenuation models for the area of the earthquake. So we use what's called tomography, and this is exactly the same thing that are used in hospitals, where CT scans, computed tomography, is used to look at the internal structure of the body. We use the same thing to look at the internal structure of the Earth. And seismologists all know about tomography, but I think there are a lot fewer seismologists here, so let me just take a few minutes to explain what tomography is. In this simple example, we have 3 stations, those triangles on top, and 2 stars, which are the earthquakes. And from each earthquake to each station, there's a seismic wave, a seismic ray path that travels. So in this particular case, there's 6. So 3 stations and 2 earthquakes. And from this kind of data, we can easily calculate the velocity in each of those 6 blocks by just looking at the travel time from each station to each earthquake. And this is kind of complicated, but just look at the vertical line on the left, which is the path from earthquake A to station, or earthquake big A to station little a, and you can see easily that the travel time is simply the distance it travels in that block divided by the velocity plus the distance it travels in the block above divided by the velocity in that block, which is that first equation on the right. So anyways, you can do this for each ray and sum them all up, and you can calculate the velocity in each of those blocks. And it's a linear problem, so it's quite easy to do the inversion in this particular case. You cannot determine the velocity in those bottom 3 blocks because there's no ray that passes through them. So this is just a simple example of how we can calculate the velocity in the blocks of the earthquake just by looking at the travel times from lots of earthquakes to lots of stations. And this is commonly done, and there's actually been at least 3, probably more, tomographic studies of the Nepal earthquake by those 3 authors on the top. So why are we doing it again? Well, we're doing it again because in the 10 years, the aftershock catalog has been much improved. There's many more earthquakes, many more events, much better located. And also, so we have much more data. And the second is that we use not only the travel times, but we use the amplitudes to also do the same thing to look at what we call the attenuation structure of the Earth. This is just an example of one of the studies that was done before by Bai et al. And these colors show the velocities. And one of the main conclusions of this particular tomographic study was that there are velocity changes at the edges of the Gorka earthquake. And those velocity changes may represent the physical boundaries that limited the rupture for the 2015 earthquake. And then there was another earthquake, the 1833 off to the northwest, and the 1934 off to the east. So anyways, these velocity structures might be representing some real physical changes of the rock structure that can help you understand the ruptures of these large earthquakes. Okay, so this is our data. It's the same kind of picture, but now we have 42 stations, 2,100 events, so that's over 42,000 P wave paths and 29,000 S wave paths. And as I said, so the data has improved. And one other good thing is that most of these ray paths were not done automatically, but actually checked by eye, the arrivals. So we consider this to be a very good data set for doing or redoing this kind of problem. One thing I didn't mention at the beginning is most of this work was done by my student, Chingtan Tamisa, and so I'd like to credit him for doing all of this work of looking at all this data. How come it doesn't go forward anymore? Okay. So just a couple details about what's happening. We do a progressive inversion from 1D to 2D to 3D. That's because these big inversions are often very unstable. And so you don't want to just go immediately to the 3D, but sort of work sequentially and make your models more and more complex, and that keeps the robustness of it better. We use station corrections, which means each station has our own sort of factor, amplitude, or not amplitude, travel time factor underneath it because the local structure can be very important. We also relocate the earthquake simultaneously as when we do the velocity structure. So that actually makes the process nonlinear, so it makes it a little bit harder than the simple linear problem that I gave before. And the other thing was we use the amplitude data to do the simultaneous attenuation. This is not working? Okay. Okay, so here's the results. So what are these? These are depth slices of the velocity model. And so on the left are the P velocity models. On the right are the VP, VS velocity models for depth slices at 5 kilometers, 10 kilometers, and 15 kilometers. These are horizontal slices. We usually use the ratio between VP and VS instead of just VS because VP is higher than VS, is always higher than VS, but we really want to look at sort of the ratio. How much higher is it than VS? And one of the basic results, this is actually not really new, but the bottom parts are red, the bottom lower figures, and that means slower velocity, so around 5.0 to 5.5. And so that just reflects the slower sediments that we see on the southern part of the earthquake, where the thrust fault is coming up. In the middle to upper part, you're seeing more of the rocks of the lesser Himalayas and the higher Himalayas, and so the velocities are faster, and it's reflecting the more of the crystalline rock material of that area. And this is true for both the VP and the VP-VS. Next slide. This is a station correction, and this is what I was saying before. The red colors are larger positive station corrections, which means the velocities are slower. The blue is faster areas. And station corrections are very important because they reflect the local geology right underneath your instrument. And the local site response could actually change the shaking by a factor of 3, 5, sometimes even 10 times. So very strong site amplification factors can really change the damage distribution and how we feel the earthquake at a particular place. Again, it's sort of red on the bottom, and that reflects the more sedimentary layers that you see of that area compared to the higher, harder rocks that you see up in the mountain areas. Next slide. Let's skip this one. Next slide. Okay, another thing I mentioned was that we do relocations of all the earthquakes with our new 3D velocity model. We do them simultaneously with the 3D velocity model. And I think everyone thought at the time of the earthquake, before the earthquake should happen on the main Himalayan thrust, on the MHT. And so you would expect most of the aftershocks to group along the MHT. But you look at all these earlier studies that were done, and they sort of do. I mean, like B and C are basically, by the way, these are cross sections, north-south cross sections. You're looking down along the thrust fault. And generally, the black lines show the MHT, or maybe you look at the E, and that shows the fault structure the best. But it's actually not very clear. And we all know there's many more faults, there's many more structures, and so when these earlier studies were done, it's not really clear that the MHT was the primary seismogenic fault during that earthquake. B, they're sort of grouped around the fault. C, if anything, it looks like most of the earthquakes are located above the fault in the hanging wall, the shallow region. You look at E, and it looks like most of the earthquakes are actually below the MHT at depths greater than that fault. So it's really not, everyone thinks it should be on the HT, but the evidence wasn't really there. There's really not a good aftershock distribution from all of these thousands of events that happened. Next slide. Okay, so these are our results. And so we think we have good locations because we use the 3D velocity model. We actually split it into 3 sections because if you look at all the earthquakes together, it gets more messy because there's lateral variations. So the top one is across the western section, the middle one is across the middle section, and the bottom one is across the eastern section. And I think from this you can say that, yes, the aftershocks are grouping pretty consistently close to the MHT. By the way, what is the MHT? It depends on the model and the geologists you talk to. So we put actually 2 different models by Elliott and Hubbard on with the 2 different lines. But in general, our results show that basically most of the aftershocks, probably 70–80%, happen within about 5 kilometers of the MHT. So I think that's a good result. It's what everyone expected. I think it's what everyone wanted to hear. And so the aftershocks do reflect where there are. I mean, of course, not all of the aftershocks. There's lots of aftershocks, particularly in the hanging wall, and there's presumably imbricate faults and lots of other complicated structures. But the main faulting does seem to have occurred on the MHT. Okay. Next slide. Okay, so the results of this travel time tomography, slower velocities in the southern region reflect the shallow sedimentary layers. And I said before, this is important because shallow velocity layers can really amplify the seismic shaking. So before an earthquake, you really want to know what your velocity structure is, and you can begin to predict where the shaking will be stronger or not so strong. Higher velocities in the northern and central section probably reflect the crystalline rocks of the higher and lesser Himalayas. Actually, I'm missing a slide. Can you go back one slide? Go back another slide. One more. One more. Oh, okay, I'm missing a slide, I'm sorry. But I had a slide that showed the results of the velocity with the slip of the main Gorka earthquake. And there seemed to be a correlation between some higher velocities and areas of higher slip. And this is also important. This is something that seismologists don't really understand, but would like to be able to say what areas of the fault will produce the bigger amounts of slip, thus producing much higher ground motion, where the shaking is really going to be hard. But it's not something at this point that we can really say much about before an earthquake. Earthquake ruptures tend to be very complicated, areas of large slip and small slip, strong shaking and not so strong shaking. And so that's an important current problem, is try to anticipate ahead of time where there may be large slip on a fault where the shaking is going to be hard. And the last point is the aftershocks really do seem to be located close to the MHT, which we take that as indicating that was the main seismogenic fault in the earthquake. Okay, next slide. So attenuation tomography, this is looking at amplitudes instead of travel times, and it just gives you another characterization of the physical properties of the rock structure. Sediments tend to have higher attenuation than crystalline rocks. Attenuation also seems to show the fluid properties better than just travel time attenuation. Next slide. Next slide, please. So we measure the amplitude, but we actually don't just measure the amplitude, we measure what's called the spectral amplitude, which means we take a FFT of the time series and look at the amplitude as a function of frequency from about, a few hertz to maybe 20 hertz. And then what we measure is what this parameter T star. And T star is the travel time divided by the quality factor of Q. And so what we're actually, the parameter that we measure is that fall off with frequency, sort of at the right end of both those plots of the blue line. How fast do the amplitudes decay with frequency? And that's sort of the basic parameter, the basic thing that we use to try to characterize the amplitudes. This is done not as commonly as travel time tomography, just because it's harder to do this. It takes a lot more time to take a spectra of the waveform and fit it with a line and actually try to characterize the amplitude decay as a function of frequency for each of those paths from each earthquake to each station. But anyways, we did this, or my student did this, for a lot of data. And the next slide. And so this T star accumulates linearly along the path, exactly as travel time does. So you can use exactly the same kind of inversion techniques for calculating what is the quality factor for each of those blocks that the travel time, that the ray travels through. And so we use 39,000 P wave values of T star and 27,000 values of S wave. Okay, next slide. And here are the attenuation models. So they're expressed in QP and QS, the quality factors. Again, these are vertical slices at, I'm sorry, I keep saying vertical. These are horizontal slices at depths of 5 kilometers, 10 kilometers, and 15 kilometers for QP on the left and QS on the right. Basically, this is showing us similar information to the P wave. That is higher attenuation, red colors in the southern section, and lower attenuation, higher Q values in the mid to northern sections, which again are just the difference between the shallow sedimentary rocks and the shallow crystalline rocks in the north. Next slide. Okay. But one very interesting thing, and this is a plot of the contours of the slip of the main shock. So you see the outside contour slip of 2 meters on the fault, and then inside that is 4 meters, and the highest values are 6 meters. So this tells you how much the fault slipped across the whole area. And I think there's a very good correlation with the QP, with this attenuation model, and the contours. The colors are independent of the contours. The contours are from totally different seismological studies, but you see that the blue color of the high QP matches very well with the 6 meter contour, which means this is a very good indication that the QP is telling us something about the high areas of slip. Next slide. Okay, that's the same slide on top. On the bottom is the slide that I was missing, which showed the correlation with the velocity. And you can see that basically there's a similar correlation with the velocity, but the attenuation is much better. I think anyone with their eyes would say there's a pretty good fit between the QP and the velocity, the slip contours on the top one. On the bottom one, well, maybe there's generally a but it's much less. And the next slide, please. So the attenuation tomography represents some kind of different parameter, probably due to fluids. So maybe there are more fluids on the fault in that particular area. That area is known to have hot springs, and there are geological reasons for confirming that. And maybe that's one good reason, or one possible reason for saying why the large amount of slip happened on that particular area of the earthquake. So, thank you.
Thank you, Professor Mori. I now request Professor Mark Harrison to talk about channel flow models for Himalaya Tibet.
For over 150 years, geologists have been speculating as to how the crystalline core of the Himalaya came to be emplaced. The past 30 years, really there's been only two models that have been vigorously debated. The traditional critical taper model, in which internal deformation is essentially by frictional sliding on thrust faults, and the channel flow model, which posits that the mid-Tibetan crust was molten 25 million years ago and has remained continuously molten since, and has been extruded through the arc, through the Himalaya. Now, interestingly, importantly, the models make very different interpretations of the role of partial melts, of the so-called Himalayan leucogranites. In one case, it's the cause, in the other, it's the effect. And this was driven home to me forcefully when the recent publication of this special issue of Elements, focusing exactly specifically on Himalayan leucogranites, and back-to-back papers, one by Matt Cohn, Sean Long, and myself. Actually, it's in the title. Himalayan leucogranites, essentially no role for the leucogranites in deformation. Another one by Mike Searle and John Cottle, in which the melts, in fact, are the active lubricant that makes that extrusion possible. So what's going on here? Let's begin by reviewing the main characters in the geology here. We seem to have lost our laser pointer. If we could recover that, might help. The Greater Himalayan sequence is shown in these kind of orange color you see here. The overlying Tethyan Himalayan sequence, generally low-grade metamorphic rocks in shades of blue, and the Lesser Himalayan sequence underneath the main central thrust in pink colors. The blue boxes are the transects for thermobrometry. I'm going to focus on a little later. And that red line is the in-depth profile. This was a seismic magnetotelluric profile that basically started this line of thinking of channel flow 30 years ago. Now, if we take a north-south section, come on, somebody's got to have that laser pointer. Check your pockets. A north-south section looks like this, and this is not controversial. Okay, you see again in orange the higher Himalayan, Greater Himalayan sequence, the blue Tethys, and the pink Lesser Himalaya beneath that. Now notice that adjacent the so-called STD, the South Tibetan Detachment, this normal fault that separates the Tethys sediments from the Greater Himalayan sequence, there's a series of granites called the higher Himalayan leucogranites. Now, about 150, 200 kilometers north, there's another sequence called the North Himalayan granites. And then even further north in that stapled red color, that's the continental arc. That's the Gangdesi batholith you've heard about a couple of times this morning. And there's the MHT. There's the main Himalayan thrust that Jim has nicely introduced for me. Okay, now that profile I mentioned, the in-depth profile ran from essentially the South Tibetan detachment north, well to the right of this diagram. The leucogranites, those two belts, they're not only physically separated, but they're temporally separated as well. The big high Himalayan leucogranites, 24 to 19 million years. The major North Himalayan domes, 17 to 10 million years. But as you'll see, there's a real range of ages. What's going on? Okay, this was a publication that was a landmark. Nelson et al., 1996. You can see in the top slide, this is the reflection profile, those horizontal lines. You see the YDR is pointing. These are these mid-crustal, sort of 15, 20 kilometer deep seismic anomalies, bright spots they're called, and certainly suggest the presence of fluid. What kind of fluid? Well, the Nelson et al. Hypothesis is that the Greater Himalayan sequence is the extruded Tibetan middle crust, and you can see in the lower diagram representing the Himalaya, the HHL, that's the high Himalayan leucogranite, the North Himalayan granite, NHG. It effectively, in fact, here's the quote, the high Himalayan leucogranites and North Himalayan granites are progressively younger frozen snapshots of the partially molten mid-crust layer. So Tibet has been molten for 25 million years, essentially continuously in this model, and is being squirted southward, lubricated by these melts. Now, this model proved remarkably attractive to a number of leading groups. Oh, sorry, I should show you here. Here's, it would really help having that laser pointer. The magnetotelluric data also showed highly conductive regions that seemed to correspond to these seismic bright spots and leading them to believe that this was, in fact, a conductive, highly conductive fluid present. Okay, so let's say several groups, look at this. Lower crustal material, partially molten from the central Tibetan plateau, extruding through the Himalaya. 200 kilometers extruded to the lower crust, of the Tibetan plateau, beneath the Tibetan plateau. So you get the idea. You can see it in this cartoon that this is the basically middle crust of the Lhasa block, southern Tibet, being extruded through the Himalaya. Now, this model, Chris Beaumont and his group published a thermomechanical model in which you can see in blue there the erosion front. We'll watch this through a couple of cycles here. So here comes India, smacks into southern Asia. You can see the tracing PT paths. Okay, there's very focused erosion, a narrow aperture in the high Himalaya. And the assumption was, look, you get this high topography in the Himalaya, that's in fact going to catch the precipitation is going to be high rainfall, high erosion, and basically the Tibetan crust senses this weakness and gets extruded through the Himalaya. Now, a bunch of problems with this model, in fact, recognized almost immediately. In fact, by members of the in-depth group. Here's Makovsky and Klemper point out that you can see the bright spots in red. That curve extends, in fact, is trending towards H2O, that's water, as opposed to melt. So silicate melt would plot on that distribution between, say, upper crust or granite and melt, but the bright spots look, in fact, more like an aqueous fluid. This moho underneath southern Tibet is seismogenic. It's cold down there, okay? So it's a little unusual that you'd have this perpetually hot middle crust with a much colder moho. Recent seismic work shows, yeah, there are low velocity layers across the Himalaya, but in fact they're intermittent. There doesn't seem to be a continuous channel. And in fact, they found that it was outside where, in fact, the classic channel flow model would put that material. Here's a recent MT study in Sikkim, Himalaya, saying that, we can see these anomalies, these conductive regions, but we calculate viscosities and partial melt fractions that, in fact, simply wouldn't permit this viscous extrusion as hypothesized. Now, we've known for 20 years that, in fact, if you look at S-wave splitting in the just below the Moho and look at the direction of transport, it essentially matches, okay, the GPS, the surface GPS. Hard to imagine how you have this coherent counterclockwise transport of Asia to the east and southeast if you've got a delinked, weak middle crustal layer. When you actually go up into the rift flanks, okay, the uplifted flanks from these north-south graben, and look at what the middle crust was like, well, let's say in this case 8 million years ago, you don't see anatectic, you don't see partial melts, minimum melts, or sorry, minimum melting. What you see is either hot anatectic melting or calc-alkaline granitoids, indicating the presence of mantle heat. And lastly, and this makes sense, anybody that's been to Lhasa, you switch on the light in your hotel room, on average, half the electricity is coming from geothermal stations that are being run by steam coming off just immediately above these bright spots, suggesting that, in fact, this is not likely to be molten silicate down there, but in fact, very hot, conductive water. The helium isotopes that come out of that, they don't scream crustal melting, intracrustal melting. They basically say, oh, look, I came from the mantle. Now, some other problems here. We seem to have a translation problem. Let's see where. Well, let me just read you what we've got here. There is a kind of stratigraphy in the Greater Himalayan sequence. Formation 1, 2, and 3. Formation 1 is basically peelites. Formation 2, calc-silicates. And Formation 3 is, in fact, you can see it peeking out on the right. It's a very characteristic ogg-and-gneiss that you can follow hundreds and hundreds of kilometers along strike, just below the South Tibetan detachment. Now, conceptualized, right, you've got the leading edge of India. You've got these Indian metasediments have been thrust through the suture, hundreds of kilometers to the north. Now they've, in fact, been squirted back. Hard to imagine how you would maintain that stratigraphic coherence. In addition, let's see if this is going to help. Okay, not really. The Beaumont model, I went to some pains to point out that it requires this narrow aperture of erosion in order to produce that tectonic aneurysm. But when you, in fact, look at the cross-sections of the Greater Himalayan sequence, here shown in pink, you can see that the nappes can extend as much as 100 kilometers south of the MHT. That is, there isn't this this very narrow aperture of the Greater Himalayan sequence being squirted out. You've got this big 100-kilometer long thrust nap sitting on top of the Lesser Himalayan sequence. So not consistent. Oh, and lastly, if you're going to drive all that material, that Indian material, through the suture and through the Gandhisi batholith, the active continental arc, and then back with 500-mile round trip. Here we go. Okay, who is the culprit? You look at the detrital zircons in the Greater Himalayan sequence here in red. You don't see a zircon younger than that 490, actually younger than exactly this rock here, that 490 million year ogg-and-gneiss. So how did you manage to push that material through, across the suture, through the active arc and back, and not pick up a single Gandhisi zircon in the path? Okay, now actually back to our paper in, remember these are the thermobarometric transects here. I'm going to point out Kona a little further up section here in the Tethys, the North Himalayan granite, and then the Everest section here, which is dominantly these high Himalayan leucogranites. Okay. What do we see? Well, I think everybody can agree, looking at the temperature and pressure from the thermobarometry, there's the main central thrust. You've heard about that multiple times, Lesser Himalaya, Greater Himalaya. Okay. There's no question that what we see, everybody agrees, there's a big jump in pressure and temperature across that. Makes complete sense. And this is what you would expect to see in the thermobarometry from a large magnitude, long duration thrust fault like the MHT. Now, interestingly, you see both in the Lesser Himalaya section, which we can, in fact, we can see intra LHS thrusting here, less clear up here, say the stratigraphy is not as clear, but you see essentially constant temperature across the Lesser Himalaya and the Greater Himalaya sequence. That's not what you see, or not what you would expect from a channel flow type model. I'll show that in a sec. Pressure is going to really depend on specifics, but you would expect pressure to decrease along a lithostat in the critical taper model. Maybe the Kuma one showing, by that I mean something like 3.5 kilometers per kilobar. The ductal extrusion model, you could expect potentially anything from this to a much lower seeming lithostat. What does the Beaumont model predict? Well, back 25 years ago or so, sure, here's the temperature. They had Lang-Tang data. That was, in fact, the data here shown in the red boxes. Okay, that was really the quality data back then. The fact is their model doesn't really fit that particularly well, and the more data we have, the clearer it is that the thermobarometry is at face value inconsistent with the channel flow model. So on balance, through the Lesser Himalaya, Greater Himalaya sequence, the thermobarometry is in fact saying, yeah, we're more consistent with thrust and placement than ductal thinning. Is it uniquely indicative? No, not necessarily so, but it's certainly, if you had to choose between one of those models, that'd be it. Okay, we could also do petrochronology, and we can do the accessory mineral thermometry. There's a couple of PT diagrams, okay, pressure, temperature. Okay. This one here is, we're looking at isoplex of garnet fraction. You can see as you, in fact, increase on this clockwise PT path, you're going to get more and more garnet, and then as you retrogressively cool, the garnet's going to be resorbed. Now, here's something about garnet you may not have known. Garnet loves yttrium and rare earths, okay, particularly heavy rare earths. So if we look at the accessory minerals, the coexisting accessory minerals, say zircon and monazite, that are forming at the same time as the garnet is either growing or, in fact, dissolving retrogressively, we can actually find something very profound. Look here at Everest. What we see is the yttrium content in the monazite dropping between about 30 and 20, 25 million years, and then growing. Garnet is growing here, and it's being resorbed here. That's the prograde path. That's the retrograde path. Okay. Here at Kona, remember high up in the Tethys, we see ages as old as 40 million years. That's expected. That's the, we call that the Eo-Himalayan phase of Himalayan evolution. And for example, Dala, we documented that the deformation there in the Tethys sediments is over by about 44 million years. So this is exactly what you'd expect. And depending where you are in the section, this age discontinuity here could either be as old as Eo-Himalayan or, in fact, peak here at this expected age of 25 million years when we think that the main central thrust got underway. Okay? We can also do accessory mineral saturation thermometry. I'm not going to dwell on this too much, and that is simply that there's a limited amount of both zirconium and light rare earths that a crustal melt can dissolve. The amount dissolved is proportional, or is a function of the composition of the melt and the temperature. So we can in fact see that the North Himalayan granitoids hotter on balance than the high Himalayan leucogranites here. That's interesting. To me, that's saying that this is forming, these ones are forming by muscovite dehydration melting. These are forming by biotite dehydration. And I'll come back to that. Now, a couple of qualifications here. 20 years ago, it was pretty clear because the ICP, the inductively coupled mass spectrometry approach had really yet to be developed. So all the ages were ion probe, okay, which can correct for common lead. And so you get accurate and precise uranium lead ages or thorium lead ages. Now, with the advent of a method that can't detect, or to a large degree, the common lead, you get ages that are too old. And what's happened is that's obscured the age difference between the high Himalayan and North Himalayan granites. Also, too, on diagrams like I showed you in the previous slide, of lots of data between 40 and 20 million years, remember we're comparing 1,000 cubic kilometer plutons in the same diagram as a little dike, the size of your vehicle. So when we look at the dominant, the big granitoids, the gangotries, the manislus, and so on, basically low temperature, high Himalayan leucogranites, higher temperature North Himalayan domes. Okay, so what drives anatexis? First, we don't think that these rocks are coming from deep into the Tibetan plateau. I've already pointed out, these things like, for example, in the Langtang section, they got buried deep, 13 kilobars, okay? That's way down there. So, it's going to get hot. The heat production, if you look along strike in the greater Himalayan sequence, the heat production is high. So we don't need external heat. Here's a plot PT diagram showing the water-saturated solidus for muscovite dehydration melting I've mentioned. And you can see the isoplus, 10% melting, 20% melting. There's lots of muscovite in that greater Himalayan sequence that's able to if you can get to these sorts of conditions, say 730 degrees and this kind of mid-deep crustal rocks, you'll produce a melt in situ. It's not a result. It's not actually lubricating anything. It's simply a consequence of it being deep and hot. But notice that, in fact, 30 years ago, the idea of decompression melting was very popular. That is, if you, in fact, have orogenic collapse, you take a lot of material off the top, you'll enhance melting. But notice that these isoplus are essentially vertical. You can drop 20 kilometers of crust and not increase the melting at all. I'm very fond of, this model here we came forth with about 25 years ago, in which, in fact, everything happens on the main Himalayan thrust, okay? This thing here, this is where the North Himalayan granites are going to form. Here's the high Himalayan granites. We start at 25 million years, continuously slip on that thrust. This region here has been depleted by that Eo-Himalayan melting that, in fact, we demonstrated earlier. And what we find is we can explain the inverted metamorphic sequence, we can explain the distribution of the thermobarometry, and we can explain the difference in age between the high Himalayan leucogranites. You see, if we start the clock 25 million years ago, by 20 million years, we produce 10-15% melt in the high Himalaya. Now at around 16, 15 million years, we're producing melting a couple of 100 kilometers in the north. I think this is a viable model today. Okay, so what's the status of channel flow? Well, I think it's clear that the Nelson-Beaumont model, somebody needs to drive a stake through its heart. It's dead, okay? So why did Searle and Cottle maintain this terminology? I think in part it's semantics. The channel flows reverted to its original sense. Here in their paper, they basically say the initial paper is Searle and Rex 89 from the Zanskar Himalaya. Interestingly, although you'll see these overturned, these recumbent isograds here that are consistent with ductile shearing, all the granites, in fact, here, here, and here, they're cross-cutting. There's no synchronous granite melting. Now, they actually didn't use the term crustal channel flow. Grujic, a couple of years later, actually evoked their sense of the isograds, did explicitly channel flow models, but in fact, in their paper, Searle and Cottle effectively limited melting to south of the suture. And I say, the fact that it's not consistent with the thermobarometry, I think, is a mark against it, but at least it appears that nobody is insisting on squirting melt from a couple of 100 kilometers north through the Himalaya anymore. So I think we've made some progress, but beware the term channel flow because it seems to be transmogrifying. Okay, thank you.
I would like to thank all the speakers for their wonderful presentations, and equally important that they have saved some time. I think for 10 minutes before the tea break, coffee break, we can ask questions or suggestions, give suggestions. Thank you. The question can be referred to any of the speakers, please.
My question goes to Dinglin, but maybe also to others. When in 2012, von Hinsberg et al. Came up with this double subduction model with this Tetian Himalayan terrain separated from the Indian plate, many were puzzling, where is the remnant of the ocean crust south of the Tetian Himalaya, south of the Greater Himalaya, and this question is still existing, at least for me. And if this model can work, it means that the oceanic crust has totally disappeared. And it's well investigated along the Himalaya that nobody found the remnant of this oceanic crust. So I ask your opinion now, because it's persistent in the literature. This Tetian Himalaya hypothesis. What do you think about it? Should we be very critical, or should we completely forget it based on geological constraints?
My opinion is clearly, I persist the one-stage collision. There's this Greater Himalaya, which collided at the middle with Eurasia at about 65 million years ago. Because for the multi-stage collision, they need another extra suture zone in Tethys Himalaya and High Himalaya. After 10 years work, nobody find another extra suture zone in this region. So there is no multi-suture zone there. So I think my opinion is one-stage Greater Himalaya collision model. That's my opinion.
I'm sure you have something to ask. Please, we have 5 more minutes.
Sorry, I have another question if no one else. Okay, to Mark. When the channel flow model came up, it looked very amazing, how much you can explain by this model. And then looking as a geophysicist on the stratigraphic sequence in the Tibetan Himalaya and the Greater Himalaya in the Annapurna and Dhaulagiri region, I was really asking how should that work, yeah, because it's a continuous sedimentary section which becomes higher metamorphic at the base in the Dhaulagiri limestone, and then you should have a channel there. How should that work, yeah? That you have a channel left and right, yeah, but not there. And obviously I could not see how I can explain the existence of a channel, especially in this region of the Dhaulagiri and Annapurna. No? So I was also surprised why this is not explained. But you gave a clear vote for forgetting the channel flow model. If Mike Sill would be here, no, then he would have a different opinion. And so I would agree. And I spoke to many, and they say also, channel flow model is amazing model, but it doesn't work. No?
Okay, you know, I think that the amplification is causing more confusion than not. Can you hear me in the back? Yeah. Yeah, look, well, thanks for the affirmation. But in fact, as I pointed out in the introductory talk, I think I'm good. Good. You know, here's a case where the geodynamics and the geochemistry were completely delinked. That it was very appealing to people that didn't have a solid or deep grasp of the implications of the geochemistry. Now, the other thing, of course, it's a little unfair. 30 years later, we've got a lot more thermobarometry, a lot of good thermobarometry, so that's becoming clear. Although you can see that even when Beaumont published that model 24 years ago, the data did not fit the curve without comment. So as I get into my dotage, as I become a literal and figurative graybeard in the field, I actually am getting more interested in understanding why it is that deep time geologists believe the things that they do. Because I see us in deep time studies, finding a model very attractive, signing on board, becoming part of the tribe, without truly understanding the implications of fields outside our specialty. That's what I find appealing about PlateauPlus, is the idea of breaking through disciplinary boundaries and making comparative studies and having an open dialogue rather than, like I said, repeating a tribal chant 30 years later. Thanks for the opportunity to do a soapbox.
Okay. Me? Okay, let me introduce myself. My name is Raihan. I'm from Geophysics Department, State College, Meteorology and Climatology and Geophysics. I want to ask to Prof. James Murray, especially for seismic 3D models. I want to ask about the data and method. Could you explain more about the magnitude and depth range of your data? And also, could you explain more about the inversion method you use or the program or software applied? Is it linear inversion or nonlinear? Thank you.
Actually, I couldn't understand very well the question. Can you repeat it?
Okay, maybe the range of data, magnitudes from 0 until what, and then the deep range data.
Okay, thank you. So for the magnitude, so we're looking at a lot of aftershocks. So most of those are about magnitude 1 to 3, something like that. And the depth of the earthquakes are from about the surface, maybe 0 kilometers to about, I'd say 15 to 20. The actual rupture didn't go very deep. It only went to maybe 15 or 20 kilometers. So there aren't very many aftershocks deeper than that. You could use more seismicities from different time periods to get deeper depths. But for that particular data set, which is mainly just aftershocks, you were looking at, like I said, maybe 0 to 20 kilometers depth and magnitudes around 1 to 3. Okay, did that answer your question?
Okay. Yeah, okay. Maybe for another question about your inversion method.
I'm sorry,
Okay.
I can't. Okay. Yeah, why don't we talk later?
Your method.
Yes. Okay, thank you. I'm Morteza Talibian from Geological Survey of Iran. My question is to Dr. Soko Adi. Yeah, you proposed backtrusting for the region based on your seismological observation. And my question is there any geological or geomorphic evidence for such a backtrusting? How well is this fault is understood?
Bisa ada yang bantu menerjemahkan ya, Mas Bagus mana? Sorry, ada yang bisa menerjemahkan, bantu terjemahkan, Pak Suci. Ya. Sorry, I look at my presentation. Oke. Mengapa ada backtrust ya, Mbak Suci ya? Ya, baik. Sebentar. Okay, thank you very much for your question. A backtrust, this evidence, this is backtrust in the accreditation width. My research is backtrust system for the earthquake and magnitude 5.7 because the short dipping. And different with magnitude and 5.9 because backstop system with dipping. This evidence of backtrust in the aggression width. I'm sorry. Okay? Thank you very much.
Ladies and gentlemen, this brings us to the closure of this wonderful session. I request all of you to clap hands in appreciation of the speaker's presentations. Thank you, please.
Okay, please. Once again, give a big round of applause for the chairs and all the speakers. And at this joyful occasion, we will now proceed the presentation of a plaque as a token of appreciation from BMKG to all keynote speakers. Please remain on this in front of the stage. Professor Linding, Professor Mike Harrison, Prof. Andreas Purk, Dr. Suko Praitno Adi, and Professor James Mori, and also Professor Muhammad Qasim Jan. Please join us into the front of the stage.
And we would like to invite the Deputy Head of Geophysics, BMKG, to join us on in front of stage. to give, yeah. No, in front of the stage.
The documentation team, please be ready to take a picture. And first, we invite Ibu Nelly to deliver the plaque for Professor Linding. Professor Linding, yes, first.
Professor Linding.
And then to Professor Mike Harrison. Please give a big round of applause. Please face to the camera so we can capture this beautiful moment. Okay, Professor Linding, please join into the front of the stage to receive a plaque from Deputy Head of Geophysics, BMKG. And there's still a plaque for Dr. Zuko Paetno Adi. And now please take a picture together with the documentation team, to all chair and speakers, and also the deputy head of BMK, the geophysics of BMKG. Please face to the camera in front of you. Thank you. Once again, please give it a round of applause. Thank you once again, and please return to your seat.
Ladies and gentlemen, we will now take a short coffee break. Please enjoy the refreshment, and we look forward at probably at 11:30, and we provide the coffee in the 2 spots, inside the room and outside the room. Please enjoy the coffee break, and please get back in the 11:30.
And we want to inform you, after the break session, for the convenience of everyone and to ensure we maximize our seating capacity, please help us by moving into the front row. We have plenty of space up here for you to enjoy the presentation. Please fulfill the front row seat first for the opening ceremony. Thank you once again. And also, we invite all the participants to visit the poster site into the left and the right side of this auditorium. Please visit the poster already standing there, and maybe there will be siapa? So once again, we kindly invite all participants to visit the poster standing beside the auditorium in the left and the right side while enjoying your coffee break. Thank you.
To all our speaker and VVIP guests, you can take your coffee break behind the stage, the room behind the stage.
Once again, we inform for all speakers and chairs, you can enjoy your coffee break at the VVIP lounge behind of this auditorium. Dan kami sampaikan kepada Bapak Ibu peserta, mohon untuk tidak meninggalkan area auditorium karena tepat pukul 11.30 akan diadakan opening ceremony atau upacara pembukaan kegiatan pada pagi hari ini yang akan dihadiri oleh Kepala Badan Meteorologi, Klimatologi, dan Geofisika. Jadi sekali lagi kepada Bapak Ibu peserta yang menikmati coffee break, mohon untuk tidak meninggalkan area auditorium. Boleh untuk keluar di area teras auditorium, namun mohon untuk dapat kembali 5 menit lagi ke auditorium dan langsung mengisi kursi-kursi bagian depan terlebih dahulu agar tidak terlihat kosong. Kami mohon kerjasamanya karena acara ini pembukaannya akan dihadiri oleh Kepala Badan Meteorologi, Klimatologi, dan Geofisika. Terima kasih.
Two. 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 Two.
Nanti balik lagi nggak mejanya?
Check this. Check. Check. Check, check. Check. To all participants, may we have your attention? The opening ceremony is about to begin. To all participants, please check. Please return to the hall and be seated. And before we commence the proceedings, we kindly ask all attendees to turn off or set your mobile phones to silent mode. And for the convenience of everyone, and to ensure we maximize our seating capacity, please help us by moving into the front row. Sekali lagi kepada Bapak Ibu peserta yang masih berada di luar ruangan, mohon untuk dapat memasuki auditorium kembali karena acara pembukaan akan segera dimulai, dan mohon bantuannya untuk dapat mengisi kursi-kursi yang masih kosong di bagian depan terlebih dahulu agar tidak terlihat kosong di kamera maupun di auditorium itu sendiri. Sekali lagi kami mohon pengertian dari Bapak Ibu peserta untuk dapat mengisi kursi-kursi bagian depan terlebih dahulu, dan apabila telah selesai menikmati coffee break-nya, mohon untuk dapat kembali ke auditorium. Check, 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 check.
tes.
Ini aja kok. Udah tak pilih yang paling gede suaranya.
Tes.
Bapak Ibu yang masih berada di luar auditorium, pembukaan akan segera dimulai. Mohon untuk dapat masuk ke auditorium dan mengisi kursi-kursi bagian depan terlebih dahulu. Sekali lagi, masih banyak kursi kosong di sisi kiri depan dan sisi kanan depan. Mohon untuk dapat diisi terlebih dahulu. To all participants, may we have your attention. The opening ceremony of the workshop is about to begin. To all participants, please return to the hall and be seated. Sekali lagi bagi Bapak Ibu peserta yang masih berada di luar auditorium, mohon untuk dapat segera masuk dan mengisi kursi-kursi bagian depan terlebih dahulu. Masih banyak yang kosong, kita akan segera memulai.
Ladies and gentlemen, head of BMKG and all the VVIP guests is now entering the auditorium.
Assalamualaikum warahmatullahi wabarakatuh.
Good afternoon, ladies and gentlemen. Welcome to the opening ceremony of the second PlateauPlus International Workshop.
PlateauPlus Synthesis, Earth Dynamics, Environment, and Human Adaptation. Please give big round of applause, ladies and gentlemen. First of all, in this occasion, we would like to extend a warm welcome to Excellency, the Head of National Agency for Meteorology, Climatology, and Geophysics of the Republic of Indonesia, which is called BMKG, Professor Teguh Faisal Patani, PhD.
The Director of Tibetan Plateau Earth System, Environment and Resources, Professor Linding.
The Deputy Head for Geophysics of BMKG, Dr. Nelly Florida Ariama, MSI.
The Co-Chair of International PlateauPlus Association, Professor Mark Harrison.
To all speakers, chair, distinguished guests, esteemed professors, researchers, and participants both online and offline.
Ladies and gentlemen, first of all praise to the God for blessing us for today with this wonderful occasion and granting us to the opportunity to gather here today in a good health and spirit.
And ladies and gentlemen, to commence the opening ceremony, we invite all attendees to stand for the singing of the national anthem of the Republic of Indonesia, Indonesia Raya. Please be standing. Thank you. Please be seated.
Next agenda, we invite the Deputy Head of Geophysics BMKG, Ibu Dr. Nelly Florida Riyama, to deliver the report of the event. To Ibu Dr. Nelly Florida, the time is yours.
Excellency, Head of BMKG, Professor Teguh Faisal Fatani, PhD, Honorable Academician of the Institute of Tibet and Plateau Research, Chinese Academy of Science, Professor Linding, representative from China, all invited deputies from BMKG, all the keynote speakers and distinguished guests, the Director for Spatial Planning of the Ministry of ATR BPN or the representative, the head of Center for Geological Survey, Indonesia Agency for Geology, from Bandung Institute of Technology, Pajajaran University, the State of Meteorology, Climatology and Geophysics, all invited guests. A very warm welcome to all of you. We are very delighted here to have you here in Indonesia, in Jakarta, especially in our BMKG office. Distinguished guests, ladies and gentlemen, the second PlateauPlus workshop is scheduled to take place in the headquarters of BMKG, Jakarta, from today, 25th to 26th, and followed by a field trip to West Java on 27th for limited participants. This significant event is graced by the presence of many accomplished and notable experts and speakers from various countries, including from China, Germany, Indonesia, Iran, Japan, Oman, Pakistan, United Kingdom, and USA. This workshop is designed to present the significant importance of collaboration in researching plateaus, which serve as a natural laboratory for studying the Earth evolution over time and its consequential impact of the human environment. Although it may seem that Indonesia as an archipelagic nation is not situated in any of the world plateaus, its tectonic, climate, and atmospheric conditions do interact with plateaus and influence the socio-cultural aspect of communities inside. But we have our high high plateau, not like Tibetan in Puncak Jaya. And thus, this workshop has become an important point for our nation also. In the course of 2 days, we will engage with presentation and talks covering the diverse topics related to plateaus and others, or including in talking about climatology also. There will be at least 46 oral presentations delivered across different academic backgrounds, organized into several sessions. Furthermore, research posters are also displayed on both the right and left side of this room, showcasing research conducted across various related topics. Participants are invited to view the poster with more than 60 contributions already highlighting the event. This occasion is attended by over 200 participants, and we have also facilitated access through Zoom and YouTube streaming, enabling many more to join and witness the proceedings. I wish to express my deepest gratitude to all speakers and poster presenters for their contributions, which have greatly enhanced the scale of this event. This highlights the importance of this conference, where we can gain insight into the advancement of research in various fields. Participants can also benefit immensely from this event by establishing valuable professional connection. I must also thank the organizing committee from ITP CHAS, BMKG, and STMKG for their excellent work in preparing this event. Should any participant have inquiries, please do not hesitate to contact them. Thank you once again, and we do hope that this conference has been both meaningful and beneficial for all of us. Thank you very much.
Thank you, Ibu Dr. Nelly Floridariama, for your report.
Distinguished guests, ladies and gentlemen, our next agenda is welcoming session. We are honored to invite the Director of Tibetan Plateau Earth System, Environment and Resources, Institute of Tibetan Plateau Research, China's Academy of Sciences, Professor Linding, to deliver the first remark. To Professor Linding, the time is yours.
Our honorable head of BMKG, Professor Toku Fatani, thank you very much. Distinguished guests, Deputy for Geophysics, Nelly Florid, Director for Earthquake and Tsunami, Diano, representative from BMKG, BRIN, and partner institutions, researchers and academics from universities around the world, all keynote speakers, presenters, and participants. It's my great pleasure to greet you to the second PlateauPlus International Workshop here in Jakarta. As the chair of the PlateauPlus Association, I extend our sincere appreciation to BMKG for hosting this workshop and for the warm hospitality provided to all participants. We also thank the Deputy for Geophysics and the Directorate of Earthquake and Tsunami for their strong support in making all things possible here. Ladies and gentlemen, Indonesia is a truly meaningful venue located at a convergence of three major tectonic plates: Eurasia, Australia, and the Pacific plates. It provides a real natural laboratory for studying the subduction, earthquake process, and crust deformations, themes that align with the core scientific focus of PlateauPlus. This year, the theme PlateauPlus in the 30th domain is highly relevant for BMKG. Plateau system influence climate circulation, hydrology, and environmental dynamics, while their tectonic origins are closely linked to earthquakes, volcanic activity, and the tsunami generating process. This makes the scientific exchange we begin today not only valuable academically, but also deeply connected to the Indonesia multi-hazards context and BMKG's mandate in meteorology, climatology, and geophysics. Dear ladies and gentlemen, since our first gathering 2 years ago, PlateauPlus has grown into an active international community. A major milestone was the endorsement by the UNESCO as a part of International Decades of Science for Sustainable Development, strengthening our global resilience. Early this year, our summer training program in Linzhi, Tibet, brought together young researchers from 80 countries and renowned experts from around the world, demonstrating our commitment to capacity building and collaboration. The partnership between ITPCAS and BMKG has already shown meaningful impact. One clear example is Dr. Bagus Andy Wimbobo. He's a alumnus of ITPCAS, who now play an important role in strengthening Indonesia's scientific capability. We believe this cooperation will continue to grow and bring even greater benefits. Ladies and gentlemen, as this workshop begins, I encourage all of us to exchange ideas, explore research opportunities, and build a long-term partnership that advances technology and resilience, not only for our scientific community, but for the society. Before closing, I would like to express deeper appreciation to organize the committee and all team members. This successful event is a result of their dedication, coordination, and teamwork. May this workshop be productive, inspiring, and impactful. Thank you all.
Thank you, Professor Linding, for your comprehensive remarks.
Ladies and gentlemen, we have reached the pinnacle of our ceremony. It is an immense privilege to invite the head of BMKG, Professor Insinyur Teguh Faisal Patani, PhD, to deliver his opening remarks and officially open the second PlateauPlus International Workshop. To Professor Insinyur Teguh Faisal Patani, PhD, the stage is now yours.
Honorables, Director of the State Key Laboratory of Tibetan Plateau Earth System, Environment and Resources, Professor Linding. Honorables, the co-chair of the International PlateauPlus Association from University California of Los Angeles, Professor Mark Harrison. Co-chair of the International PlateauPlus Association from Pakistan Academy, Professor Muhammad Qasim. Representative from Ambassador of China, the Deputy for Geophysics of BMKG, Dr. Nelly Florida, the Deputy for Weather Modification, Dr. Tri Handeko Seto, representative from the Ministry of ATR BPN, Indonesian Agency for Research and Innovation BRIN, Indonesian Agency for Geology, Indonesian Agency for Geospatial, the researchers from Bandung Institute of Technology, Pajajaran University, the State School for Meteorological, for Meteorology, Climatology and Geophysics, STMKG, the Chinese Academy of Sciences, and from various research institutes and universities in China, invited speakers, presenters, participants from various research centers and universities around the world. First of all, I would like to say very sorry that I being late in joining this important workshop, because previously I should attend the MOU signing ceremony with the Minister of Environment and also the head of Indonesian Geophysical Information Agency. Plateau acts as natural laboratories for studying processes shaped by tectonics, climates, and human activities. Examining global plateau and archipelagic environments reveals how geological, environmental, and anthropological factors interact, deepening our understanding of the Earth and humanity's role in it. The archipelago of Indonesia is shaped by the interaction between the Indo-Australian plates in the west and south and the Eurasian Pacific and Philippine Sea plates in the north and east, just has been mentioned by Professor Linding. This complex setting has built up very active tectonic earthquake activity, both from active faults and megathrust, as well as active volcanic arch belt along the region. The activity of volcanoes is influenced by the activity of tectonic subduction along our subduction margin. Large explosive eruption, for example, Tambora in 1815 and Krakatoa in 1883, injected aerosols into the stratosphere and produced measurable short-term global climatic effects. The threat of a tsunami from tectonic activity forces us to always be prepared, especially in the wake of the devastating 2004 9.1 magnitude of Indian Ocean earthquake and tsunami. Therefore, the complex tectonic, climate, and atmospheric conditions of our archipelagic nation interact with those plateaus outside our region, which influence the socio-cultural effects of our people and their awareness of natural disaster mitigation. Ladies and gentlemen, let us use this event as an opportunity for joint efforts to understand the dynamic of the Earth, and any discussion that results here could be used to inform a better future in scientific and disaster hazard reduction effort. Any efforts can contribute to reduce the possibility of human casualties during a natural disaster. May everyone involved in this workshop be benefited, and let us use this opportunity to engage and expand our network, also deepen our collaboration in understanding the Earth with its processes. I would like to express my appreciation to the committee who arranged for this workshop, and I do hope that we will have an enjoyable and productive workshop today in next few days. I hereby formally open the second PlateauPlus workshop in Indonesia. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you. We kindly ask the professor remain on stage to carry out the symbolic opening of the event.
We also invite the director of TPESER, deputy head of geophysics, and deputy head of weather modification of BMKG to join at the stage to accompany symbolic opening.
All right, ladies and gentlemen, next we respectfully request the head of BMKG to symbolically open today's event by striking the gong. Let's count down together. In 3, 2, 1.
Next, to express our profound gratitude and appreciation for the continuous partnership, we would like to present a token of appreciation.
Once again, we respectfully invite the head of BMKG to present the plaque to the director of TPESER. And to the documentation team, please be ready to capture this amazing moment. To head of BMKG and the director of TPESER, please step forward to deliver and receive the plaque. Please face to the camera so we can capture this beautiful moment. Thank you. Once again, thank you to the head of BMKG, the director of TPESER, and the co-chair and all of the deputy heads of BMKG. Please return to your seat. Thank you. Okay, but first we have to take a pictures. To the documentation team, with our BMKG pose. This is our pose to take a picture. Thank you. In 1, 2, 3. Thank you for your applause. We kindly invite all of you to return to your seat. Once again, please give a bigger round of applause to the head of BMKG and the director of TPESER.
Ladies and gentlemen, before we continue, let us take a moment to pause and pray. At this time, we would like to invite Mr. Hakul Fahmi to lead us in a moment of prayer. Hakul Fahmi, the floor is yours.
Assalamualaikum warahmatullahi wabarakatuh. Distinguished ladies and gentlemen, I invite all of you to join us in a moment of reflection and prayer, according to your all respective faith. I will lead this prayer in accordance with the Islamic tradition, and I kindly ask all non-Muslim guests to observe it in silence according to your own beliefs and convictions. Let us begin. Bismillahirrahmanirrahim. Alhamdulillahi Rabbil Alamin. Wassalatu wassalamu ala ashrafil anbiya'i wal mursalin. Wa ala alihi wa sahbihi ajma'in. Ya Allah, Ya Alim, the All-Knowing. We gather today for the second PlateauPlus International Workshop to study the intricate connections between Earth dynamics, environment, and human adaptation. We seek your blessing on the minds and work of all scientists and researchers present. Grant us the clarity to unlock knowledge about deep Earth structures and natural hazards, and wisdom to mitigate the impacts of hydrometeorological disasters in the tertiary domain. Ya Allah, Ya Hadi, the guide, let this cooperation foster strong and lasting international partnerships between all nations represented here. Guide our efforts so that our joint research may truly benefit humanity and secure a resilient future. We ask for your protection for all participants and a safe and successful conclusion to this workshop. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Walhamdulillahi rabbil alamin. Wassalamualaikum warahmatullahi wabarakatuh. Thank you.
Thank you, Mr. Hakul. Ladies and gentlemen, following the prayer, we invite all of the participants to take a photo session. We kindly ask you to stand at your place, and the documentation committees will be take your photo from the stage.
So we invite all the documentation team, please going to the stage. To documentation team, please, the photographer, please come to the stage.
And all of the participants, please be seated on your place. Sorry, please be stand on your place.
To all participants, just remain on your place, and the documentation team will take a picture from the stage. Thank you. Please smile with your best smile. In count 1, 2, 3. Okay, and the next pose, BMKG pose, still remember? Yeah, and then count 1, 2, 3. Thank you. Please give big round of applause for all of us. And by the end of the final of the photo session, the opening ceremony for the second PlateauPlus International Workshop is officially adjourned. We thank all our speakers and esteemed guests for their presence, and we will now take a 1-hour break for lunch.
Okay, we kindly request all the VVIP guests and speakers to have a lunch in backstage, in behind this hall. All of the speakers and VVIP guests, you can take your lunch at behind the stage.
So once again, we kindly invite all VVIP guests, esteemed speakers, and session chairs. Please please proceed to the VIP lounge located directly behind the stage. Thank you. And to another participants, you can enjoy your lunch in front of the auditorium in the table of the registration.
Bapak Ibu peserta bisa mengambil makan siangnya di meja registrasi. Terima kasih.
Bapak Ibu eselon 1, eselon 2, kami harap dapat bergabung ke VIP Lounge untuk menikmati makan siang. Sekali lagi kepada Bapak Ibu eselon 1 dan 2 untuk dapat bergabung ke VIP Lounge untuk makan siang bersama dengan Kepala BMKG. Terima kasih. And for your information, the first technical session, Deep Earth Dynamics and Tectonic Collision, will commence promptly at 13:25 at local time. Once again, at 13:25 at local time. Thank you and please enjoy your lunch.
Bapak Ibu peserta, kita akan kembali ke ruangan auditorium di jam 1:25. Terima kasih. Mobilnya udah makan. Mobil udah.
NTRB itu tsunami ready-nya Sanur Paus. Gimana sih prosedurnya? Setelah dari temper kan kita kan nyampein ke NTRB itu.
Biasanya mereka diminta presentasi dulu di depan NTRB.
Di sana berarti kan? Atau di Jakarta? Oh, online aja. Catatan tadi evaluasi dari mereka.
Itu amanin kita mah. This one. Okay. I see.
Itu masih nggak mungkin tuh fungsinya pengamatan yang tuh fungsinya kan seperti kortipnya itu emang konstitusional gitu lah jelas kortip aja jadi ikut nanti Pak
sudah lengkap. Tanya Mas Safid. Mas Angket.
Panama tapi masih ingin rasa.
Attention please. We kindly request all attendees to make their way back into the auditorium. Our next session about deeper dynamics will commence in less than 2 minutes. Once again, we can request all attendees to make their way back into the auditorium. Our next session will commence in less than 2 minutes. Thank you.
In order to stay within the schedule, I would like all speakers of the next session already to move up onto the stage. This is forward.
Yes.
And this is back.
Yeah, right.
And this one, now it does work. So you do have a pointer. I didn't know that.
Okay.
So
Okay.
you can, they will show your slides and then forward and backward.
Okay. Okay. Thank you. 응? 이 안에야. 이게 빨리 저上面来. 네,它스피커하고那个报告人料.
Good afternoon, ladies and gentlemen. Welcome back to the second PlateauPlus International Workshop. We hope you had a pleasant and refreshing lunch break, and now we are ready to commence our first technical session of the workshop.
We hope you had a pleasant and refreshing lunch break, and now we are ready to commence our first technical session of the workshop.
And we now Session 1, Deep Earth Dynamics and Tectonic Collision. The focus of this session is on geophysics, mental dynamics, subduction zones, and lithospheric structure. And the session is scheduled from 13:25 until 15:05 with local time, and will feature insightful presentation concerning the structure and dynamics of Earth beneath our feet.
It is our distinct honor to introduce and hand over the proceeding to our esteemed session chair, that is Professor Andreas Mulk and Professor Dicheng Zhu.
Yes, and Professor Dr. Andreas Mulk is a director at Sandberg Research Institute and Natural History Museum, Frankfurt. Currently, he holds the position of professor at Goethe University, Frankfurt. Please give a round of applause to Professor Andreas Mulk. And Professor Di Zhangzhu is professor in China University of Geosciences, Beijing, with research interest on geochemistry, geodynamics, petrology, and plate tectonics. Please give big round of applause to all chairs. Thank you.
Thank you.
Yes, I would like to remind all speakers that we have 10 minutes allocated, and you will hear a bell after 8. So once you hear the bell, there's 2 minutes left in order for the rest of the program to stay in time. I would directly like to hand over, and we hear the first presentation.
Hello, everyone. Good noon. I'm Dicheng Zhu from China University of Geosciences, Beijing. I'm very happy to have this chance to present our recent work on the cluster evolution in collision zone. The topic of this time is about accumulation and its impacts on Earth's habitability. I will introduce my talk from this outline. So the first is, what is accumulation? Aquamelting is created by myself. This is based on my research studies in collision zone, in India-Asian collision zone. As we know, in collision zone, it experiences oceanic subduction and continental collision. We know that during pre-collision, it is characterized by the generation of water-rich mafic arc magma. After that, during the pre-collision, syncollision, and the post-collision, it is dominated by the extensive colossal melting. So during the pre-collision, it is dominated by the accumulation, the formation of whatever Homeland-rich cumulates during pre-collision and the remelting during the subduction, late subduction, syncollision, and the post-collision. So I take the first 4 letters and the last 7 letters combine to form a new word, accumulating. It means that the cumulates formed during the pre-collision and followed by remelting is remelting. This process is triggered by lower back and the slab break off. So maybe you can ask me why we should have a new word, accumulating. I think there are 4 key points. The point 1 is that the mafic, ultramafic cumulates may be retained in the newer class rather than being delaminated like before. Previously, as we know, the mafic, ultramafic cumulates has been proposed to delaminate because they are high density. However, recent studies indicate that if the presence of 10 to 18 water melt in the melting residue accumulates, and anomalous to high density bodies captured by high viscosity spider bomb can reduce their overall density and viscosity, therefore handling delamination. This is our the first key point. The second is that previous studies indicate that the newer crust is difficult to melt because they think they are refractory due to the heat problem because no additional heat provided. But recently, experimental results indicate that the potassium-rich cumulates can melt under lower cholesterol conditions like this temperature and pressure conditions, and can produce intermediate to phasic potassium melts. This is the experimental result. The key point 3 is that the remelt of cumulate can generate abundant rather than limited phasic melts, like proposed previously. As we know, previously indicates proposed that the melt, colossal melting, can partial melting just like produce very limited phasic melt. But if we can consider the events occurred in collision zone, multiple phases of mafic magmatism during syncollision and post-collision, which are induced by slab rollback and break off. This magma provides additional heat input for cumulative melting, so there is low heat problem. If the thickness of cumulates is very large in long-lived magmatism, so the volume of phasic melts produced by the melting of cumulates would be very large. The fourth point is that the potassium-rich phasic magmatism, which developed during continental collision, formed by the remelting of potassium-rich cumulates, rather than by sediment import and colossal contamination. This is proposed by the strontium and lithium and lead isotopes previously. But if we consider if we see the compilation or met inclusion compilation from continental arc, we can see that the mafic, ultramafic cumulate and the non-cumulate in the continental arc are dominated by potassium-rich composition. If this composition melt, it can produce potassium-rich felsic melts. So, accumulating for cluster preservation, we have sampled very many samples from the Ganges basilis. The key finding is that during the pre-collision, it is dominated by fractional crystallization to produce Hopland-rich cumulate and medium potassium calc-like silt from the water-rich pre-emitting magma. During synchronization and post-collision, it is dominated by partial melting and magma mixing. Okay, so we also find a combinational shift at about 70 million years. This shift is co-occurring with the change of India-Asian convergence rate. So we think this rift from previously middle potassium to high potassium is caused by the remelting, accumulating, or accumulate. Our accumulating hypothesis can be tested in other collisional zones like Appalachia and British Caledonia and Western and Eastern Queensland. So we think accumulating is an important process for the computational metering of continental crust and its long-term preservation in collisional zone. Accumulating for Earth's habitability. The first is like a hot pot in Sichuan. The breakdown of major rock-forming minerals will produce potassium-rich felsic rocks. It provides the physical platform for life. The second is the magma's fractional sulfide at the base of the continental crust from sulfide-rich cumulates. This cumulates, decomposition of this cumulates will release copper-rich release all from melts, so provide the mineral demand for our human. The third is the minerals, the breakdown of the minerals like barite and hoplite will release water and phloem. This will influence the climate and the environment. Thank you all.
Thank you very much. We have a common discussion after the first few talks, so I would immediately like to invite our next presenter, which is Dr. Yashin Hu from the Southern University of Science and Technology.
Hello, everyone. Thank you thank the organizer for the invitation, and thank you for listening to my talk. I'm a geodynamicist, so mostly my part is the part of my work. The presentation is about the force that drives the Indian-Eurasia collision. So how to? Oh, next slide here. Okay. So people here all agree that Tibet is very important because it shaped the topography, the climate, and the biodiversity, and so on, right? So, but in the field of geodynamics, there's one remaining question, that is, what is driving the Indian-Eurasia collision? What drives the uplift of the Tibet? So a very simple gravitational potential energy analysis shows that the deviatoric stress generated by this high Tibetan plateau is very strong. It resists collision, and it's far exceeding the ridge push force here. As shown in this figure, the deviatoric stress of GPE of the Tibet is very large, but the ridge push is only this large. So there's a force deficit something is driving the Indian-Eurasia collision. So there have been many hypotheses. For example, the Indian slab maybe have driving the Indian-Eurasia collision, or the basal mantle drag because of large-scale mantle convection, or there's also some refined models. For example, the combination of the mantle convection with a step in the lithosphere thickness. And of course, there are also people proposing that the Sumatra-Java slab pole is driving the Indian-Eurasia collision. It's an external force away from this cross-section. So the question is why it is so difficult to solve this problem. Because two reasons. First, it's very multi-scale, because we know the net slab pole strongly depends on the viscosity of the subduction channel, but the subduction channel is very thin. It's about 1 kilometer, and the viscosity is very low. It's about 6 orders reduction compared to the slab. Another point is a very non-linearity of the rheology. For example, if you look at the mantle viscosity, you can see here some part of the viscosity is very low, but some part is very strong. So it's strain rate dependent. So this results in a very significant computational challenge. And of course, if we want to analyze the Tibet and the Eurasia collision, we need a global model, so the force can be accurately generated. So there are some issues, there are some attempts in earlier models to solve this problem. For example, including Becker and China, they use global models, but there are clearly issues. For example, they have very wide weak zones, and the slab is not even attached to the surface plate, so there's no slab pole. There are also some more finer models, for example, from Cortes and Tackley, but the problem is the subducting channel is still too strong. The viscosity here is too strong, so the subducting plate and the overriding plate cannot be fully decoupled. So the slab pole force is not accurately generated. So we use this code called RIA. It's developed in 2010, but it's keep refining until recently. So the strength of this model is it uses adaptive mesh refinement, so the maximum resolution is about 1 kilometer. And we can use a lot of CPU cores. It is scalable to 1 million cores. And we also use nonlinear mantle rheology. So for example, in the subduction channel, so the viscosity can be fully resolved in these models. So we can fully simulate the slab pole force. So we have used this model and using the adjoint model to fit the present day plate motion, and it yields a decent fit. And we also found that the subduction channel have different strengths, as highlighted by this color. So that means the viscosity in the subduction channel is very important. Now we also used this model to study the Pacific plate motion change. And because we have resolved the plate subduction zone, the structure, the mechanics very well, so we can see that the detachment of this small slab pole can cause a significant change in the Pacific plate motion at 47 million years ago. It may account for the Hawaiian Emperor Band. So now we use this model to study the Indian-Eurasia collision. One uncertainty in this region is the slab structure. We consider a flat slab, and we also consider a relatively steep slab in India. And we have designed several models, but by varying the viscosity of the weak zone, the subduction channel, and we also vary the slab structure, and we also vary the viscosity of the lower mantle to generate different strengths of basal drags. Overall, we can see that model 1 is a reference model, and model 2 and model 3 tests the Tibetan slab pole, and model 4 tests the Sumatra-Java slab pole. Model 5 and 6, we test the basal drag. So there's a result. So at the first glance, you can see most of the models have a good fit to the plate motion, actually, yeah. Including model 1, model 2, they all look very good. And if you zoom into this Indo-Australia region, and you can see that we have got this force. From model 1, 2, 3, we can see the Tibet slab pole increases, right? And then we can also see the predictive arrows, the red arrows, is getting larger. Larger than the observations, the black arrows. So, and we can compare the Sumatra force. Yeah, we tune the parameter. We can see the Sumatra force changed, and we also see the basal drag highlighted by the background color also changed. But we can see there's a decent fit in the plate motion from model 1, 4, 5, 6, right? So this means if you only use plate motion as constraints, then you cannot get a unique solution. So what we do is we look at the intraplate stress. I mean, this is very interesting. We found that in the Australia plate, we found a neutral surface. North of this neutral surface is dominated by compressional force along this direction. But south of this neutral surface, then it is extension. It's just like a bending beam. Half is compression, half is dominated by extension. So we use this surface as a diagnostic for these different models. Then we found that the best fit model is actually model 1. This is the best fit model. And we see the fit to the stress is very good here. I mean, red is bad, blue is good. So overall, this model is very good. So if we analyze this model, we can see that the basal drag is overall actually negative. But beneath the India-Eurasia, the basal drag is positive. But the main driving force is actually Sumatra-Java slab pull from this subduction zone. There's also some stress. You can see once you have a slab pull here, you will the Capricorn plate will generate some compressional force here, so push the Indian plate northward. So overall, we think that the main driving force of the India-Eurasia collision is from the Sumatra-Java slab pull. That means you need extra force to drive the Tibet uplift. So we think Iranian plateau may not go as large as the Tibet plateau. So what's next? We hope to build a very Earth-like models. We have a very research briefing to express this idea. We want to have very fine models, and we want to study the intraplate deformation so that we can better constrain the forces. Okay, thank you.
With the sound of the tone, every speaker was able to terminate their presentation. Awesome, thank you very much. I would like to have the next speaker up here, Dr. Prayogo from the Chinese Academy of Sciences. And the floor is yours.
Okay, good afternoon everyone. First let me introduce, my name is Angga. I belong to Indonesia Agency of Meteorology, Climatology and Geophysics, and also a researcher at Institute of Geology and Geophysics, Chinese Academy of Science. Previously we have talked about the continental collision by previous speaker. So I also will talk about how the transformation from the subduction transformation from the west to east, so we can have the research to revealing the oceanic to continental transition beneath the Sunda Banda arc using the finite frequency tomography. First, I want to give thank you for our collaborator team. We have several great people from several institutions in China, in Indonesia, and also in Australia. First, why Sunda Banda? Sunda Banda relate to our workshop topic. This region is the final segment of the Tethyan subduction where the ocean meet the continent collision. And this region also one of the most hazardous subduction zones, including the volcano, earthquake, and another hazard, natural hazard in this region. And another question is why the 3D slab from the previously research still have mystery. So we need to explore more about the slab situation, especially in oceanic to subduction, oceanic to continental zone in Sunda Banda Art. So we have three important questions. First, how does the slab geometry change or have evolution from west to east? Does the slab is flattened, have the stagnation, or the next is the tearing? And the third is how do the process drive the surface feature like the arc jump in wetter region? We can see the detail about the wetter region in next slide. This is our data how to process all of waveform to do the finite frequency tomography. We have more than 700 broadband stations across the Southeast Asia, and also we have also another station in the southern part of the subduction line. So we have two big parts of the the station from the south from Australia and then north from the South Asia, especially in Indonesia. Our method using the multi-frequency approach, we also using the crystal 1.0 to do the crystal correction. And next we also using the advanced finite frequency tomography for the better resolution. Just in our opinion, the finite frequency maybe the first time we used to analyze the deep mantle and beneath the Indonesia region. Another information is we also using the teleseismic earthquake around the study region. Yes, our study region in this blue box. So we have teleseismic events around the study region from the 30 to 95. Our model, we do the several resolution tests. I can show you. The first is the recovery test. So from this recovery test, we can clearly recover the upper mantle while the long wavelength feature remain resolvable in the mantle transition zone. So from this recovery test, our model is reliably to have interpretation. This is our first finding from the slab morphology. We can view from the depth slice. We do the several depth slice. So from these three depth for the upper mantle, middle, and for the depth to 420, we have a conclusion that the anomalies are clearly recovered in the upper mantle. And also we can see the tail of the slab pattern from the west to east. And then our second finding is from the cross-section view. In the west, we can see that our model is show that the slab is strong. The slab is steep in the west region, especially in Sumatra. We can see this is the Sumatra region, and then the slab is steep in the west parts, and the eastern part in this region, this is from Banda region, this is Timor, and then around the Seram Islands here, we can see that the slab is flattening as continent approach. And then the last, we also do the profiling from west to east. We can see that the anomaly is diffuse. They have the stagnant slab aligning with the wetter arc jump. So from these two models, from the depth view and also from the vertical view, we have synthesized all of our models, so we can image how the slab change from the west to east. This is our update result. So from the from this 3D model, we can imagine this point of view is from the north side. This is Sumatra, so the slope is so steep, and then the Java starting to flatten and then fragmented at under the Banda Timor region. Yeah, we can also synthesize this all model to 3D formats, how the oceanic subduction and then the transition of the continental subduction change in under the Wetar region. Wetar is in the eastern part of the East Nusa Tenggara in southern part of Banda. We can see this, and this slab starting to fragmented to so many complex situation in this region. That's why if we can see previously in the maps, we can see that the Wetar in Wetar region, the coastal lines is suddenly change direction from north to from south to north, following by the surface pattern for the volcano. We can I mark it in this line in the magenta line. This is the volcano pattern. So the volcano from the west, and then in this region the arc is jumped to the north part of Banda Timor. So our implication is, and we need to take away is, as our conclusion is, first, the high resolution 3D view of the oceanic to continental transition reveals that the slope is steep, then continue to flat, and then the last in the east is fragmented transition. The main factor is the buoyancy. This is the primary control of the slab morphology. And then the slab tearing at depth directly causes the Wetar arc jump at the surface. And the last, active analog for early continental collision in final Tethyan system. Thank you.
And before we have our little break for discussions, we go to the final presentation of this first block of talks, and I invite Professor Bo Zhang from Peking University.
Thank you. Thank you very much. So, let me see. Thank you. So today's talk, I focus on the seismic anisotropy and the rheology decoupling of the crust and the mantle in the East Himalayan taxi. So let me see. I'm Boran from Peking University. So just now, some geologists very interested in the Himalayan origin belt. So I just focus on is very strange local syntaxes. There are two syntaxes is very strange. There's the west one and the east one. The East Himalayan syntaxy is very local extreme topography and tectonics at the East Himalayan syntaxy. So why it is very extreme originaceous? So let me see. It's around the East Himalayan syntaxy. We can see some very strange GPS rotation around the East Himalayan syntaxy, and even the very huge stratigraphic fault around the East Himalayan syntaxy also. So depends the surface tectonics and the crust tectonics. Some geologists think about some intrusion tectonics and erosion tectonics and the inter-channel flow. It's very strange. Why is East Himalayan syntaxy is a local, very small tectonics. However, it controls very big tectonics models. So it's Professor Dings suggests a very good field works-based structures in the East Himalayan syntaxy, and it depends his publication. We find it's the model pressure high-grade metamorphisms almost at the 11 million years, And even in the central part, we can find some argin data by the diorite, and indicate a very quick extrusion and cooling at the later Miocene. So, and then Professor Ding suggesting some very high-grade granulite belt unit extruded and in the core of the syntaxins, and depends on his tectonics interpretation. It's almost the horizontal tectonics controls East Himalayan syntaxis structures and structure patterns and even the metamorphism extrusion. So let me see some current publication. So some very quick extrusion and quick exhumation at the core of these syntaxins compared to the around regions. So, and even we can find a very quick erosion, almost at beyond to the 6 millimeter per year, and exhumation rate almost get to the 2.5 millimeter per year. So I asked a very important, we want to know what the deep dynamics process has controls extremely rapid uplift and some deintonation and distinct crust structures in these syntaxins. It's local syntaxins. So let me see some geophysical data. Today, most of the posters and some presentations show some deeper tectonic structures. Let me see, in these regions, depends on the geophysical data, we find very interesting some post-delamination and tectonic sinking beneath these regions. Let me see some very low pulsation rate beneath the East Himalayan syntaxy, and even some systematic northward dipping of the moho levels. So some Model B, from the geophysical data, we can find some very strange, let me see, some moho levels. It's the dome-like moho levels beneath the East Himalayan syntaxy. And another indicates some partial melt occurred in the middle and the lower crust beneath these syntaxins. So both another evidence, I show it just a little bit. The low velocity zones beneath the East Himalayan syntaxy, and even some MT data indicate some very, very large scales, steeply dipping conductive zones beneath these syntaxins. So, and almost these geophysical data indicate some vertical tectonics control and affect these syntaxins. And so, let me give some inward conclusions. Is in this region, small region, we can find a significant crust sinking and moho upward, and then is the dome-like shapes beneath the syntaxins, and the lithosphere and ionosphere RAB is discontinent, and we can get some lower shear wave velocities and low resistivity zones, and even some VPVS radius. So it's very strange. So, and let's some geologists understand. So now is the geophysical data just the response? It's not the control factors. In fact, what is the control factors? It's the rock. Rock is the real control factors. The rock cannot treat us. So, and the rocks is solid, is the minerals, all kinds of minerals in the rocks. If he experience the solid ductive deformation in different temperature and pressures, maybe can get some fabrics. So, for example, the minerals CPO patterns. So these CPO patterns can control and affect some seismic features, and some P waves and some S waves is also. So it's quick. So we can use the high pressure experiment method to check the seismic patterns. Also, we can use some geodesy method to get it. For example, the fabrics-based calculate method to determine the seismic features, VPVS and surface viscic. So it's we use the data supported by the EBSD and some TMRS data. So as simple as that. And so let me check what kind of the rock in the these syntaxes. If we go outside, we can find many atmosphere, and with variance melting frictions, look like this is atmosphere, is a magmatized atmosphere. So around and in the core of the syntaxes, outside atmosphere with almost some melting fractions beyond to the 15 to 17%. So I take the very respective atypical samples, like this is the magmatized afibrillite, and we check some volumes of frictions, and we check what kind of the minerals deformation in the inside, and we get the fabrics, so we can get very important seismic porters. We can see the afibrillite leucosome volumes, if it's below the 10%, we get the shear wave anisotropy is almost 15 to 14%. It's very important data to indicate we compared with some another publications is very similar. So I got the conclusions. Afibrillite layers can contribute almost 15% S-wave anisotropy. It indicates our middle or lower crust compared by some ionosphere layers. So, and we can compare it with the ionosphere layers with the upper unit and lower unit. We can find this, the velocity, S shear velocity, and even the P velocity is very totally different from the upper unit and the lower unit. So we conclude it's very important to decouple layers. So, and then it's very important we find some very important thing is some magmatite afibrillite also contribute almost 9% to 20%, 12% another share of the shear velocity. Is very important because if the atmosphere layers with the partial melting, maybe it's contribute some anisotropy of the in the crust. So let me see. So another data is the delete time. We can also indicate the F layers delete time almost 0.2788%. So let me see. And so in some physical data, receiver function data get some delete time from the shear waves almost 0.45 and almost to the 0.9. So only the lower and the middle crust dominated by the little atmosphere or some atmospheres with the various metals, we can get this delete time. So we can, it's our conclusion. So we can say if we get this difficile data, we can contribute factors is the atmosphere's layers with the various metals frictions in the middle or lower clusters. So so we give some another interpretation in these regions. During the retrograde discrimination of this syntaxy, maybe some partial melting contribute very much is, for example, the buoyancy uplift the basement, let some rock uplift quickly during the last time. So it's models. So I give a very simple calculation. If the melting get to the 1%, we can get some buoyancy pressure almost 20 million per PA. If the melting increased quickly, get to the 10%, we can get the buoyancy pressure is very almost 200 MA%. Or contributes tectonics almost 14%. It's very important. Another thing we should know, if the melting increased, so maybe the host rock strength will decrease quickly, and even some velocity decrease also. So indicate if our atmosphere in the lower and the middle cluster with various meltings maybe indicate some atmosphere layers where some rheology's weakness occur very quickly. So it's our conclusion. I think here. I stop here. Thank you very much.
Thank you very much for all these presentations in the first round of this afternoon session. And I would like to open the room for questions. If there was no immediate one, I would start potentially. Coming back to the first talks that we've heard, you presented us a nice example of where the potential stress would come from. That is the slab that is actually facilitating convergence. And then we heard about slabs being deformed and maybe stalling and maybe having different ways of going down. Is that something that your whole Earth model actually looks into, that the downgoing slabs may actually change their force difference depending on whether they're steep, flat, or actually starting to stall? Is that something that the model incorporates?
Yeah, you mean, are you talking about the slab morphology beneath Tibet, right?
Well, or in wherever you want it to be. You said it's the downgoing slab in the
Sumatra
yes.
drives. Yeah.
Does the geometry of the slab, does that factor into your calculation?
Yeah, beneath Sumatra, the slab geometry is relatively known because we have the seismology slab 2 model. The slab 2 model delineates the slab surface structure. I mean, large uncertainty comes from the slab structure beneath the Tibet. Yeah, because of data coverage of seismological data, right? So whether it's very flat or it's steepening, it actually changes the force. If it's a very nicely curved, deep subduction, the slab pull force will be large. But if it's a flat slab, yeah, you know, the decomposition of the force, the slab pull will be small. Yeah. So we think beneath Tibet, the slab pull is actually small. It does not contribute much, yeah, from our modeling. Yeah. Thank you. Apple.
The question is, what makes the shape of the Emperor seamount bend when you look at your model?
Oh, okay. Yeah. Actually, I have done, recent years, we've done a couple of works on this. We think there's some intra-oceanic subduction in North Pacific. So we call it a Kronosky subduction. The Pacific is subducting beneath the Kronosky plate. So it's a northward dipping subduction zone. This provides the force for the Pacific plate moving northward. But at 47 million years ago, the slab detached, maybe because of the collision of the Hawaiian plume head with the subduction zone. The slab detached, then it shifted. So there's some like geological evidence and geophysical evidence in there.
Yeah. A question to Dr. Priego, if I may. So, from what I understood from your presentations, you claim that the western part of Sunda subduction zone has steeper slab angle and it's gradually flattened toward the eastern parts, right, toward the Flores Sea and Banda Sea. But why do we find more deep earthquakes in the western part of Sunda subduction zone than the one in the eastern part? Because for my current understanding, it should be the other way around. Thank you.
So he says you have a steep slab and a shallow slab, but why do you get the deep earthquakes where the slab is shallow? He would expect it to be different.
Okay, thank you for the questions. As far I can explain is about the for the steep part in the west. For the steep part from the west, the earthquake is more in the deep epicenter. And about the flattened slab at the east part is more higher, more complexity, more various the earthquake hypocenter. Is that do you mean? Sorry.
I mean, based on our data, we find more deep earthquakes in eastern part of Sunda subduction zone in Florida Sea and in Banda Sea. But from your presentation, I learned that the slab angle in the western part is steeper than the one in eastern part. So from my current understanding, it should be the other way, and that is why it interests me to know what causes such phenomenon. So maybe you have the explanations why it can be like that.
Okay. Actually, we haven't seen first. Okay. Okay, thank you. Actually, we haven't see the local earthquake for our analysis. So how we can determine the possibility earthquake at the eastern part is analytically is more complex situation in the eastern part. So we need to explore more for each part of maybe like in the Sulawesi or in the Banda region, where is the slab position and more various slabs. So yeah, I think we have to explore more about this situation. But actually, the first one, in my opinion, is because in the eastern part is more complex subduction structure. I think like that. Thank you.
Sounds like a topic that could be deepened after the session. There was a question in the front row.
My question is addressed to the first speaker about hornblendites. In Kohistan Arc, where I have been working for ages, we have been discovering more and more occurrences of hornblendites. One of the body which we have studied very carefully, there the hornblendites are associated with pyroxenites and peridotites, but we feel that they are not from a single process. Some of them appear to be cumulates. In some of the rocks, hornblende seems to have been imposed on earlier ultramafic rocks, pyroxenites, or even on gabbros. So maybe over there, there has been one activity was magmatic, the other activity was somehow hydrothermal or whatever, but fluid was made available. And then the last activity was that we have gabbros in which hornblendite dikes are seen, and we believe that those gabbros were affected during metamorphism by hydrothermal fluid. So the story is very complicated. So I wanted to see if you can comment what you have seen.
My impression was about gabbroic rocks and hornblende-rich cumulates, whether fluids were involved. What he has seen is that these hornblende-rich rocks seem to be intruding gabbroic rocks, and it was more about what is early magmatism and what could be fluid addition in terms of melting.
Yeah, the processes and the composition are very complicated in the lower class section, but the hornblendite-rich gabbroic rocks are easy to melt. Compared to the hornblendite, compared to hornblendite, required a very high temperature to produce. Yeah. Okay, thank you.
We have an online question here. And the question is, how good is the agreement between the seismicity map comparing the slab pattern of your study? I think that is probably what we've just discussed, the relationship between the geometry of the plate and the seismicity. I think this is something that needs further investigation. Where is the locus of the seismicity and where is the downgoing slab?
Okay, I'm sorry. Can you make it clear?
No, I can't. It disappeared. But I think it's the same question that we just had. And can you give me the second one? The second question was for a different speaker. I apologize. It was about the back thrusting. And the question here was whether similar patterns of back thrusts can be found in different or in similar localities. But that was...
Let's see first.
Okay.
Okay, thank you for the question. First is how good the agreement between the seismicity maps comparing the slab pattern of of my study. Okay, this is one. Maybe this will be one of my my notes. But initially, comparing the slab pattern in our study is confirmed that the situation and the complex situation make the there is slab pulls from south to north. This dynamic situation make the earthquake will be should be more suitable. The location, the maps, the earthquake hypocenter will be more complex near the slab line. And then the second. Okay, thank you.
So then we change chairs and continue the second part.
Okay, let's move to next half session. The first speaker will be Professor Shaofeng Liu from China University of Geosciences. Let's welcome.
Next slide. Nothing. Please show my PowerPoint. Hello, everyone. I will give my talk, but the talk is not show off. Okay, just wait a minute. Okay. The title of my talk is The Dynamics of the Large Mantle Wedge System in the East Asia in 4 dimensions. I'm from China University of Geosciences. So, you know, Western and Eastern Asia underwent a very, very complex tectonic interaction among the Eurasia, Pacific, Philippine Sea plate, and Australian plate and Indian plate. So formed a typical triple junction, which connected with the Izu-Boni Mariana Trench and the Japan Trench and the Nankai-Ryukyu Trench. This is a triple junction. There's a second character. The third character formed lots of banding subduction zone. The big banding subduction zone is the Sanda Trench. And also there's a Mariana, and also here many banding subduction zone. From the mantle structure in the East Asia, the big character is a large horizontal slab within the mantle transition zone. Within the transition zone, there's a horizontal slab. We call the large mantle wedge. But this horizontal slab not not continuous, it's segmented. But in the Southeast Asia, a large mantle wedge now is avalanche, is sinking down. So penetrated through the mantle. So now, our question, I should ask a question. The present day configuration of a subducted slab is a mantle revealed by the seismic tomography. It records the tectonic evolution through geological time. This is the present day situation, but recorded the geological time, recorded the tectonic evolution of geological time. So our question is, what drove the evolution of this horizontal slab? That is say large mantle wedge. How is it linked to the surface, plate tectonics and deformation and even topography? But today I do not talk about this, more topography because of time. So to answer this question, we implemented a deforming plate reconstruction for the whole, almost the whole East Asia. And recently I almost finished the Tibetan Plateau deformation reconstruction since 60 million years. So from this figure, we can see. So this part, Tibetan Plateau, mostly shortening, but after 15 million years, so there's some extension. So you can see here there's extension. East Asia, mostly is extension during the Cenozoic. But the southeastern part, before the 24 million years, is extension. But afterwards, mostly some part is shortening. This is the character of the deformation. So second, we should build up the model. So we created more than 26 global mantle flow model. We call the cases 1, 2, 3 series, based on the 3 reconstructed plate models. There's a plate model 1, plate model 2, the plate model 3. And also we consider the variation of the physical properties in the mantle layers. So according to the velocity in the different layer. So we built so many models, but we should evaluate the flow model. So by comparing the model, the present day mantle architecture with the seismic tomography, and we also compare the dynamic subsidence compared to the observed residual subsidence to see which model is the best. So that's a comparative result. Compare the model structure, mantle structure, and with the seismic tomography picture. So we find the case 3-2 is the best. We also compare this one, dynamic topography, and observe the residual subsidence. So we also find the case 3-2 is the best one. So finally, we get this model. So we use case 3-2 to do our modeling. This is the modeling result. This is for the section 3. From this, you can clearly see at the beginning, about 70 million years, there's a rollback subduction. And then we can get the horizontal, we get the large mantle wedge. But in the Southeast Asia, at the beginning, probably about 26 million years, we got the large mantle wedge. But afterwards, this large mantle wedge sinking down. That is say to avalanche, because of the continental collision. So this is for other places, so I do not show the detail. For example, this This is the Mariana arc shape, so you can get the horizontal subduction. And also this is a Ryukyu, this section. Also we can get the horizontal subduction within the transition zone. So our result also compared to the present day tomography shows very, very fit. I think this is a good result. So now we can do some discussion. So this is a modeled movement field. From this figure, we can clearly see from 60 to 50 billion years, Indo-Eurasia collision. This part begin to collision. But this part, southeastern part, Sunda-Java subduction zone, roll back. So the material mostly moved to the south. From the 50 billion years, Philippine Sea plate northward movement, blocking the material. So move to the north, and so the southeast escape in the southeastern Asia. So and gradually form the arc shape. So this period of time is this subduction zone mostly roll back. And during about after 24 million years, the exact time I do not really clear. The Australian plate moved to the north. Australian plate, there's occurred the continental margin with the arc, the collision. So this collision make the arc shape very clear. The arc continental collision. So drove the Sunda-Java forward subduction. After that period of time, after 24 million years, the forward subduction. So from the structure, Southeast Asia, the structure, before the 24 million years, the basin moves to the extension. After 24 million years, so the basin is post-rift subsidence, and sometimes some places also we can get the compression. So in this area, we also can see, because the material migrated, escaped to the east and the southeast, and also drove this arc shape along this place and the center. So this is our conclusion. Thank you.
Thank you very much, Professor Liu. The next speaker will be Dr. Lei Yang. Please. Let's welcome.
Hello everyone, this is Lei Yang from Institute of Geology and Geophysics, Chinese Academy of Sciences. I'm very happy to come here and present some of our very recent results regarding the crustal heterogeneity along the Sunda-Jubanda arc. And this is a collaborative work together between the IGGCS and BMKG. I'll go for 5 parts, and first the background. So the Sunda plate has a very complicated tectonic setting relative to the Sunda plate. Indo-Australian plate moves toward the northeast, the Philippine Sea plate moves toward northwest, and the Caroline plate exhibits a similar but relative motion to Philippine Sea plate due to the spreading of the Ayu Trough. In the western part, Indo-Australian plates subducts beneath the island of Sumatra obliquely, and in the middle, the subduction is almost orthogonal. And at east, the subduction transitions to collision at Timor Trough and at Salem Trough. So this kind of arc-continental collision is also accommodated by the back arc thrust, such as the Flores thrust and the Whiter thrust. The continental part of the stand-up plate grew largely by the closure of several tithing oceans and by addition of the material from Pacific margin. The western core of the stand-up plate was assembled from the Indochina East Malaya block and Cebu Masu block that separated from the Gondwana in the Paleozoic. And since after that, the continental blocks separated from the Gondwana and moved towards north and formed the current Borneo, Java, and Sulawesi. Due to the very complicated tectonic setting of Sunda land, Indonesia is faced with severe natural hazards such as earthquakes, tsunami, volcanoes, and the better understanding of the geological context and the subsurface structure is crucial to the mitigation of the natural hazards. So for this research, we are more focused on the crustal scale structure along the Sunda to Banda arc. So I'll quickly go through the methodology part. We totally utilized 667 broadband seismic stations across the Sunda plate and its adjacent region to perform research function and H-kappa stacking. We selected events larger than magnitude 5.0 with an epicentral distance of 30 to 95 degrees from 2021 to 2023. We calculate the radial research function and applied common conversion point stacking method to migrate from the time domain to depth domain. We also applied the H-kappa C method to calculate the crustal thickness and the VPVS ratio. We'll select the data with very strict quality control so that our results are very reliable. Let's see some results. So we first present the research function imaging results for the Moho geometry, and the entire arc is divided into three parts: profile AB for the island of Sumatra, BC for Java, and CD for the rest. We can see a very segmented pattern of the Moho discontinuity. So the positive phase signals represent the velocity increasing interfaces, which might relate to the Moho discontinuity, the base of the sedimentary layer, or their multiple reflections. And the negative phase signals related to the velocity decreasing interfaces, which in the crust might indicate the the top boundary of the low velocity zones. So we can see that in profile AB, there is an abrupt crustal thinning from 50 kilometers to maybe 30 kilometers beneath Toba supervolcano. Additional offsets are below Merapi and this volcano. And from profile BC, we can see an ambiguous Moho signals from here to here, but there is an abrupt Moho drop right here. And along profile CD, we can see a contrasting Moho depths in the west and the east. We also, so here show the H-kappa stacking results, and based on these H-kappa results, we can divide the whole region into 4 groups. So from here to the central Sumatra, there's a medium to low VPVS ratio, and from central Sumatra to east Java, there is a high VPVS ratio, and from the island of Bali to Sumbawa, there is a higher VPVS ratio, and for the rest, there is a low VPVS ratio. So there is slab tearing right below the slab, right below this Moho segmentation beneath the Toba supervolcano, and there is a slab window right below this this Moho drop, which indicates that the Moho geometry is influenced by the slab geometry. And the contrasting Moho in the west and eastern part
corresponds to the oceanic to continental conversion of the subducting slab, which indicate that the crustal structure is influenced by the subducting process. We also underline the factors that might influence the crustal heterogeneity. We first consider the influence from the arc volcanism. As we all know that the active arc volcanism might lead to high VP-VS ratio due to the high melting fraction. And we do observe that around some volcanoes such as the Merapi and the Tambora, the VP-VS ratio is larger. And we can also observe the low velocity zones above the Mohor, which indicates the magma chamber. However, we also observe that beneath some volcano, the VP-VS ratio is not that high. And also the arc volcanism, the arc volcanoes are almost evenly distributed along the whole arc. So this arc volcanism cannot be used to explain this kind of crustal heterogeneity. We also consider the influence from the subduction parameters such as the subducting angles. So the subducting angles and the plate edges increases to the southeast of the arc, which might lead to higher degree dehydration compared to the subduction from the northwest of the Sumatra island. So this kind of larger amount of water might lead to the higher degree melting. But this gradual increasing subducting angles is hard to explain the distinct contrast of the VP-VS ratio in the northwest and southeast Sumatra. We also consider the other mechanism that might lead to the material exchange between the mantle and crust. So based on the plate reconstruction, it is suggested that there was a slab window migrating from the East Java to Central Sumatra during the period of 60 million years ago and 40 million years ago. Such a slab window can form between the diverging plates of the subducting active mid-ocean ridge, and above the slab window, the arc volcanism diminishes and was replaced by volcanism of the mid-ocean ridge, which leads to a more mafic composition of the upper plate and with higher VP-VS ratio in the crust. And for other regions, like here, the high VP-VS ratio might be due to the context of the intra-oceanic arc, and this part might lead to the conversion to continental subduction. I will leave my conclusions here, and with this, thank you for your attention.
Okay, thank you. The last speaker, Nava Holanyanto Doka from BMKG. Let's welcome.
Good afternoon, everybody. Thank you for having me in this international workshop. My name is Nova Dendoko. I'm from BMKG. And this time I would like to present our recent ambient noise tomography study and reservoir function studies in central Indonesia. And so the map in the right shows the study area covering two major islands, Borneo and Sulawesi. These regions have a complex tectonic story as an implication of the convergence of three major plates, Eurasia, Pacific, and Indo-Australia. Borneo is part of Sunda block, and this island is tectonically stable, while Sulawesi was assembled by the collision of multiple continental fragments, implying that Sulawesi has most active faults in central Indonesia. Borneo and Sulawesi were part of single landmass in the late Mesozoic, but were spread during the Cenozoic by rifting in the Makassar Straits. So the the objective of the studies are understanding the characteristic of crustal structure of central Indonesia using surface-based tomography. And the second is understanding mode depth variation using receiver functions. So I go to the summary. So in the summary of this book, we observe high heterogeneity velocity in these regions, prominent low velocity anomaly at depth less than 14 kilometers, indicating the broad and deep sedimentary basin beneath North Makassar Straits, and high velocity anomaly at depth 20 to 30 kilometers, indicating shallow moho beneath the North Makassar Straits, which is the thinnest crust in the study area. We also observe moho depth of 40 kilometers beneath Central Sulawesi, which is suggesting the rapid uplift and exhumation occur in these regions. And this is in the ambient noise tomography processing workflow. This is normal workflow for ambient noise tomography. We collect continuous seismic data from 108 seismic station. We use noise pi to compute the waveform cross correlation and distribution curve measurements. We then provide spatial distribution of group velocity using fast matching surface tomography, and the group velocity distribution and then invert to produce a shear wave velocity model using SURF 96. We continue vertical component. We use continuous vertical component seismic data which collected from a dense seismic network distributed in Borneo and Sulawesi. And so we go in the lab, show the cross correlation and stacking results, showing clear empirical Rayleigh Green function obtained from this study, and in the right some example of cross correlation from several stations in Borneo and Sulawesi, along with the distribution curve results. So the tomography interpretation steps were carried out by first testing the model parameters, including grid resolution test, damping smoothing test, as well as the number of iterations. So a grid size of 1 degree was chosen, providing the most optimal results covering the area from Borneo to Sulawesi. The image on the right shows the result of group velocity distribution for several periods covering the study area. And we then inverted the obtained group velocity to produce 1D shear wave velocity model at its grid point covering the study area. And to improve the model solution, the inversion process is carried out by imposing a moho depth constraint, when the moho depth constraint is obtained from class 1.0 model. So, then obtain 1D velocity model and then combine to construct 3D model, and interpolation is performed. We observe up to 1.0 km per second lateral heterogeneities as a function of depth. This result eliminates significant low and high velocity anomaly across these regions. And the prominent low velocity anomalies at shallow depths are observed, for example, in the North Makassar Straits and the Kute basins. And the rapid change of velocity in vertical direction from low to high was found in the North Makassar Strait, which we interpret as thin crust layer in this region. And the relatively high velocity in the surface were observed in several areas, such as in Central Sulawesi and Western Borneo, and this region associated with topographic elevations. Based on the velocity value, we then estimate the discontinuity profile of the sediment basement layer and the moho layer based on isovelocity, and the discontinuity profile shows the North Makassar Strait region as wide, more or less 300 kilometers, and deep basins, about 14 kilometers, indicating the existence of extensive sediment basin in these regions. And we found relatively shallow moho, about 22 kilometers in the North Makassar Straits, indicating the crustal layer in the North Makassar Strait is relatively thin. And to confirm the moho depth from a velocity model, we also conducted the receiver function study, and the receiver function signals were determined using the iterative deconvolution method in time domain. And the moho depth is calculated using the systematic search, using the moho depth and VP per PS ratio stacking. This is the data used in this receiver function study, the teleseismic wave recording with distance 30 to 90 degrees, recording at 60 permanent seismic station in Borneo and Sulawesi. And the table in the left shows the result of Moho depth calculation from seismic station in Borneo, Sulawesi, and in the right showing a map of the Moho depth distribution from this study. The interesting thing about this result is that seismic station around the North Makassar Strait show contrasting results with Eastern Borneo, tending to produce a relatively shallow moho, while in Western Sulawesi, which include the neck of Sulawesi to Western Central Sulawesi, the moho is deep. So it's clearly seen that the crust in Western Central Sulawesi is relatively thicker than in Borneo. The following is a vertical cross-section of moho depth profile and PB per PS ratio on the A axis and BB axis transects crossing Borneo and Sulawesi. The red and blue dashed line represent the sediment basement discontinuity and moho from the crust 1.0 model. The black bars with error bar indicate the moho depth and VP per PS ratio at seismic station. It can be seen that the moho depth beneath Sulawesi is more heterogeneous than beneath Borneo, especially in Central Sulawesi, where the moho in Central Sulawesi is observed to be very deep, more than 40 kilometers. The overall average moho depth in Sulawesi is deeper than in Borneo. The relationship between moho depth and elevation shows a regression line slope value of 7.7, which is much higher than the average continental crust slope with 4.45. And a higher slope in the continental crust is also found in the rift zone, which has value of 5.5. Furthermore, moho depth has a low correlation with elevation with the value of 0.28, which indicates that moho depth varies greatly compared to the elevation, indicating a complex tectonic condition in the study area. And for more detail regarding this work can be found in our publication in Geophysical Journal International and Journal of Seismology. Thank you very much.
Okay, thank you all speakers. Now it's time for discussing. Any question for the three speakers? Okay.
I have a question to Dr. Yang. Dr. Yang showed moho image for 3 profiles along the streak. For 2 streak, they are clear moho offset. For the profile AA, you showed moho offset up to 20 kilometers. You explained it's due to the geometry change of the slab. My question is that possible for the moho slab? So for the moho offset, represent the moho in different plate. For example, the moho in one part for the 55 kilometer represent the subducting Australian plate. And the shallow part of the moho represent the structure below the Sumatra Islands. Yeah.
So could I repeat your question again? So are you asking about the moho segmentation, like the segmentation beneath the Toba supervolcano or somewhere else? Could you repeat your question?
So I just think the moho offset might represent the transition of the moho between the subducting Australian plate and the overriding Sumatra Island.
So I think the transition is almost in the eastern part, from the subduction to the clearing, and
Professor Dean? Yeah.
Okay, here I have a question for Jiaxun Hu. If the subduction of India oceanic crust along the Java Sumatra is a force for keeping the India continent keeping subduction, why this mechanism cannot work well in the east side to keeping the north drift of Australia and form a plateau here?
Are you asking why the Australia plate is not?
Why this mechanism cannot work in the east side for drive the Australia plate to go to the north to make a plateau here?
Because I think the time is not enough. Maybe.
It's just working the west side. I cannot work in this side.
I think it will work similarly in the east side. But the problem is Australia and the Sonda collision occurred at 4 million years ago, as shown in your slides, right? 4 million years ago. So I think the time is not enough to build a plateau there.
Yeah. Do you think so? Do you think the India Australia is a whole regional plate, or they have many fragments in different places?
There's a lot of deformations there, but for now it is still one plate, I would say. Yeah, because there's no like fracture zones, fully developed fracture zones.
Yeah, maybe
no subduction there. Yeah,
maybe the Australia continent is big enough. Its force is small. It cannot drive this part to go further subduction.
Yeah, we can discuss later. Yeah.
Okay, thank you.
Okay, next question. Okay, please.
My question for Jianzhu Hu.
Who?
Yeah.
Yeah. Who?
As we know that the microcontinent India and Tibetan collision can trigger the tectonic extrusion or tectonic earthquake. In this case, for Indonesia, what is the tectonic implication in Indonesia regarding the tectonic extrusion in China?
Sorry, maybe you can.
Question was, what is the implication of the tectonic of the extrusion of Indochina for Indonesia? Is there a relationship between the extrusional movement and the geodynamic evolution of Indonesia?
Yeah, this is it's a related question, but I didn't model that. I think they are related according to earlier studies, because if the retreat of the Sumatra slab will enhance the rotation motion. Yeah, according to some numerical models, but I didn't model that for now. But I'm actually doing a work on Asia deformation, but I just haven't tested that. Okay, I cannot answer your question for now. Yeah.
Is it true the Myanmar earthquake in March 2025 any relation with this tectonic extrusion?
Yeah, I have a hard time understanding you. Maybe you can discuss later, afterwards. Yeah.
Okay.
Discuss later. Okay, please. Over there. Yeah, the same introduction.
Yeah, I had a question for the last two speakers, and actually similar to Bailing's question. Usually when people see tears or offsets in Moho, it's about 2 or 3 kilometers, pretty small. But the last two talks had offsets of maybe 10 or 20 kilometers, which to me seems very huge for just as, over a short distance for the MOHO to be offset over 10 kilometers. I was just asking, is that a reasonable thing, or what kind of physical process can cause such a huge offset in the MOHO over such a short distance?
You talk about the offset is generally very thin, very thin, but you said that it's very thin.
Yeah, I cannot hear clearly what the point of the questions. Yeah, sorry, can you repeat it because the sound is not,
It
not very clear.
It seems unusual to me.
Yeah. Okay. The question is the depth of the MOHO. The depth of the MOHO in Borneo or in Sulawesi?
So usually when people see offset of MOHO, it's maybe 2 or 3 kilometers, not, sort of small. And I've never seen offset of 10 or 20 kilometers like you.
You were showing large offsets of the MOHO, yeah, over short distance. And he said, typically, I've only seen small differences. Is it possible that the MOHO changes by 10 kilometers over a short distance?
Yeah. Okay. That's interesting questions. So we need to check it. Yeah. But I think the limitation of the data and the seismic station, the quality of seismic station probably influence the receiver functions processing, but yeah, I think we need to check again in these results. Thank you, Professor.
So could I also answer your question? So as our results show that beneath the MOHO, like the MOHO discontinuity segmentation, we can observe the slab tearing as well as the slab window beneath it. So this very complicated tectonic set, the deeper part, might be responsible for this MOHO jump or MOHO drop. And also in the eastern part of the arc, we observe the MOHO depth contrast due to the conversion from the oceanic to continental subduction beneath it. So the oceanic subduction converts to the continental subduction because the continental subduction can be lighter than the oceanic subduction. So we have some higher, thinning crustal depths in the east part. And also, I just recall the question from Professor Bailing. Are you asking about the whether part of our MOHO depth, MOHO is from the subducting slab? Is that your question? So I think right below the Sunda arc, the island of Sumatra, the arc, the MOHO depth beneath the MOHO is much deeper, around 100 kilometers. So we think that our 40 kilometers depth MOHO shouldn't correspond to the MOHO discontinuity from the subducting slab. So yeah.
Okay, so for example, the tear is 20 kilometers underneath. It's a very vertical distance on the tear. Could be 10 or 20 kilometers.
So Sunderland, lots of the rift basin extension. So if the extension, lots of rift basin, because of extension, so MOHO probably thinning. Lithosphere also thinning. so make the moho uplifting, and also this area also get some compression. So some places the moho, the thickness of the cross was probably get thicker. So there's some very short upset. I think is usual, probably because of the tectonic structure.
Okay, so I think those are good answers. I just
Right?
I'm
I just a guess because I did not do the work here.
yeah, no, I'm just a little bit worried. You have such huge offset, so make sure that that's correct.
Okay, the last
Fall.
question. That young?
There's a
Yeah,
fall
please.
there.
Last question.
Okay, one quick question for Lei Yang. How did you perform the quality control of the data, and how many data is not being used after the quality control, like the percentage of data being discarded? Thank you.
The question was, after reduction of the data, how big a percentage of the data has to be discarded because it doesn't fit the quality control? And with what fraction of the data can you actually work in the end? So how much is garbage and how much is data that's being used?
It is about ambient tomography or separate.
Actually, my question was for Lei Yang.
For Lei Yang. For Lei Yang.
Sorry.
For Lei Yang.
How much of the data the raw data that you have, how big a fraction do you have to discard because it's not good, and how much can you actually keep?
So we have a very strict quality control of our data, and we also examine the the influence from the back azimuths. So we totally have more than 600 seismic stations that is used for the data processing, but at last we only keep not more than 300 stations for our receive function imaging as well as the H-kappa stacking. So almost half of that to make the results very robust. That's it. Thank you.
Very warm discussions, but the time is ended. We must stop it. Thank you all for the several speakers, including me. Thank you all. Now it is now the coffee break time. When we come back at 13:20. Okay.
Okay, once again, please give a big round of applause for the chairs and all speakers. What an outstanding discussion in this session. But now we have to break for 15 minutes, and please back into this room at 15:20. Thank you. Please enjoy your break. And once again, to all participants, we kindly invite you to visit the poster while enjoying your coffee break. So please come to the poster and visit all the poster on the left and the right side of this auditorium. Once again, we kindly invite you to visit the poster standing on the left and the right side of this auditorium. Thank you. Once again, we invite you to visit the poster. Once again, we kindly inform you that on the left, on the right, and the right side, there is a standing poster you can visit while enjoying your coffee break. Check 1, 2, 3, check. Once again, we want to inform you that on the left and the right side of this auditorium, there is a standing poster you can visit while enjoying your coffee break.
Cek 1 2 3 cek dicoba cek 1 2 3 cek 1 2 3. Cek 1 2 3 cek. Cek 1 2 3 cek.
Okay, ladies and gentlemen, welcome back to the auditorium. We begin to start our next agenda. We are now ready to resume the program with our next technical session. We now move to session 2, seismology and seismic hazard assessment. The focus of this session will be on critical topics such as earthquake monitoring, active faults, and engineering seismology. And it is our pleasure to introduce and hand over the proceeding to our distinguished session chairs for this segment. Please welcome Professor James Mori, Professor Ling Bai, and Professor Ling Chin. Once again, we kindly invite the Professor James Mori, Professor Ling Bai, and Professor Ling Chin. Okay, thank you. The session is scheduled to run from 20 until 17:10. Professor James Murray, the stage is yours.
Oh, okay, that's one. Okay. Yes. Okay. Yes, I'm the first.
Okay, well, welcome back for the next session. And just a reminder for all the speakers, I only see one speaker here, but so you have 10 minutes to talk, and there will be a bell when you have 2 minutes left. So that tells you how much time you have left. So why don't we go ahead and get started. And the first speaker is Professor Morteza Talavian. So please.
Good afternoon, everybody. So as you see from the title, this is about the benefit of earth science. We also, as a geologist, have been asked what's the use of geology for real life, and that's the topic of my talk actually. The history of building code, the way they how to build the buildings is long back. It's going to nearly 4,000 years ago, when we have the first rules about the making buildings and how they have to be safe. Then we have in Roman times, we have another regulation about the fire and also the walls and the height of the buildings and this kind of things. So it has a long history back in human life. Then in modern days, still we are improving it. These are two buildings in two different places. One is Iran, the other one is in China. As you see, they are collapsed because of the earthquake, but with different magnitude. That's actually prompting that maybe something is wrong with the building codes. And if you look at the building codes, they improve. Both China and Iran improved building code just after these two earthquakes. So that's meaning that we are learning from the earthquakes. We are every day improving ourselves, and we are adding more information to building codes. The cost for the disaster, earthquake disaster, natural disaster is increasing despite that we are getting better, we are constructing better, but the cost is increasing. The reason for that is because we are investing more in the cities, we're investing more in the industries, and also more population go to the cities. And if you compare the magnitude with the risk, which is the multiplication of the hazard and also vulnerability of the buildings and industry, you see that it doesn't matter how big the earthquake is, but it is matter that how close the earthquake is to people and to construction. So if there is an event close to big city, then the risk is much higher. So how good should be the building? How strong should be the building, and how restrict should be the building code? It's a matter of economic. If we can build the building so strong that it never collapses, well, it's very costly. So we cannot do that for any kind of building except for special buildings. On the other hand, if you could go for cheaper buildings, we are vulnerable to hazards. So we have to make balance between cost, economy, and safety. So if you look at these three buildings are three generations of building code in the BAM city, which is happened in 2003. You see the new one is not collapsed, but the old one is completely collapsed. And you clearly see the effect of building codes, how it can save the life of people in different buildings. So the way of going balance between the economy and the safety is to go through probabilistic seismic hazard assessment. And I go through this to see what's the problem with this method and what do we need more. For seismic hazard assessment, the first thing which we need is to have this curve actually, which has a slope, B value, the A value, and also the M max. These are three main parameters which we need for any source and then we go for PSHA analysis. The rest of analyze is just simple and standard. Any machine, any algorithm can do that. So there is no problem with the rest, but the important part is the beginning. So here, if you look at the data which has been used for PSHA in this part of Iran, you see that we have problem of the input data. The curve to the top, to the bottom here, as you see, this curve has limitation of data in lower magnitude, also in the upper magnitude. Often, when the earthquake is bigger, that means the return period is longer. That means we don't have sufficient instrumental data for that. We don't know history of big earthquakes, especially in the other regions in central Iran where we have longer return period. That effect is more important. So if you compare the PSHA, which is completely based on catalog to the right, with the known faults to the left, we see that they're compatible in some parts where we have had an earthquake in the last 100 years, but in other places, they are not consistent. So that means if you go just by catalog of the earthquakes, you are missing major events which may happen in future. And the problem is that we look at hazard in different ways at different parts. We have to combine different methods, different source of information to understand properly what is the hazard. Hazard is not simple structure, it's not simple phenomena, it's a mixture of different things and can be understood through different angles. And then the methodology is very, very simple. So if you understand the geometry of the faults, geometry of the source, then we know the slip rate, which is a very important parameter. Then we can go through the rest of calculation. With those equations to the right, we can so understand the A and B value and then go for PSHA analysis. So the first part is to understand the source, and for the sources, we first need to know the faults. The faults are those which are obvious on the surface. We can use satellite image, we can use topography data, we can use geological maps, but when we go for other faults which are hidden, there is more techniques which we have to use. If you look at this image, you see the red dots are those which are due to hidden faults. So we knew the source for the green dots, green events, but we didn't know the source for the red ones. So nearly half are due to hidden faults. So we have to care about the hidden faults. This is one earthquake in the Zagros, and there is one also in the central, in Tehran, the middle of the city. We have just recently reported a big hidden fault in the central part of the city. So it's important to recognize the fault. It's also important to recognize to understand the slip rate, which you can do by dating or by other methods. So the other methods include the GPS or local seismic networks, which at the same time we can understand how deep the fault is going down. It is very, very important if you look at this equation to calculate the moment, that how thick is the elastic thickness. To do that, we can either do the larger scale monitoring by crustal structure, which have two projects, one by China, one by Europe, has been done in the country, or use local seismic data, or even INSAR and waveform modeling and other techniques to understand how thick is the elastic thickness. Then the next step is, and the final step is to understand the slip rate. This is more important than other things. The slip rate is usually less than 5 millimeters in Iranian plateau, but we have to be very careful about the accuracy of that. If you use GPS, we should take into account that GPS is not always representing the slip rate, because in some parts we may have aseismic deformation, including in the Zagros. We may use INSAR also at the same time to have a general idea. And then we go for dating. This is again BAM earthquake. And we may go for dating and take sample and date, or go for trenching to find accurate information about the fault. And finally, I'll pass this one. These are the source for the whole country. nearly 550 sources has been evaluated, and as a result and PSHA analyzed, we have the final maps which are going to be the part of building code from the beginning of next year. It has been for public evaluation for a few months, so next year we will have this as a base for building new building code in Iranian plateau. And finally, if you compare it with the catalog, you see that there are places which we have information from the catalog, but there are places which information comes from the faults and slippages. Thank you.
Well, thank you. We'll have discussion after the first four talks. So the next talk will be given by Professor Ling Bai from ITP.
Good afternoon, everyone. I'm the speaker Ling Bai from ITP-CAS. The title is Make Thrust Earthquakes and Main Himalayan Thrust System. So here, the population density of the world. The large earthquakes occurred since the last century. And also the plate boundary. We can find for the Tertian tectonic domain, there are three major features: the active tectonics, high population density, and frequent large earthquakes. So earthquakes occurring in Himalaya are not as many as earthquakes in the Pacific subduction zones. However, there are lots of devastating earthquakes in Himalayan and Tibetan plateau, especially for Himalayan region. These earthquakes are associated with the main Himalayan thrust. The MHT is defined as the detachment that separates the Indian plate from the overriding Himalayan origin. Historic earthquakes since 10th century show evidence of great Himalayan earthquakes. The concept of the MHT was firstly proposed 40 years ago based on earthquakes. There are lots of earthquakes with low dipping angle toward north. Below the laser Himalaya, the depth of the MHT is about 15 kilometers. Below the Tertian Himalaya, the MHT is located about 30 kilometers. The MHT is associated with water released from the underthrusting sediment or the anisotropic shearing here. The intense microseismic activity or the high electronic conductivity. However, many scientific questions remain controversial for the megathrust earthquakes and the MHT. For example, where in 2015 there was a Nepal earthquake with magnitude 7.8. So it was on debate for the location of the aftershocks. The aftershocks may be located above the MHT or on the MHT or even below the MHT in the Indian plate. So also for the eastern Himalayan area, what's the mechanism of the large Assam earthquake was on debate. So since 10 years ago, we started the field work along the Himalayan southern Tibet. So here I will show two examples for the eastern Himalaya and the central Himalaya. For the central Himalaya, we can combine the data from China-Nepal border and also station within Nepal area. So this figure shows the along-streak variation of seismicity. For this part, there are two clusters. but for the two eastern sides, there are one earthquake cluster only. The profiles along the streak and also across the street. For the western part, there's flat and ramp flat geometry. But for the eastern part, they are very flat but deeper. So there's a long streak variation. And also, if we look at the structure, here shows high velocity but no earthquakes. Why the rupture toward the east stopped here? We explained there might be an Indian basement ridge here. It stopped the easternward propagation of the rupture. So we summarized the lateral variation of main Himalayan thrust control the rupture length of the 2015 Goha earthquake. And then for the eastern part, we deployed stations in the eastern end. The interesting thing is that earthquakes are not all very shallow as proposed by people before. So here shows an example. If a seismic station just located above the earthquake hypocenter, there's still a time delay between the S and P wave. It means this earthquake is not very shallow. We define this earthquake at a depth of 50 kilometers. So combine the receiver functions, the location of the earthquake, and the focal mechanism earthquake, we define a structure, no steeping structure represents the MHT. For the southern part, MHT is shallow, about 20 kilometers. Toward north is increased depth. So we find the flat and the ramp geometry for the MHT as well. We also look at the focal mechanisms and the stress field. We propose that both of the larger earthquakes are related to the presence of the MHT system. So other evidence shows the some earthquakes are thrust-folding earthquake, not strike-slip earthquake. If the earthquake is strike-slip fault, aftershocks should be related to the geometry of the Jiali fault, but aftershocks are very located closely to the epicenter, but not distributed along the streak. So we identified the MHT for the first time for the eastern Himalaya. It represents flat ramp geometry. So here, simply comparison of the East Himalayan region and also the Sumatra. There are some common features and also different features related to the depth of earthquakes, the geometry of the slab, and also volcanism activity. So here the summary. If we look at the keywords, we find 3,000 publications. Some are in geology, some are geophysics. So finally, multidisciplinary studies are required. Thank you much.
Okay, thank you for the talk. And we'll have questions after the last talk. And the next speaker is Professor Ling Chen from IGG, National Academy of Sciences.
Good afternoon, everyone. I'm Ling Chen from the Institute of Geology and Geophysics, Chinese Academy of Sciences. Today I will talk about our seismic constraints on the subduction dynamics and geological hazards in Sumatra. In this morning and just right now, previous talk, people talk a lot about Sumatra. Recently we went to Sumatra and did some preliminary seismic studies, collaborated with colleagues in BMKG. Today I will show you some preliminary results. So first, why we go to Sumatra? Of course, first because it has a very extremely active seismicity. Here I want to emphasize the magnitude of the earthquakes here. You know, in this century we have 6 large earthquakes with magnitude 8.5 and larger. 3 of them happened in these regions here. And also, in Sumatra, we have very intensive volcanism. There are more than 30 active volcanoes in Sumatra. The most significant one may be not an active volcano, but very influential eruption, Toba super eruption at about 74,000 years ago. There's a super eruption, the most violent in the Quaternary, called significant climate impact. So that means Sumatra is the most active subduction zone compared with other subduction zones. Another feature of Sumatra is it is a typical oblique subduction zone. As you know, all over the world, there's about 90% oblique subduction zone. So Sumatra has its global significance. For oblique subduction, you have plate convergence direction oblique to the trench. It will cause stress and strain partitioning. People believe this is oblique subduction and the active seismicity, volcanism, and tectonic magnetic processes should be closely related with each other. But what's the relationship and what's the detailed processes are not well understood. So what issues we are focusing? First, we focus on the subduction boundary structure and properties and related slab deformation to understand the oblique subduction. For subduction boundary, we first focus on the low velocity layer on the top of slab. It is commonly interpreted as the oceanic crust, subducting oceanic crust. We did detect such a layer in Sumatra, but have some different observations. We found in the northern and southern Sumatra, the low velocity layer is shallow, and the top and the bottom is parallel with each other. But in the central part, the low velocity layer is detected at a relatively large depth, and the top and the bottom are not parallel. And the interesting thing is the thickness of the low velocity layer is 10 to 14 kilometers thick, and it thickens with depth, unlike a normal oceanic crust. Based on our observations and other observations, we interpreted it consists of a normal oceanic crust and serpentinite mantle layer. It is thickened with depth because the water continuous release. If this is further confirmed, it means here you have diffuse subduction boundaries. It's related to the slab and upper mantle interaction. And you can also use earthquake sources to look at the subduction boundary. But because here we have a lack of near-field seismic observations, so previous results unable to delineate the subduction boundary. We developed a new method using teleseismic waveforms. You can see along the same profile, we have these earthquake locations, it can will constrain the geometry of the subduction boundary. And these earthquakes concentrated in the up deep and down deep belts. And combine the more results, we see the relocated medium-sized earthquakes, that means magnitude 5 to 70.2. They show the complex geometry of the subduction boundary, and it indicates slab deformation and also controls the extent of large megathrust earthquake ruptures. The big earthquake rupture area are within the up and deep, down deep seismic belt. It's very helpful for seismic hazard assessment. And the second part we concentrate on the upper plate crustal structures to understand the response to this oblique subduction. And we separate the intrinsic attenuation and the scattering attenuation because they sensitive to different structures. For example, intrinsic attenuation along this profile shows that there's a high attenuation. It's delineated multiple magma pathways, and the scattering attenuation very, very sensitive to structural heterogeneity. We see that just beneath the Great Sumatra Fault, we can see the high scattering attenuation. It shows this fault is vertically extended to at least 20 kilometer depth. We're still working on this topic. And we also look at the arch area. It's the northwest end of Sumatra. We see this area, we have very thin crust and high melt fraction in the crust. This structure and properties varies from southeast to northwest. These features are consistent with lithosphere extension and the volcanic migration associated with the Andaman Sea opening. So that means in Sumatra area, the lithosphere deformation and the volcanism are controlled not only by the oblique subduction, but also affected by the upper plate tectonic processes over a broader regions, even related to the India-Eurasia collision. And we have ongoing working on this. And in particular, we want to. It cannot work. In particular, we also install new stations, seismic stations in the outreach islands in Sumatra, and want to understand the sedimentary processes and the earthquake occurrence. This project is still ongoing, and I hope everybody who is interested in this project join us. That's all. Thanks for listening.
Okay, thank you, Professor Kang. And the next talk then is by Dr. Bagus Adi Wibowo from BMKG, please.
So maybe before I start, I would like to call fellow BMKG presenters to come forward for the next sessions, after the discussions. Thank you. So good afternoon. My name is Bagus Adi Wibowo. Today, I would like to present one of my published research, the slab morphology and associated seismics and volcanic activities beneath the Sulawesi Islands, Sulawesi. So the introduction is, so Sulawesi is quite complex. Indonesia itself is quite complex, like the previous explanations about how the complex of the tectonics is. And our the seismicity around the region is very high due to the complex interaction between these subduction zones, and then also we have these settings, and also its own complex situations within the Sulawesi itself. And then why we choose Sulawesi is because at this time the position is quite complicated, and then there is a lack of study, and then we want to focus on the lithospheric velocity structures for 300 kilometers. So how we do that? So we take the data from the NKG database from the Ignatius catalogs, and then also from the ESC, and we combine it, and then we relocate the earthquake using hypo-DD, and then we make the regional model of the tomo-DD to produce the seismic velocity model beneath the Sulawesi Islands within 300 kilometers. And we before we do the inversions, we also do the data preprocessing to make sure the quality of the data itself. And in total, from 2017 to 2022, from 137 stations, we use more than 10,000 earthquakes with the various number of the earthquakes, and this is the estimation of the rate from the earthquakes to the station. So we can see how well is the coverage of our rate from the earthquakes to the stations, and we use the magnitude from 2.5 to 7.5. And so for the initial velocity model itself, we acquired by ourselves with using VIII. And then we determine the VP/VS ratio for the data for the running for inversions. And then we do also we try to compare the research from previous research about the regions, which we try to see what is the novelties of our research. And then after doing inversion, so we acquire the velocity models for the Sulawesi Island. So we can see that here is the velocity model from the VP model and VS model after we removing area without the resolutions after doing the checkerboard test. So checkerboard test is we want to see which area have a good penetration, which area and which depth have good resolutions to be interpreted. And then so from So from this result, then we make some cross sections to show importance tectonic settings of the area. The first of all, we try to make cross sections along these regions with this which crossing from the North Sulawesi Trench to the south, crossing near the Chola volcano. So we can see that the North Sulawesi, the Selada slab or North Sulawesi Trench is subducted to the north beneath the Sulawesi arm, and confronted by deeper part of the Sangihe slab from the east. So we can see the three distributions of the earthquake itself. This is the subducting slab, and this is the small part of the Sangihe slab. And then we can see we have like low velocity model beneath the Chola Una section. Chola Una here. Chola Una is one of the only active volcano in these regions, because most of the volcanoes in the north, in the Sulawesi, is located on the north of this side of area. And then we went to the east. We have like this. We show some more complex interactions between the from the North Sulawesi slabs, and then the Sangihe slabs, and also from the Bangga Sula part. So this is we're showing the Sulawesi slabs, Bangga Sula, almost vertical in here, and then the shallower part of the Sangihe slab. This is the VP, VS. And we can see how complex is the situations. And then this one is close to the active volcano in the northern part of Sulawesi. So we can see this is the shallower part of Sangihe slab. But this we have the very very shallow syllabus slab part in here. So it's not so penetrate deeper than the western part of the syllabus slab. And we can also see very low velocity model, very slow velocity contrast beneath the active volcano in this area. And then the syllabus slab only exists until 60 kilometers. And this is also, and in this part we can see the double subductions from the Sangihe, Halmahera, and Molucca seaplate in this area. So we can see this is the dome shapes from Molucca due to the Sangihe slab and Halmahera and this Molucca collision zone here. And then going north, we see the more complex situation from the Sangihe slab, Halmahera, and Molucca sea collision zones, and we can see clearly in here. And this is the distributions of low velocity contrast beneath the Palu-Koro fault. Palu-Koro fault is famous because it caused the tsunami in 2018. That maybe in 2018 the major strike slip fault that caused a submarine landslide at this area. And then the last one is velocity. So Sulawesi is very complex. You have subductions here. You have a long strike slip fault on this area, but you also have like swarm activity in this area. But the unique thing is not that we don't have any volcanoes around this area, but we found a swarm activity in this area. So we can see the directions of the swarm activity here. And this is the simple model that we produce for the northern Sulawesi part area. So this is the syllabus part subducting from the north to the south and meet with the Banggai Sula slab that almost vertical in this area. And beneath this two, we have Sangihe Platte subducted beneath this two part and then reach more than 600 kilometers. So we can see that here our syllabus slab reached 200 kilometers. And then the Banggai Sula slab almost vertical here, and then we also see how Sangihe slab subductions is subducting beneath these two sections. So this is all from me. Thank you.
Okay, thank you for the talk. So the last 4 talks are open for questions or comments. Have any? I have a question for Professor Telmian. Where did he go? You mentioned the problem about blind thrusts in Iran. So how do you deal with them in your seismic hazard map?
Yes. Actually, first we have to recognize them, and that's the most important part. Then either we directly go and date them by if we have any river terraces or any geomorphic feature, so we can understand the slip rate, or we use regional GPS networks. There are two types of looking at them. Then the rest of things are similar to other faults.
Yeah, it's a difficult problem. I think for the Japanese hazard maps, they put in some number like 15 or 20%, maybe about 15%, they said can happen anywhere.
Yeah.
So random, and then that sort of takes care of, well, overall. But
yeah, for Japan, the problem which you have is that you have subduction deep there, and you don't know, and both sides are sea, so you cannot put GPS inside the sea. That's the problem, actually. But fortunately, we have only in the southeastern Iran subduction. The rest of the formation is continental.
okay, thank you.
Thank you. Welcome.
Any other questions or comments?
Okay, here has a question for Bagus. Based on your work, you found 2 subduction in both sides of Sulawesi Island. The west one is a Pacific plate. The east side is the Australia plate. I just wonder. There is 2 seismic zones in both sides of the Sulawesi Island?
Yes. So for the Sulawesi Island itself, is most of the activity of the earthquakes caused by the activity in the Pacific plates. But and then inside the Pacific plate, we have like small micro plate called the Pacific Sea plates in the northeast of the Sulawesi.
Okay, that's micro plates.
Yeah, and then but in also and then the microplate after the microplate, when we go to the west to the Sulawesi itself, we have like smaller subductions at the northern part of the Sulawesi itself. The younger subduction than the Philippine Sea plates, and also another double subductions in the north.
That means the North Banda Sea is begin to consume to subduction.
Yes. That's what we got from our research, Professor.
Thank you.
Thank you.
Any other questions or comments? I have maybe a funny question for Professor Cheng. So you showed Sumatra has had so many very large earthquakes in the last 20 years or so, magnitude 8s and close to 9. Some people might say, well, maybe that means the next 100 years will be relatively safe. What do you think about that?
Okay. The question is, some people said in the past 25 years there's a lot of big earthquakes, magnitude 8 to 9, and some people suggest maybe in the next 100 years will be safe. But to my understanding, in each places there's a recurrence period for large earthquakes. The occurrence of large earthquakes not only depend on the fault properties and sleep on the fault itself, but also depend on the tectonic forces or tectonic stress and strain. Because our Earth is very complicated, and the stress and strain change a lot, depend on it changes a lot and varies with time and space. We cannot predict the occurrence of big earthquakes as accurate as expected. So I cannot say that. We may need to collect more data, more sample data to do some statistical analysis and to focus on each areas which are prone to big earthquakes, to better understand the mechanism of earthquakes. After that, we may predict, we may do earthquake predictions. That's my understanding. Thank you.
Over the last 100 or 200 years, are there many big earthquakes in Sumatra?
I think Sumatra are very prone to big earthquakes. Maybe not so long we'll meet another big earthquake. That's why we come to Sumatra, to try to better understand it. Thank you.
Okay. Any other questions? Yeah.
Well, thank you. I have a question for Prof. Cheng. Based on your integrated study, you have found an interesting layer in subducting plate. I'm curious, what will happen when this layer, serpentine layer, reach the dehydration zone, where the slab start to melt? Is this layer will affect the mantle supply for the Sumatra volcanism.
You mean the serpentinite, the mantle layer, the influence of this layer to the volcanism?
Yes, in the next few million years, when it reaches the dehydration zone, is this layer will affect the mantle supply for the volcanism.
This layer, when it go down to the large depths, when the pressure and temperature increase, the serpentinite will change to another, some other mineral, and the water will release. This water may reduce the melting temperature and cause the melting of the mantle wedge. That's the source of the volcanism, magma. But it really depends on the pressure and the temperature. The pressure and temperature itself depends on the subduction angle of the slab. So along the Sumatra area, you have very complicated slab geometry. You have different depth extent of this serpentinite layer, and you have different volcanic activity. So we need to combine both seismic imaging and geochemical data together to understand this.
Thank you. Other questions or comments? We still have a few minutes. Well, how about Bai-Ling? I have a question for you then. You've studied many earthquakes all along the Himalayas, and so where do you think is, I don't want to say dangerous, but likely place for a big damaging earthquake, or maybe that would be close to some city? So where would you concentrate your efforts about studying seismic hazards along the Himalayas?
So simply, I think there are different kind of earthquakes. To the southern part of the Himalayan, there are thrust type of earthquakes, reverse faulting earthquakes. But further north, in front of the MHT, there's no large earthquakes. So further to the north, there might be some earthquake with normal faulting, but many of them are small. Never found many large earthquakes greater than 7.5 for normal faulting before.
So, pick a place. Where do you think is dangerous?
The laser Himalayan, along the laser Himalayan ramp, is the most dangerous place. I think. Yeah.
Thank you. Any other questions or comments?
What should like to explain? What role the Bangesula subduction in shaping the Sulawesi Island metamorphic?
So I mean, I think the Bangesula subduction is like because it's already vertical, so it helped the northern part of the northern part of the Sulawesi slab is uplifted. So and then it also reduced the penetrations of the Celebes slab itself. That's why we can see the limitations of the subductions of the Celebes slabs from the west to the east. We can see because the interaction between the slab is far more active in the western part of the Sulawesi slab, Celebes slab. So the syllabus slab is penetrated shallower than the syllabus part in the western part of the subductions. So it helped the uplifting the northern part of the syllabus slab itself. Yeah.
Okay, well, I think it's time to move on. Let's thank the last 4 speakers again for their good talks. So I hand the mic over to
For the next half, we have 4 speakers from BMKG and STMKG. Can you come to the stage, the next 4 speakers? Yeah. Already there? Okay. 4. Okay. So the first one will be given by Dr. Pepin, please.
Right. Hi everyone, my name is Ruben Spendi. Today I would like to talk about identification of unmapped faults associated with recent destructive earthquakes in Indonesia. Here are my outline. So as you know that Indonesia is one of the highest seismic hazards of any country in the world. The highly complex tectonic settings in this region resulting from the collision of the Indo-Australian and Sunda blocks and the interaction of the Pacific and Philippine Sea plate. That's why in the last 6 years there has been huge number of the earthquakes that had occurred in Indonesia, including 2004, the great earthquake and tsunami in West Coast Sumatra. In 2017, National Center for Earthquake Studies in Indonesia has recognized 13 megathrust segments and 295 active faults throughout Indonesia. I think this number will increase this year because we have more study about this, not only from seismology, but also from geology and geodesical approach. And the additional seismic stations operated by BMKG, in particular in the past 6 years, has greatly improved the detection of small earthquakes from previously identified faults. So here are several destructive earthquakes from previously identified faults. I have enough time to describe all of this in less than 10 minutes. So here are the magnitude 6.2 Mamuju earthquake that had occurred on 40 December 2021. This earthquake produced strong motion up to 6 on the mm scale in West Sulawesi, caused severe damage to more than 279 houses, including the office of Governor West Sulawesi, and resulted in 84 fatalities. Our results saw this earthquake caused by movement on faults within the Majene Fault and Thrust Belt. The next is 2021 Semangkobay earthquake sequence. This earthquake, starting from 30 June 2021 in southernmost Sumatra, in particular in Semangkobay. So our results show that this earthquake caused by several andesitic faults that are similar to the West Semangko fault, and this fault actually part of small graben system, which was located in the Sunda Strait and activated by ongoing extension in this area. The next is magnitude 7.3 Forest earthquake. This earthquake occurred on 14 December 2021. Quite a lot of destruction in forest islands, up to 6 on the mm scale in this region. And tectonic setting in this region quite interesting because here are transition zones from subduction to collision, and you can see here several destructive earthquakes followed by tsunamis in the 60 years ago. And based on the seismicity data, in the last 6 years, there have not been any shallow earthquake with magnitudes more than 7.0 in this region. And actually this area dominated by a deep earthquake. Our results show this earthquake caused by movement on fault, then we call a skeletal fault system, and divided into 3 segments, and all of these reveal structural fault mechanism. The next is Pasaman earthquake in West Sumatra. This earthquake produced a stronger motion up to 6 on the MMS scale in Pasaman, West Sumatra region, and it damaged more than 1,700 houses and caused at least 18 fatalities in West Sumatra. And you can see here, in the last 6 years, there have not been any shallow earthquake with magnitude 6.0 in this region, but in neighborhood, there have more than 4 earthquake with greater than 6.0, including in 1977, Jobat earthquake in 2007, and in Traslep Badang earthquake in 2009. Based on our result, this earthquake caused by newly identified fault, then we call as a Kajai fault, which is parallel to the Great Sumatran Fault System, and focal mechanism solution reveal right lateral slip faults. The next is Cianjur earthquake. This earthquake occurred on 21st November 2021. Even though this earthquake quite low magnitude, unbelievable, this earthquake damaged more than 40,000 houses and caused at least 321 fatalities. The Cianjur region actually covered by young volcanic deposit from surrounding volcanoes and traversed by Chimari fault with a total length about 100 kilometers and divided into 3 segments. While the behavior of this fault is relatively well understood, Cianjur earthquake was not located along any of recognized segments. And Cianjur area has experienced events of magnitude 7 to 8 in 1834 and 1879. However, due to limited station coverage during that period, the source fault of both earthquakes could not be meaningfully constrained. So our result saw this earthquake caused by conjugate pair of faults trending north-northwest to west-southwest and south-southeast to east-northeast. The next is Jayapura earthquake sequence. This earthquake starting from 1st January 2023. You can see here, quite interesting because this area surrounded by thrust fault mechanism, but our results saw this earthquake in northeast to southwest and focal mechanism solution normal fault. The next is Bawean earthquake. This earthquake occurred on 22nd March 2024 in Java Sea, north of East Java. Usually this earthquake dominated by deep events caused by subductive slab of Indo-Australian plate, but our results saw this earthquake caused by newly identified fault trending northeast to southwest, and focal mechanism solution reveal left lateral slip faults. The next is Kolaka southeast Sulawesi with magnitude 5.1. You can see here distribution of earthquakes quite far away from a fault line, and our results saw this earthquake caused by newly identified fault trending northwest to southeast, and focal mechanism solution reveal normal fault. The next is Poso earthquake with magnitude 5.8 on August 2025, few months ago, and our results saw this earthquake was not located on the Carol fault, but from supply or imbricate thrust structure in this area. The next, actually, few years ago, we deployed several Borgla seismometer along West Java Big Arc Thrust, and our results show that the Big Arc Java West Java Big Arc Thrust is active. In particular, previous studies said this fault is potential active fault. We conclude this earthquake is active fault and characterized by thrust fault mechanism. The next is Bekasi earthquake. This earthquake occurred on West Java Big Arc Thrust with focal mechanism solutions via thrust fault mechanism. The next, this is the last slide. So, few months ago, two earthquakes occurred in different area and different regime, and our results of this earthquake, in particular in northern part, caused by extension of Flores big actress in northeast Java. So here are the concluding remarks. So several recent destructive earthquakes in Indonesia serve as a reminder that shallow crustal earthquake caused by active terrestrial faults, in particular located near large population center, pose a major natural hazard. Mapping this active fault is very important for seismic hazard maps and understanding their implication. However, without implementation of building codes, seismic hazard maps are nothing. Thank you very much.
So let's move to the next speaker, Dr. Dimas from STMKT, please.
Hello everyone, thank you very much for having me here. Today I'm going to present part of our work to understand the rupture behavior along the Sunda Banda Arc in Indonesia. So as introductions, that the Sunda Banda Arc in Indonesia belongs to the Eastern Tethyan tectonic domain, where several key tectonic processes remain poorly understood. And in this Sunda Banda Arc, we have tectonic transitions from the subduction zone at the Sunda or Java Trends to the continent arc collisions at the Timor Trough. So our current study is trying to review the rupture behavior of large earthquakes in the Sunda Banda Arc and the spatio-temporal seismicity patterns across the western and eastern Sunda Banda Arcs, and discusses their possible relations to the tectonic processes. So there are three key questions here. I think the first question will answer the previous question from Professor James Mori. Where will the next impending large megathrust rupture occur along the Sumatra subduction zones? So we will focus on a zone we call the Mentawai seismic gap in the Sumatra subduction zones. The second key question here is, why do historical and instrumental records indicate no occurrence of large megathrust ruptures, saying magnitude larger than 8 in the subduction zone south of Java? So if you see some previous studies, there is no indication of large magnitude larger than 8 earthquakes in the subduction zone south of Java. And the third key question here, why are back arc thrusting faults highly active in producing cascading moderate to large earthquakes in the eastern Sunda Banda Arc? So we will go first to see the seismicity of Indonesia. If we plot only the deepermost earthquakes in Sunda Banda Arc, we can see here the deepermost earthquakes extended just from the north of the Java to the around the Wetar region in the eastern Sunda Banda Arc. And then if we move further to the intermediate depth earthquakes, we can see some pattern of the intermediate depth earthquakes. For example, here there are some clusters of intermediate depth earthquakes in Sumatra and also in central part of Sumatra. And then if we look for another intermediate depth earthquakes that has shallower depth, we can see here some interesting pattern. For example, here near the Toba supervolcano that may be related to the slab window beneath the Toba supervolcano in Sumatra. And these are the shallowmost earthquakes in these regions. To understand the rupture behavior in these regions, we conducted finite fault inversions. I will not go in detail because of the time limits, but in these finite fault inversions, we use the body wave and surface wave seismographs as our data to concern the rupture model of the large earthquakes in these regions. We also conducted our column stress changes analysis and then hypocentral relocation using double difference algorithm and statistical analysis of the seismicity. So let's move for the first part to the Sumatra regions. So the question here, where will the next impending large megathrust rupture along this Sumatra subduction zone? If you see here, in the northern part, of the Sumatra subduction zone, it has been ruptured during the 2004 magnitude 9 earthquakes. And the southern parts, generally it has been ruptured during the 2007 large earthquake sequence. And then there is a regions that remains, there is no large earthquake in these regions, but historically there was a magnitude larger than 8.7 in 1797 and larger than 8.8 in 1833. So this region is what we call the Mentawai seismic gap along the Sumatra subduction zones. And then from the current studies, we understand that from the nearest region here in the Sumatra subduction zone, we observe the updip and downdip after slip, and then outer rise normal fault here near the nearest regions. And then also the same in the south. We observe updip and downdip after slip region here in the region of the 2007 southern Sumatra earthquakes, and also outer rise normal faulting earthquakes during the 2010 Mentawai earthquakes. And then this region is what we call the seismic gap that probably can be the future rupture of the next large impending earthquakes. And in 2022 to 2023, there is an increase of seismic activity in this Mentawai seismic gap. So we conducted the final fault inversion here. You can see here there was a magnitude 6.7 here, 6.7 here, and another is earthquake with magnitude 7.1, rupture mostly in the northern edge of the Mentawai seismic gap. So this is the waveform fittings of our rupture models. And then we conducted a kinematic source analysis of these recent earthquakes, and we found that they are located along the northern edge of the Mentawai megathrust segment, which is widely recognized as a seismic gap. But although these events release a small portion of accumulated slip budget in the segment previously ruptured during the 1797 and 1833 earthquakes, a substantial amount of potential slip remains. So we conducted our column stress changes analysis, and we conclude that this seismicity of the recent earthquakes can contribute to the stress concentrations near the boundaries of impending rupture of the Mentawai seismic gap. And then we move to the Java, the subduction zone south of Java. The question here, why we don't observe any large megathrust earthquake saying magnitude 8 in subduction zone south of Java. So there is a substantial difference between Sumatra and Java subduction zones. The oceanic crust south of Java is significantly older than the west of Sumatra, which results in a steeper subduction zone beneath Java than Sumatra. So we do not observe any magnitude larger than 8 earthquakes in the subduction zone south of Java. Instead, most of the damaging earthquakes are intraslab events, such as the 2009 Tasikmalaya earthquakes and 1921 event that analyzed by Professor Emil Okal in his publication in 2012. This is a very famous publication that he concluded that there was no record of the historical and instrumental data of the large earthquakes in the subduction zone south of Java. And as I mentioned before, most of the damaging earthquakes, both in the historical era and the instrumental era, are the intraslab events. And we conducted our final fault rupture inversion for all possible large earthquakes in Java, and found that they are located in the intraslab regions. And the sources of these damaging intraslab earthquakes exhibit simple rupture characteristics, typically involving a single and compact asperity. So it's very small asperity with a single triangular source time functions. So meaning that they are high stress drop events, and high stress drop events indicate that a large amount of seismic energy is radiated from a small region of rupture and choose within a short duration. This results explains why in the historical data we observe many intra-slab damaging earthquakes in subduction zone of Java. And then if we see the seismicity south of Java, most of the recent seismicity is located in the down deep part of the subduction zone. So we conducted our hypocentral relocation and found that most of the seismicity south of Java originates from the backstop thrusting in the forearc region rather than at plate interface. So we suggest that the subduction zones south of Java being a creeping or partially creeping subduction zone, as also suggested by previous studies. And then for the next questions about why are backup thrusting fault highly active in producing cascading moderate to large earthquakes. So if we see here, a lot of moderate to large earthquakes in the eastern Sunda Banda Arcs originated from the backup regions. So we conducted our source study here, and in general, we found that our finite fault model suggests non-overlap asperities areas. For example, in 2002 to 2009 Sumbawa earthquakes and to 2018 Lombok earthquakes. So for our conclusions here, indicating that the rupture pattern and seismicity distribution suggest features along the immature or Yao fault zones, with the eastern segments of the Flores or backup thrust more mature than the western segments, suggesting the backup thrusting is more closely related to the stress propagation from continental arc collisions during Pleistocene and propagated from east to west. I think that's all my presentation. Thank you very much.
Thanks, Dr. Dimas. So Dr. Sigit will talk about volcanic structures and borehole observations, please.
Good afternoon, everyone. My name is Sigit Pramono. I'm from the Engineering Seismology Division, and thank you for moderator having me time to deliver my presentation today. And I acknowledge to my team from the Engineering Seismology Division collaborate with me to prepare for the material presentation. And this today will deliver from a presentation about the influence of the shallow volcanic geological structures on the ground motion based on the seismic observation. And this the outline is the earthquake engineering surfaces in our division, and then the instrumentation and historical monitoring of the borehole station. We take the location of the CBC borehole station, and then the purpose for engineering application in use and in EWS prototype, and then the geological material, set survey related with the geophysics method, and then the comparative assessment of field survey, and then analysis of seismic borehole, and then the conclusion. And this is the background and related with our talks in the engineering seismology division. So we are the bridge between the seismology and the engineering. So we have provided the information related with the what we need in engineering, but in the seismology, not pure talk about the seismology, but in here we provide related with the what the need technical, and then the information related to the hazard, like the hazard analysis from the strong motion sensor. And in here we concern about the strong motion sensor from the borehole station. And this is the location of the borehole station related with the interest location related to the topic. We choose in the one location in the CBC. So this is the one island in the Sunda Strait, and this is the very crucial location because it's the many factor and many source of the hazard can be detected from the area. And from the BMKG program before until the 2022, we already installed in the Padang and then Bali and then Depok and then Tangerang Selatan. And then 2025 with the E3 program, we already conducted, installed the new borehole station in the Sulawesi, and then in Jakarta, and then Lembang, and then the Sukabumi. And then this is the location of the borehole station in the Sulawesi Island. So this is the location in the South Lampung region in the Sulawesi Island, and approximately 2 meters from the coastline, and then less noisy than the caused by the cultural activities, and then the mobilization to the eastern with limited transportation because the very limited area, and then they experience some troubles in drilling process because of the soil layer and then limitation in electricity. And this is the location. This we can measure from the source of the earthquake, like from the subduction zone, and then the fault in the Sunda Strait. We have a look at that, so we can see, or we can see in like the closest of the fault, like the 35 kilometer, and then the from subduction zone 107 kilometer. And this is the utilized of the data from the borehole station in our program in the BMKG, in the first from the engineering application, as a reference for infrastructure development, and then the constraining amplification factor, and then the set specific ground motion model in the volcanic region. And then the innate use detecting micro-earthquake properly, and then the producing less noisy data for earthquake analysis, and then mapping earthquake source that is still unrecognized. And then from the innate use, from the rapid detection from the earthquake event, and then producing reliable data for earthquake detection. And this is the location in the Sulawesi Island. So this is the borehole station. So in the close to the coastline, and this is still in the sedimentary zone in the Sulawesi Island in the volcanic area, and formed by 3 major episodes. If we historical about this, the area from the Proto Sulawesi, and then the Old Sulawesi and the Young Sulawesi. And Eastern Quarter Plain borehole station are formed by strong northward long shore currents that the transport and deposit coastal sediment over all the volcanic unit, creating a flat lowland distinct from the rugged volcanic highlands. And we decided the location in here before the manufacturer. We have to consider to operate this instrumentation, because before we already installed in this location from the surface installation sensor, from the innate use sensor. So we will combine between the downhole sensor and then the surface sensor. And this is the sample of the rock from the location, like the more than 56 meter or 46 meter. So we got the condition of the breccia, but in here we found there is the alluvium in the upper of the location, and this is the many type of the volcanic deposit we already found when the drilling process. And this is the very big effort and the difficulties to do the drilling, because this is the many obstacle related with the condition of the rock, and then there's the many factor and something like that. And this is the geoelectrical survey. This is mentioned. This is describe about the condition of the in the upper. This the beside this and in the alluvium. So this we, and in the andesite we already found in the some upper, and then alluvium, and then the andesite, and then the basalt under to going to down. And this we do the geophysical method survey. This using the SPAC. So we using the for sensor. So we have the engineering seismology, and with the standard value 760 meter per second. So we we determine the depth of the engineering bedrock this until the 260 meters. This is the inversion using the single inversion from the noise, where we can determine the vertical profiling in the located on the borehole station like this, and this is the very significant increase in the almost in the 20 meters, and then that, and we make the comparison. Sorry. As this is the yes, this is the from the MISW, especially using the artificial source. We detected from the 30 meters, so we get the description of the conditional of the subsurface from the VS 30, and then we make the comparison between the HVSR and then the SPAC method, and there is no many significant, and then this is we have the comparison between in the surface and then the borehole station, and in here before in the surface, so we can hear this the noisy, but in the borehole station this is the decrease. So in the band of the period of the frequency, this already decreased. And then this is the sample from the Jakarta event for magnitude 4.7, and this is the very clear the noisy for the borehole PSLEB, and then the surface we still having the noisy in the before the event. So I think this is very useful for the clearly to detect the first arrival. And this is the conclusion, the earthquake event in Jakarta South great contribution, and then the volcanic background type profile, the axial composition, volcanic deposit material, and furnace alluvium in the upper deep. And we hopefully we consider to scope utilize in the scope of innate use, use, and engineering. Thank you.
Thank you, Sigrid, for the good seismic waveforms. The last speaker is Lin Tang. He will talk about structural Sulawesi from teleseismic P-wave tomography. Please.
Thank you so much. Good afternoon, everyone. My name is Lin Tang Kusumastuti, and thank you for being here today. So it's a great honor for me to be here today to share my research beneath Sulawesi. So my research, entitled Evidence of Multiple Subducting Slabs Beneath Sulawesi from Teleseismic P-wave Tomography, was published in Geophysical Research Letter this year, and it was conducted in collaboration with my supervisor in KVUPM, and then the University of Cambridge, and also BMKG. And let me start with a basic question. Why Sulawesi? We know that Sulawesi is a very complex tectonic region where we can see here the tectonic evolution of Sulawesi map by Hall in 2012. We can see Sulawesi has evolved through tectonic processes that are very complicated, such as collisional events, rifting and accretion, and also opening and closing oceanic basin. I'm sorry. So we can see it's very complex tectonic region, Sulawesi. So there are tectonic features beneath Sulawesi that are not fully understood by previous studies. Now, here are the complex geological feature in Sulawesi. For example, the first one is multiple subducting slabs in the northern region. As we know, there are multiple slabs in this region. And then the second one is strike-slip Palu-Koro fault zone, as we know that it is a major active in Sulawesi. And also the isolated active volcano in the Gulf of Tarini, where it is not derived from volcanic arc, produced from subducting slabs. But due to the limited time, I just want to focus on the first one. So the geometry of multiple subducting slabs in northern region of Sulawesi are still debated. So there are several seismic tomographic studies that has been conducted to produce 3D velocity model at global, regional, and local scale. And for example here, at global scale, Hall and Spackman in 2015, using global P-wave velocity model, identified high velocity anomalies beneath northern Sulawesi. As you can see here, the blue color. And based on seismicity and his tomographic model, they illustrate the slab configuration like this. If you can see in this picture, the green color is Sangiha slab, and then the blue color is Celebes slab, and the pink color is Sula slab, which spans from 120 to 124 degrees. However, they have a limited resolution, around 100 to 200 kilometers, so it limits the ability to see the detailed insides of upper mantle beneath Sulawesi. Now, at the regional scale, Werner et al. In 2022, they use a joint waveform in tomography for Southeast Asian, and they revealed high velocity anomaly beneath northern Sulawesi. However, they don't specify whether it is Celebes slab or North Dipping Sula slab. And at local model, Jayadi et al. In 2023, they use local earthquake tomography to map the P-wave velocity model in beneath Palu-Koro fault. However, they have limitations, such as they limited to areas of active seismicity, and then they only relied on sparse seismic network, only 20 seismic network, and then only map shallow structure at depth of 50 kilometers. So we can say that there is no high resolution 3D imaging capable of revealing the detailed structure of upper mantle beneath Sulawesi. And we have very good opportunity here because BMKG expanding the broadband seismic network in Sulawesi. So thanks BMKG. So what we did is we used the seismic tomography to have relatively high resolution 3D velocity model beneath Sulawesi and investigated the geometry and depth extent of the subducting slabs beneath Sulawesi. So these are the data that we used. We can see here, this map shows the distribution of 89 seismic stations operated by BMKG, spans from January 2020 to October 2023. We use the seismic recordings, and for the teleseismic events, we use the earthquake parameter from IRIS. And you can see here, this is the distribution of teleseismic events that we use. And for the methodology, the first step is to prepare the data for inversion. And using adaptive stacking, we can get the travel time residual. So for each event, this is one event, and this event has many traces, and these traces were initially aligned with the global model AK135, and then by using adaptive stacking, we can get the travel time residuals, and this residual shows how much earlier or later seismic wave arrives compared to the reference model. And from this pre-processing, we have around 40,000 residual times from 985 seismic events. And then for the inversion, we use FM Tomo package, and basically these are the steps of tomographic inversion. And to assess the near surface effect, we incorporated the crustal model from Dr. Nova in 2024 and Moho Depths from Linang in 2023. 22. And from the information, we got the 3D velocity model. However, we need to know, before showing our tomographic model, we need to know how well the data constrain the model and to identify the well-resolved region. So we did a synthetic test, resolution test. The first test is checkerboard test using alternating high and low velocity pattern. And we did 3 different checkerboard tests. And then we also did a sparse spike test, and we distribute 5 different locations of spike. And also we make synthetic slabs to know if our model is good. So these are the checkerboard test results. The output model can recover in the input model at the most region, as you can see here. The output model can recover the input model at the most of region beneath the seismic network. And we can see the smearing effect at the edge of the model due to the ray path coverage. And then for the sparse spike test, most of the input spikes are well recovered with position and amplitude closely matching the input model. And these are the results of slab synthetic test. We can say that the resolution test confirmed that the 3D velocity structures are well resolved in most regions in Sulawesi, which supports the reliability of our interpretation. And these are our tomographic models. We can see high velocity anomalies indicating multiple subducting slabs at the red block in the northern Sumatra. And the green color shows high velocity, brown color shows low velocities. And we can see the slabs at depth range of 100 kilometers to 250 kilometers. And also we created north-south cross-section to know the high velocity of multiple subducting slabs in the northern Sumatra. And we found H1, H2, H3 as south dipping slab, north dipping slab, and west dipping Sangihe slab. If we recall the slab configuration from Hall and Spackman in 2015, the depth extent of slab shows deeper than previously reported. And then there is no evidence for the north dipping Sula slab west of 122.5. And the resolution and the synthetic test confirm that it should be feasible if there is slab here. If there is slab here, we can see profile B. It should be here. There is a high velocity anomaly, or H2, if there is Sula slab here. But we don't see it, okay? For further investigation, we created a profile across the proposed tiles. We can see AA prime profile. And again, our model confirms the absence of high velocity regions, north dipping Sula slab. AA, there is no H2 here. And we want to know the depth extent of H2 or Sula slab. We found the depth of H2, north dipping Sula slab, reach up to 350 kilometers. So we interpret the three slab interpretation, but revise the geometry by limiting the north dipping Sula slab to east of 122.5. These are our model from the slab configuration of our model by considering the geological constraint from Hall and Spackman in 2015. So this is the conclusion. Thank you very much for your attention.
Thanks for your talk. Now it's a discussion session. Any questions for the above 4 talks?
over there. Oh.
Hello, good afternoon. Thank you for the opportunity. Good afternoon, everyone. My name is Kike Salsabil Azara. My question goes to Mr. Sigit. I have two questions. The first one is about the HVSR result. The first one is how much the standard deviation you use to do the HVSR inversions. And also, there is a very thick low velocity zone between 23 to 26 meters depth. My question is, what caused this phenomenon, and do you ever validate or compare the low velocity zone with others' data to support this result? Thank you.
Which one?
Thank you for your question. Could you please repeat from the second question? The second question.
Oh, the second question is, I saw in the slide 11, there was an image about HVSR inversion result, and there was a very thin low velocity zone between 23 to 26 meters depth.
Okay.
So what caused this phenomenon, and do you ever compare or validate to support this result?
Okay, thank you for your question. I would to answer your question, the first related to the standard of the SR, our process for that, our sampling from the noise in the PSLA station. And we already done for processing that in the waveform. And the first, we look at the result first of the default the standard deviation, and then we make the justified, and then mention or not related with the condition and then that the result. For example, we have the sampling like the alluvium in the depth of the borehole in the 30 meter until 20 meter. So this is the peak of the SVSR, the very high. So I think this makes sense. So because if the location in the volcanic, if I choose the location in the top, not in the sedimentary, I think this use should be flat, and the peak of the SVSR. But actually the result of the SVSR in the sedimentary, and we doing then we doing the boring. We found that in the alluvium material, so the peak the very high, and then in the one peak, not multiple peak, and I think this makes sense to describe the actual condition, and then the processing of the waveform, the sample noise from our data. And the second question related with the condition, the very increase in the shallow depth. Yes, actually because we not choose in the middle on the top on the Sibisi Island in the volcanic peak. So we chose but we choose in the sedimentary and close to the coastline. So over there we can see there is any the alluvium, and then so we found from the boring, so found the alluvium material, and I think from the VS very low, and approximately maybe 100 until 200 meters per second, and then going up to in the more than 20 meters until the 500 until 600 meters. So very increase. I think that's all. Thank you.
Yes, I have a question to Dr. Diamas Sianipar, if I'm correct. You talk about the lack of big events in south of Java.
Yes.
But we know that due to elastic rebound, we often have cycles of sinking or uplifting of islands in other parts, similar to what happened in Bande Aceh in the last big earthquake. Have you or anybody else has tried to find any evidence of such events in southern Java by studying coral reefs or any other evidence in the coastal region?
Okay, thank you. This is a good point. So the difference between the Sumatra subduction zone and the subduction zone south of Java is very important, because in the Sumatra we have the 4 arc islands. For example, the Nias Island, Mentawai Islands, and Enggano Islands. So previous studies, they can conducted the analysis on the coral uplifting data, even to they can possibly to infer for the rupture dimensions of the previous historical earthquakes. But in certain part of Java, we don't have this 4 arc islands. It is so different with the Sumatra. So we don't have any evidences of historical earthquakes from coral uplifting data. And also our GPS observation or GNSS observation the resolution is not so good, because most of this GNSS stations are located in the Java, inland of Java, and we don't have a good resolution of the data from the beneath the sea south of Java. So this is the crucial difference. So I think there is no evidence so far from the coral uplifting data from subduction zone south of Java, but several evidences are coming from the records of the historical damaging earthquakes. But some previous studies, they try to, even for our group, we try to model this historical damaging earthquakes, and we found that almost all of these damaging earthquakes are intra-slab events, not events that occur in the plate interface in the Java subduction zone. Thank you.
Yeah, sorry. Still for the Dimas. My question is, according to you, is it possible that in Java is magnitude more than 8 based on the catalog data and also on the tectonic setting?
Yeah.
And why?
Yeah. That's also a good point. So I think there are 2 models now. The first model is the one that shows that the subduction zones south of Java is a huge seismic gap from the western part to the eastern part, that several previous studies also model the possible ruptures of these scenarios, and they try to produce the tsunami simulation from these kind of models. In this presentation, we try to propose a different hypothesis, because the first, Professor Kelin Wang and his group, they conducted analysis, and they found that the subduction zone south of Java, the seafloor is very rough. That may be the indications of the aseismic creep. So they proposed, Professor Kelin Wang proposed that subduction zone south of Java is aseismic creep subduction zone. And another groups, they try to use the geodynamic modeling. They also propose that subduction zone south of Java also as a creeping subduction zone, not a lock subduction zone. So the question remains, so our group now is trying to analyze more seismicity data from this subduction zone, and we try also to use the geodynamic simulations, trying to understand whether this subduction zone of Java is lock or creeping segments. I think that's...
So you answer yes or no? Possible or not?
Yeah, if we look for the hypothesis that it is a creeping segment, so no occurrence of magnitude larger than 8 earthquakes.
No.
Yeah. Thank you. Okay.
There's another question.
Thank you very much. My question for Dr. Pepen.
Okay.
Yes. You are proposing the newly identified active faults, right? So I guess it could be the very significant contribution from BMKG to our national earthquake sources map, right? So my question is actually whether your result has been validate it with the GPS data observation to strengthen your finding? Thank you very much.
Thank you, Bu Suci. Good question. So we ask for information that we have National Center for Earthquake Studies of Indonesia, consists of scientists from different agencies and universities. So they have kind of good discussion from different background, from geodesy or geological approach for the new identified fault. So yes, we need to validation from different method and observations to conclude whether this fault is active and exists on their area. Thank you.
Okay, I think we'll close this session, so why don't we thank all the speakers again. And let's see, what time should we come back? Who knows? Well, maybe we need a short break at least. Should we make a 10-minute break?
20 from 20?
Okay, 5 minutes and come back.
15.
All right, ladies and gentlemen, in a few minutes we will proceed to our final technical session for the day with the session 3 about geochronology, orogeny, and tectonic history of the Tibetan Plateau and Himalayas. And the session will be chaired by Professor Paul Valdez and Professor Xuang Dai. So if you have finished your break, please return to the auditorium and we will commence with the session 3. Thank you.
In particular, can we have the speakers up for the next session? Okay, yep. Hi. So you're first on. Is it? Yeah. Yes. Yeah, that's right. So we're just missing one speaker. Chin Long Ran. Is the one? Are you Chin Long? Okay, I'll start. I'll just introduce very briefly. Okay, welcome to this new session. So this is session 3 of the conference, and it's in 2 parts. We've got 3 talks today, and then 3 talks tomorrow, at, starting at 11 o'clock on this session, which is on the regional geology, tectonics, and basin evolution. And so it's my pleasure to introduce the first speaker, Professor Iftikhar Ahmed Abbasi. Over to you.
Thank you very much. Thank you. Okay. My talk is about foreland basin sediments, the Oman foreland basin. It's about the lithofacies and the provenance of the sediments into the basin. Oman foreland basin is a basin that developed. It's a marine foreland basin, and it developed in response to the ophiolite sequence, abduction of the ophiolite sequence onto the Oman platform sediments. The basin developed in front of the mountains here. That's the Tethys Ocean, and after during the closure of the ocean and subsequent to the closure, the sediments were deposited in a foreland basin here. That's the Oman foreland basin, and the whole basin extends over a very large area in front of the Oman mountains here. So this basin is known as the Aruma Basin here. The mountain belt is this mountain belt here with very high the gravity anomalies because of the ophiolite abduction here. And the basin is developed right in front of the mountains in here in this way. In this work, we have worked on the facies distribution, how the sediments were deposited, particularly during the very early stages of the basin development. So the first sediments which arrived in the basin, how these sediments, they were deposited, and the source of these sediments, whether the sediments, the majority of the sediments were coming from the abducted the sequence, the ophiolite sequence, or they were derived from the cratonic part from the Arabian-Nubian shield area, because these were the first sediments which were deposited into the basin. And the mountain belt, this mountain belt, at that time hasn't had achieved a very significant relief at that moment. A lot of these, this mountain belt was still under the ocean. So if we look at these sediments, the basin itself, just briefly about the Oman mountains and the ophiolite belt. The ophiolite belt is actually is abducted on top of the platform sediments, Miocene platform sediments, and it is comprised of the mantle rocks, the mantle peridotites, the oceanic crust, the banded gabbros, the layered gabbros, sheeted dikes, and very spectacular the lavas. Here, the lava flows here. So that's the general setup of the sequence. It's a very large, thick sequence, very nicely exposed. Overall, the sequence is more than 15 kilometers thick of these ophiolites, and in front of these sediments were deposited. So when the abduction took place, the ophiolites started abducted, then these sediments that were deposited, that's the Muti Formation, that I'm going to talk about it, and these first sediments were derived from either from the ophiolite sequence or from the shield rocks. That's how the sediments look like. That's the Aruma group. These are the first sediments which were deposited in the foreland basin. That's the abducted sequence and the underlying platform sediments. The sediments are usually in the form of thin carbonates and some marl and crusty sediments. So what we did was we measured sections across this area here. All these yellow sediments that you see, the yellow color, that is this Muti Formation here. These are the sediments which are the sections being measured. This Muti Formation in field, it looks like this. It's in different places. The thickness is highly variable, starting from a few tens of meters to hundreds of meters in different parts. That's how it looks like. The sections are in the eastern sections, particularly the eastern sections, they are mainly carbonates. The western sections are mostly clays. That's how these different lithofacies look like. These are highly fossiliferous limestones, and they contain different types of carbonate microfacies. The very important in these carbonates, they are fossiliferous, but they also contain zircon here, some of the zircon grains here. So when we worked in more detail, we found plenty of population of zircons within these carbonates here. Based on these fossils, these are different type of fossils that we identified, and on the basis of these fossils, we dated these sediments from Sinmonian to Campanian in age here. So that means they are mostly in the middle to late Cretaceous sequence. The sediments were deposited from shallow marine to deep marine. It depends. Most of the western ones are in relatively shallow marine. Most of the eastern ones are in relatively deep marine sequences. The zircon that we identified and separated from within these carbonate sequences, these were then separated and dated. The sections are, the zircons are coming from this area here, these areas. And 3 sections we took, 2 sections in the east, 1 section in the west for the dating. And when we analyzed this sequence, most of the eastern section, they have a limited distribution between 900 to 400. But the western sections, which are close to the cratonic side, they have much wider spread here, 900 to, 118 to reaching up to 300,000 here. 300 million years in this part in here. So based on this, when we look at from the distribution, particularly in these sections here, most of this, the zircon that was derived mostly from the Arabian-Nubian shield here, and this is giving us an age of 900 to somewhere up to, 400 up to 900 in these sections here. But when we are looking at the western sections, they are giving us relatively wider spread in these sections here. So the sediments, major sediments, what we have concluded is that they are actually derived from the Arabian plate side. Some of these sediments, the zircon, were derived from these older outcrops, which are Precambrian sediments. They also contributed. A relatively small population was derived from the uplifted, the allochthon, from the ophiolites and associated ocean floor sediments. So some of it was derived from there, but relatively small amount. Most of the amount of the sediments were coming from the western, from the Arabian-Nubian shield area. So the concluding diagram is that major part of the sediments was derived from this Arabian plate here and were deposited into this marine foreland basin here. Small amount was also coming from these small ophiolites, but major contribution of the sediments in the very early part of the foreland basin, marine foreland basin, was from the Arabian-Nubian shield. Thank you very much. Thank you.
Okay, thank you very much. We'll now move on to the second talk, which is Chenlong Ran talking about zircon geochronology and provenance constraints.
Good afternoon, everyone. My name is Chenlong Ran from China University of Geosciences, Beijing. It's my pleasure to share with you our recent work titled Zircon Geochronology and Prevalence Constraint on the Indo-South-Chantan Clishin in the Tibetan Plateau, China. Let's begin with the research background and major controversies. The Bengong-Lujiang suture row marks the closure of the Meso-Tethys Ocean between Lhasa and the Chantan terrains in its eastern segment, where the Indo-microblock is located. The region is regarded as one of the most tectonic complex areas in the Tibetan Plateau. It's widely believed that the Indo-microblock divided the Meso-Tethys Ocean into two branches. The north part of the Indo-microblock expand high pressure metamorphic rocks and ophiolites, which record the subduction and clishin process of the north branch of the Meso-Tethys Ocean. Previous studies on the north branch of the Meso-Tethys Ocean proposed different clishin models. Some suggested that the clishin between the Indo-microblock and South Chantan terrain occurred as early as 181 million years, based on evidence from high-pressure metamorphic rocks. In contrast, based on study of arc magmatism, they proposed the north branch of the Meso-Tethys Ocean had not closed by the mid-Jurassic. However, Zai suggested a later clishin model occurred during 170 to 165 million years. More recently, Gore proposed a different model suggested that the clishin between the Indo-microblock and South Chantan terrain occurred in two different stages. According to their study, the first cliche took place at 181 millimeters, corresponding to the earlier subduction of the mesothetic ocean and the formation of the high pressure metamorphic rocks. The second cliche occurred at 178 millimeters, represent the final closure of the ocean. Based on those studies, we raised our scientific questions. What's the precise time of the collision between the endo microblock and the substratum terrain? The next part, I will focus on primary work and the results. Our study areas is located in the north part of the endo microblock. This region preserves the continual sedimentary records since late Jurassic, providing important information for understanding the evolution of the north branch of the Mesothetic Ocean. Based on previous studies, two major stratigraphic units are expanded here: the late Jurassic Trichala Formation and the Jurassic Endo Formation. We collected and analyzed 9 sandstone samples of the Trichala Formation and 1 turf sample and 8 sandstone samples of Endo Formation. Based on those formations, we conducted multiple previous analyses, including detrital-zircon geochronology, sandstone petrography, and cluster composite analysis. These methods help us to understand the source change of these two formations. The Trichala Formation is mainly composed of weakly metamorphic clastic rocks, and the Endo Formation is mainly composed of sandstone, conglomerate, and mudstone with interbedded turf layers. Zircon edge of the turf from the Endo Formation gives us depositional edge of 176 millimeters, and the maximum depositional edge also supports the edge constraint for the Endo Formation. Parallel current and cluster composition analysis show differences between those two formations. In the Endo Formation, the parallel currents were south or southeast, and the clusters contain more periclastic and gradient gravels. But in the Trichala formations, the parallel currents were north or northwest, and the clusters show a high proportion of quartz and quartzite. In addition, we carry out petrographic studies. The sandstone of the Endo formations contain more volcanic lithical fragments than those of the Trichala formations. When we plot the detrital composition and the Diggins diagrams, we found that most samples may fall in the recycled orange field, and the Endo formation contains some arc-derived detritus. We use kernel density estimation plots on detrital zircon edge data from sand samples to analyze their prevalence variations. Figure A to Figure D represent the Endo formation, and Figure E to Figure G correspond to the Trichala formation. The two formations show differences in their edge distribution. The Endo formation show edge peaks at 182 240 milliyears, and from 400 to 450 milliyears, which are a lot upwards in the Trikala Formation. Then we combine the our edge data and compare them with the data set from the South Chantang terrain and Ando microblock. In figure A, the light blue line presents the Ando Formation, which match the well with the South Chantang terrain shown by the orange field area, and the pink dark the line represent the Trikala Formation, which match the well with the Ando microblock shown by the green field area. We also confirmed the multiple dimensional scaling. The results show that during the deposition of the Trikala Formation, the main source of sedimentary was the Ando microblock, whereas during the Ando Formation deposition, the South Chantang was the dominant source. The next part is the discussion and conclusion. Based on previous study and our new data from Ando and Trikala Formations, as shown in figure, we conducted the evolution of the Ando microblock during late Jurassic to mid-Jurassic. As shown in figure A and figure B, during the late Triassic to earlier Jurassic, both the north and south branches of Mesothelic Ocean was subduction northward, and the Trikala Formation was deposited along the north margin of the Ando microblock. During the mid-stage of the earlier Jurassic, figure C, the Ando microblock collided with the South Chantang terrain, accompanied by high pressure metamorphism, and the Ando aphionized preserves record the oceanic basin. In the last stage, after the collision between the Ando microblock and the South Chantang terrain, the Ando Formation was deposited along the north margin of the Ando microblock, showing by directing sedimentary sources. That's our conclusions. Thank you for your attention.
So the last talk is today is Qinghai from the Institute of the Tibet Plate. Okay.
Okay, ladies and gentlemen, dear colleagues, I'm pleased to have the chance to discuss the seawater retreat history from South Tibet. Okay, as it is generally accepted, the existence of high Tibetan plateau affected the climates and the environments in India, South China, and Southeast China, causing a humid climate in those areas. Without a Tibetan plateau, those areas were supposed to be as arid as the Sahara Desert. Some recent study reveals a very complex history of Tibetan plateau uplift. That it shows that the different areas have different uplift history. The Tibetan was formed not in a uniform way, but separately. But nevertheless, surface uplift from all areas must start from sea level to the present elevation. Regarding the South Tibet, at least the three processes are involved during the growth of South Tibet. First, the initial Indo-Asian collision, which took place under the seawater. The second is the seawater retreat and the disappearance of the Neotic Ocean. Afterwards, the South Tibet uplift from sea level and to the top of the world. Therefore, the seawater retreat can be taken as the minimum age control as the Indo-Asian collision, and also taken as the onset of surface uplift of South Tibet. So this simplified geological map shows the study area in South Texan Himalaya, Qingzhi and Guru. People who worked in the Tibet know that the Texas Himalaya can be divided in the northern part and the southern part. Our study area located in the Qingzhi Guru, southern Texan Himalaya. So the Paleogene strata are well preserved in some isolated areas. The lithologies are very clear. From the bottom to top, there are limestones, green beds of silica-clastic rocks, and the red beds of silica-clastic rocks. But however, different scholars adopt different schemes for the stratigraphy, which makes the stratigraphy quite complicated for newcomers. Here, for simplicity, I refer from the bottom to the top as the limestone, green beds, and the red beds. The green beds in South Tibet represent the youngest marine deposits. So the first report on the age of the youngest marine deposits comes from 20 years ago. Based on studies of nanofossils, some scholars suggest that seawater retreat occurred at about 34 to 38 million years. However, from the same area, Qingzhi, some independent working group studied the pelagic foraminifera and restudied the nanofossils, but they come to a very complete conclusion that the seawater retreat occurred about 50 million years ago. In those studies, here are one for our studies. We also propose that the at Qingzhi seawater retreat occurred about 50 million years ago. However, in 2016, Atkinson's working group claimed they find the latest marine fossil at Guru. Therefore, they again revived the opinion of the latest marine seawater in South Tibet. So in this study, we conducted the study pelagic foraminifera, large benthic foraminifera, detrital zircon, uranium lead aged, and the strontium isotopes in South Tibet with a major focus on the Guru area. So the fossils from the limestone and also strontium isotopes suggest that the depositional age of the limestone start from 62 to 53 million years. Regarding the green and red beds at Guru, we find a well-preserved pelagic foraminifera. We find there are similar pelagic foraminifera assemblage in green and red beds. And we also find the coexistence of Cretaceous and Paleogene forms in those beds. But the youngest forms from the green and red beds show the age of 49 million years for the depositional cessation. Except for the forms, we also analyze the detrital zircon uranium lead ages. We find a youngest peak of about 50 million years, confirming the previous result that the youngest peak is result from the input of material from the nearby Gandhis arc. An interesting finding is that in the youngest peak, we find a near continuous age record from 49 to 56 million years. Among thousands of detrital zircon ages, there's no zircon age with age younger than 49 million years. Not only us, but also other working groups, they also report the youngest zircon age of 49 million years. Therefore, we interpret this phenomena as that the deposition cessation happened at 49 million years. This result is consistent with the foraminifera result. So this figure shows some key fossils for the biostratigraphy at Guru. This is the age for the strata. Here comes the question, why Atkinson claimed they find the latest Eocene fossils. They said they find two key fossils, but only one fossil with photomicrographs, this one. We also find these fossils, but they defined this fossil as a cubensis, this latest using fossil, but we find this determination may be problematic. We think this fossil should be a costulata. This is a reworked Cretaceous fossil. So combined with other people's work, we think that the Indo-Asian collision first occurred at about 65 to 60 million years ago, forming fall deep at Sandaling area. At about 56 million years, collision signal migrated to the Qingri area, first forming a fall barge, and during 53 to 49 million years, causing a fall deep in this area. At 49 million years, seawater retreated from the entire Chechnya Himalaya with the formation of a wedge top. Later on, the foreland basin migrated to the Lesser Himalaya and Sub-Himalaya. At about 40 million years, seawater retreated completely from the entire Himalaya. So we also compare the sedimentation history in the west of Chechnya Himalaya, of, let's say, Zangsaka, and the east. We find almost similar or even identical sedimentation history. Since the sedimentation process in the Paleogene is mainly controlled by the Indo-Asian collision, therefore we refute a diachronous collision process from the west to east. Instead, we propose there should be a synchronous collision, at least between the east part and the west part. So here's the conclusion. The depositional age of the limestone green beds and the red beds are 62 to 53 to 49 to 49 million years respectively. Seawater completely retreated from the Chechnya Himalaya at 49 million years, which implies that the initial Indo-Asian collision should start before 49 and the surface uplift of South Tibet began at 49 million years. Thank you.
So this is our half section about section 3. Dinner is important, but I think the discussion is more important. So the questions.
Have found some detrital ophiolite massive, like ultramafic rock or spinel from the Samuel ophiolite.
Okay, well, this is a very common question which is asked, and I mean, you have a very good point to that. The ophiolites.
Do you find some ophiolite material in the Arman foreland basin?
Yeah. Most of these old age zircons, mostly these are coming from...
Yeah, the zircon is rare.
Yeah. But from the ophiolite, in some part of the sediments, particularly close to the abduction, in very proximal parts, there are some sediments, some material which is being derived from the ophiolite. Not mostly from the ophiolite, but the associated ocean floor sediments, the chert which is associated with the abduction, that chert is found in some of the sediments.
Okay.
But any major contribution from the ophiolites, that is not much reported. We did not find any rutiles in these ones. Zircon, yes. Maybe even if there was some sediments coming from the ophiolite, might have been then oxidized or changed and not preserved completely into these ones. And the reason also could be that maybe this electron, this sheet, the abducted sheet, in the early part, it did not actually attain a good relief. Maybe it was mostly still buried under the ocean water. So that's one of the reason that The major contribution is not from the ophiolite as such, but from the peripheral bulge and also from the distal part of the craton area, the shield area. Most of the sediments are coming from there.
Okay,
And the edges are also
I
pretty
get
broad,
it.
yes.
Yeah, thank you.
Can I ask a question while you're here? You mentioned there was very high orography, significant orography in the region. Would you care to speculate how high it was and how important was it for the erosion processes?
What actually I was mentioning was about the overall thickness of the ophiolite sequence and the Havasana. So if the whole sequence, the abducted sheet, the allochthone, is estimated to be something like 15 kilometers thick. The initial part when this the foreland basin was developing, the topography was not high. Most of the topography was actually attained during the Miocene time when the collision took place between the Arabia and the Eurasian segments. So initially part, the sheet was there, but not very high. It was later on that it actually attained the topography, but that was during the Miocene time.
Thank you.
Yes.
Well, thanks to all speakers. I have a question for Xinghai on your last conclusion. First, let me say I find it absolutely important to study marine rocks in high elevation regions because marine rocks are absolutely essential for understanding paleoaltimetry. You find a marine rock, you know where you are in terms of surface elevation. You said the last time you see marine water is around 49 million years, and I totally buy this. What's the logic then to say that the surface uplift of southern Tibet must be older than 49? Could you just say 2 more sentences about what the logic is behind that statement?
So, unless do mean there's 2 ages, one is 49, one is 40, right? The 49 is, is the age for the testing Himalayas rise above the sea level, because the migration for foreland basin is from the north to the south. So they drive the seawater flow sequentially from the north to the south. The 40 million years is not from my work, it's from the literature, but I think it's somehow reasonable because it shows the seawater retreat from the lesser Himalaya or sub-Himalaya should be later than 49 million years.
Can I have I think a quick question? But can you, from the forums, say anything about the water depth as the seaways were closing?
Actually, at about 56 to 53, the water depth is relatively shallower because the larger foraminifera usually live in much shallow water, about less than 100 meters. But for the green beds, the planktic foraminifera may live in the open ocean, should be, because there's a formation for the fall deep. The water should be about, let's say, outer shelf environment, it could be hundreds of meters. In the end, the wedge top deposition, I think, is completely from the ocean. It's already on the continent, on land.
Okay, so I think time is up and I don't want to stop anybody from the dinner. So I think we've finished today's sessions, and so I thank you again for all the speakers today. Thank you.
Okay, ladies and gentlemen, once again, please give a round of applause for the chairs and speakers of the last session of the day. Thank you. And we have successfully completed the highly productive first day of the second PlateauPlus workshop, starting from the Keynote session 1 this morning through the opening ceremony and across to the session 3. And with that, the formal technical session for Tuesday, November 25 are officially adjourned. And for all other participants, we thank you for your active participation today. And we look forward to welcoming you back tomorrow, Wednesday, November 26, for Keynote Session 2, which will commence promptly at 9 at local time here in the BMKG Auditorium. Have a pleasant evening and a good rest. Thank you.